In section A1, we're going to cover some algebra essentials. A set is a collection of objects. And so we can write something like, let A be equal to the set, and we use a brace, and what goes inside the set are what are called elements. So we can say, let A be a set with the elements of 2, 5, 8, and 17. We can let another set B be defined as the set of consisting with elements 1, 5, 17, and 18. With sets, we can take something that's called an intersection or a union. The intersection of two sets, so the intersection written like this is called A intersect B, basically means it's asking for the set consisting of all the similar elements that are in both, so it's all the elements in A and B that are both in A and B. So what elements are both in A and B? Well, both A and B have 5, and they both have 17. So the intersection, A intersect B, is the set of 5 and 17, since both A and B have 5 and 17. So this is intersection. The other thing we can do is take a union. So union, and this is going to be written with an upside down, so like a U. A union B, and this is all the elements that are in or B or both A and B. So the union of this means basically every single element that there is. And what elements do we have? Well, we have a 1, a 2, a 5, 8, 17, and 18. So again, so 1, 2, 5, 8, 17, and 18. This is the union. Now, if we define our universal set, capital U, and the universal set basically means all the numbers that we're going to be dealing with in this problem. The universal set, let's just say, be all the numbers 1 through 5. So 1, 2, 3, 4, 5. The universal set is that, and we'll define A to equal 1, 4, and 5. Then what we define to be the complement of A, and we're going to write it as A with a line over it. The complement of A is basically everything that's in U but not in A. So this is everything in U but not A. So U is 1, 2, 3, 4, 5, and A is 1, 4, and 5. So the complement of A is going to be 2, 3, since 2, 3 is in U but not A. If we defined B to be the set 1, 2, then, and we calculated what A union B is. And what is A union B? Remember, the union means all the elements that are in A, or all the elements in B, or all the elements that are in both A and B. So we look at all the elements in B and A and combine them all together. So we have a 1, 2, 4, and 5. So A union B is 1, 2, 4, and 5. What is A union B complement? The complement means everything that's in U, 1, 2, 3, 4, 5, but not in A union B. So not 1, 2, 4, or 5. Well, that leaves us with just 3. Since 3 is in U, but it's not in A union B. 1, 2, 4, 5 all are in A union B. So the complement is just 3. Thinking in terms of a Venn diagram, if you recall what a Venn diagram is, that's those circles that we see overlapping. So if we have this left circle is A, and we define the right circle to be B, then A union B is all the elements that are in A, all the elements in B, and all the elements that are in both of them. So A union B basically covers every possibility. But if we were to look at A intersect B, what we have is only the elements that are both in A and B. And so A intersect B is just this small portion right there. Now let's look at this. So if this circle is our set A, and this big box around it is our universal set U, what is A complement? Okay. A is just the circle. A complement means everything in U that's not in A. So what is that? That's this region. Everything that's not A. That's what A complement is. Next, we'll learn the distributive property. So if we have A times some quantity B plus C, this is like saying A times B plus A times C. So we have A times B plus A times C. Now, if we have that the product A times B is equal to 0, this implies that either A equals 0 or B equals 0. Because anything, if you're multiplying two numbers and you get 0, then one of them is 0. Or in fact, maybe both A and B are equal to 0. But at least one of them will be 0, because 0 times anything is 0. Now if we have inequalities, these are the signs like these, meaning greater than or less than. This first sign means greater than. The second sign means less than. So we might say something like 7 is greater than 2. Or we could say, if we wrote it the other way, 2 is less than 7. We can also do this with negative numbers. So any positive number is greater than a negative number, so we might say that 3 is greater than negative 4. But what about if we have two negative numbers? Well, negative 1 is greater than negative 5. And to think about this, we can look at the number line. So we have 0, negative 1, negative 2, so negative 1, negative 2, negative 3, negative 4, negative 5. Negative 1 and negative 5, which number is greater? Which number is further to the right that's negative 1. So that means negative 1 is greater than 5. Or excuse me, negative 5. How would we graph the inequality x is greater than 2? Well, we look at the number line. So we have 0, 1, 2, 3, 4, 5, 6, and so forth. And we look at 2, so we start with 2, and we graph any value greater than 2. So that's all these numbers out here. That's the graph of x is greater than 2. What about if we changed it so that x was greater than or equal to 2? In this first case, we had an open circle because we're not including the point 2. Because if you think about it, if we said 2 is greater than 2, that's not true. 2 is equal to 2. So we don't write that. That's why we don't include the point. But if we have this line right here, that means greater than or equal. So this line would look like 0, 1, 2, and so forth. We'd start at 2, we'd fill it in, and then we'd go outwards because we're actually equaling 2. Similarly, if we wanted to graph a negative, maybe say x is less than negative 1, we would graph, so we'd start maybe 0, and we go negative 1, and anything less than negative 1, less means we're going to the left. And so we say negative 1, since it's not less than or equal to, it's just less than, we have an open circle. Now if we have an absolute value, what does that mean? So the absolute value means we basically take the positive of something. So the absolute value of 5 is just 5. But if we took the absolute value of negative 4, that is positive 4. Absolute value means we're taking it to be the positive. And so if we had the absolute value of 0, that's just 0. So if we wanted to find the distance between 2 points, so if we have 2 points, just A and B, the distance between those 2 points is going to be B minus A, the absolute value. So what is this saying? This is saying B minus A, the difference between it, but if it's negative, we're going to take the positive. If we're measuring distance, distance is always positive. You can't say something like, cut me a piece of lumber that's negative 2 feet. You say, cut me a piece that's 2 feet long. So let's do an example. So say we have a point that's negative 4. Oops, let me change the thing. So we have negative 4, and we have another point that's 2. So what's the distance? Well, the distance is going to be the absolute value of 2 minus negative 4. Okay, and so 2 minus negative 4 is going to be 2 plus 4, which is 6. So our distance is 6. Well, another way to think about that distance is looking at the number line. So we have negative 4, negative 3, negative 2, negative 1, 0, 1, 2. How far is this? Well, we start from negative 4, so we have 1, 2, 3, 4, 5, and 6. So yes, that is a distance of 6. So let's do another example. What if we're trying to find the distance between 2 points? Say we find the distance between 2 points, negative 3 and negative 7. So the distance is going to be the absolute value of negative 7 minus negative 3. Negative 7 minus negative 3, well, the minus a negative, that means this is the same as the absolute value of negative 7 plus 3. And negative 7 plus 3, this is equal to the absolute value of negative 4. And the absolute value of negative 4 is just positive 4. And that's our distance. You might see problems that would ask you to find the value of an expression using the given values. So the expression you might see might be something like x plus 14y. And they might also give you that x is equal to negative 4 and that y is equal to 2. So what do we do here? Well, in this case, these problems are just simple plug and chug. So if you're asked to find the value, you just plug it in. X is negative 4, so this is going to equal negative 4 plus 14 times 2. So we have negative 4 plus 14 times 2 is 28. So this is negative 4 plus 28. Negative 4 plus 28 is 24. You might also see more complicated expressions. So you might be asked to find the exact value of something like 11x minus 10y all divided by x plus 15. Okay, and you'll be given that x is equal to 7 and that y is equal to 4. So what is this? Well, this is going to be 11 times x, or 11 times 7, minus 10 times y, which is 10 times 4, divided by x plus 15. So divided by 7 plus 15. I'm going to move this up so we have more space. So what is 11 times 7? That's 77. So this is going to be 77 minus 10 times 40, or 10 times 4 is 40, divided by 7 plus 15, which is 22. And so we get 77 minus 40 is 37, divided by 22. The final example that we'll do will be if you have the expression the absolute value of the quantity 6x minus 7y. And you're given that x is 7 and y is also 7. And in this case, I'll also move it up. So, what is the expression? We plug in 7 for x and 7 for y, so this is 6 times 7 minus 7 times 7, all in the absolute value. 6 times 7 is 42. 7 times 7 is 49. So what is 42 minus 49? Well, that's negative 7, but this is all in the absolute value. Since negative 7 is less than 0, the absolute value makes it positive. Positive 7, and that's our answer. The domain of a function is basically all the possible x values. Okay, so put that in writing. So what do I mean by that? What are possible x values? Well, when can we not have an x value? Say for example, if we had 6 divided by x minus 3. What can we not happen? So when we're dividing, what can we not divide by? We can't divide by 0. So this implies that x minus 3 cannot equal 0. So if we add 3 to both sides, that means that x cannot equal 3. And that's our domain. You can write it as the domain is equal to the set of all x such that x is not equal to 3. That's one way of writing it. Another way of writing it could just mean that you can write as domain is all real numbers except 3. And another way would be to write it in terms of the interval. So we'd go from negative infinity all the way to 3, and we use a parenthesis to mean that we're not including 3, union 3 to infinity. If we included 3, instead of writing a parenthesis, we would use a bracket. So these are 3 different ways of writing our domain. You might see something slightly more complicated. What about if we had 6x minus 7 divided by x squared minus 9? Well, we can't divide by 0, so we're going to say x squared minus 9 cannot equal 0. So if we add 9 to both sides, we get x squared cannot equal 9. And now what happens if we solve for x? That means x cannot equal plus or minus 3, because we took the square root of both sides. And so our answer, our domain, is the set of x such that x is not equal to plus or minus 3. Now, another type of thing to look out for is having, when you have a square root. What is inside this square root, x minus 2, that can never be negative. You can never take the negative of a square root. Or excuse me, the square root of a negative. So that means that x minus 2 has to be greater than or equal to 0. So solving for x, we add 2 to both sides, and therefore we get x has to be greater than or equal to 2. That's your domain. You could write that as the set, the domain is equal to the set of x such that x is greater than or equal to 2. If you wrote it in interval notation, that would go from 2 to infinity. We always use a parenthesis when we have infinity, and 2 we use the bracket because it includes the point 2. Now if we were to multiply something like 3 times 3, that's equal to 3 squared. If we were to have it multiplied more times, 3 times 3 times 3, that's 3 cubed. So basically, if we have any number, a times a times a, and so forth, and we multiply them n times, that's going to equal a to the n. We multiplied 3 twice. 3 times 3, it was to the power of 2. 3 times 3 times 3 to the power of 3. If we have something a to the power 0, any number to the power 0 is equal to 1. Anything to the 0 power is always going to equal 1. Also, if we have some number a to the negative power n, The negative means we could write it as 1 over a to the n. So let me move this up a little bit, and we'll do an example. Say we have 3 to the negative 5. This is the same as saying 1 divided by 3 to the 5th. So if we had something like 3 to the negative 5 multiplied by 3 cubed, this becomes 1 over 3 to the 5th times 3 cubed. Or rather, 3 to the 3 over 3 to the 5. Since these both have 3 as the base, we can actually write this as 3 to the numerator, 3 to the power 3 minus 5, which is 3 to the minus 2. And 3 to the minus 2 could also be rewritten as 1 over 3 squared. 3 squared is 9, so this is 1 over 9. Now, where did we get this last thing from? Well, we have another property, and that property says that if we have a to some power n times a to some power n, that is equal to a to the m plus n. If we have a to the power m raised to the n, this is actually a to the m times n. If we have a times b to the power n, this is going to be a to the n, b to the n. If we have a to the power m over a to the power n, that's going to be a to the m minus n. And lastly, if we have a over b raised to the power n, this is going to be a to the n divided by b to the n. So let's work some examples. If we have x to the power 2 times x to the power 3, that's going to be x to the power 2 plus 3. 2 plus 3 is 5, so this is x to the 5th power. If we have, say, 5 to the 2 power raised to the 3rd, this is going to be 5 raised to the power 2 times 3, or 5 to the 6th. If we have another thing, like 4 times 3 raised to the 2 power, this is the same as saying 4 to the 2 power times 3 to the 2 power, which is 4 squared is 16, 3 squared is 9, and 16 times 9 is 144. So if we had another problem that looked like 6 to the 4 power divided by 6 squared, well, that's going to be 6 to the power 4 minus 2, which is 6 squared, which is 36. And so just as a note, we're going through an order from the last page. This is the first law that we did. This is the second. This is the third. This is the fourth. And now the last example would be if we had something like 4 over 5 raised to the power 2, this is the same as 4 to the power 2 divided by 5 to the power 2, which is 16 over 25. In section 8.4, we're going to discuss factoring polynomials. So if we have something like 2x plus 4, this can be factored because 2x and 4 both have 2 in common. So we can pull out 2 and get x plus 2, because 2 times x gives us our 2x, and 2 times 2 give us 4. This can work for anything else. So say for example, we have something like 2x cubed plus 5x squared. What do these have in common? Well, they don't have 2 or 5 in common, but they both have x. In fact, they both have x squared. So we can rewrite this as x squared, since they have x squared in common. If we take out x squared from this first term, what's left? It's just 2x. Plus, if we take out x squared from the second term right here, what's left? Well, what's left is just 5. And you can always double check your work. X squared times 2x give us 2 times x cubed. We're good so far. And we'll double check x squared times 5, which is 5x. We'll now take a look at some special cases. First off, we're going to look at something called the difference of two squares. And that is if we have something of the form a squared minus b squared, that will equal the quantity a minus b times a plus b. And we can check this. We can go ahead and FOIL these two. We have a times a plus a times b, then negative b times a, and negative b times b. So let's go ahead and write that out. So this is a times a is a squared, plus a times b is just ab, and then we have negative b times a, or minus ab, and then we have minus b squared. Well, our ab and negative ab cancel, and so we're just left with a squared minus b squared. So yeah, it checks out. So this is the formula for difference of squares. Anytime you see anything of the form a squared minus b squared, this is what we can do. So let's do an example. What about if we saw something like this? X squared minus 49. Well, x is a squared, but 49 is not squared, at least not in its current form. So we can rewrite it. 49 is what number squared? 7 squared. So this is x squared minus 7 squared. And now, using this formula right here, that could be written as the quantity of our first number is x minus the second number, 7, times x plus 7. What about if we had another example? 36x squared minus 64. Well, what do we do here? First, notice that 64 is 8 squared. But what about this first term? Well, x squared is a number squared. It's the number x squared. And so is 36. That's the number 6 squared. So this could first be rewritten as the quantity 6x squared. The quantity 6x squared is 36 times x squared. Minus 64 could be rewritten as 8 squared. So now, applying the formula, we have 6x minus 8 times the quantity 6x plus 8. Let's do one more example. If we have 12x squared minus 48, what do we do here? Well, like we did in the previous slide, we looked at what they had in common. Well, none of them, this term doesn't have any x's, so we can't factor out an x. But look, we have a 12 right here. Can 12 go into 48? Yeah, we can. Okay, so how many times does 12 go into 48? That's 4 times. So this is equal to 12 times the quantity x squared minus 4. Alright, are we done? Well, we did one factor, but we can actually do more. Look at this. X squared is a square number, and 4 could be written as 2 squared. So this could be written as 12 times the quantity x squared minus 2 squared. And so therefore, if we wrote it using the difference of squares, we get 12 times x minus 2 times x plus 2. And there you have it. So we just combined the last two steps, the last two formulas, into one problem. The next formula we'll learn is called perfect squares. Now there are two forms that perfect squares come in. The first is if we have the quantity a plus b, that quantity squared. Well, what happens when we have that quantity squared? A common mistake that I see students make is they say this is equal to a squared plus b squared. But this is not the case. When we square something, that's really just saying this is a plus b times a plus b. And now if we went ahead and factored it, we multiplied a times a, so we get a squared. A times b, we get plus ab. B times a, we get another plus ab. And then b times b, we get b squared. So I'll use the pointer. So we did a times a to get a squared. A times b to get this term. B times a to get this term, which b times a is the same as ab. And then b times b is how we got b squared. Simplifying this, we end up with the formula for a plus b quantity squared is equal to a squared plus 2ab plus b squared. The other perfect square formula is if we have a minus b quantity squared. It's going to be very similar, except the difference comes here where we minus 2ab, but it'll still be a plus b squared. So the only difference between these two, instead of adding and subtracting, comes right here, where it's the 2ab. Otherwise, it's still positive a squared and positive b squared. So let's do some examples. But make sure that you write down these two formulas for reference for when we start the example. If we had something of the form x squared plus 4x plus 4, what is that? If I wrote it in the form of the perfect square formula, that would be x squared plus 2 times 2x plus 2 squared. Okay, so just double check this is the same. 2 squared is 4, and 2 times 2x is 4x. So now this looks like the form that we have, and that said a squared plus 2ab plus b squared. Okay, so this is a squared plus 2ab plus b squared. What is our a? Well, our a in this case is x. our b in this case is 2. And so we have 2, a, and b. And this simplified to what again? This simplified to, if you recall, this was a plus b quantity squared. And so this formula becomes a, in this case our a is x, so x plus 2 quantity squared. And that's the answer. Another example that we'll do is if we had 16x squared minus 72x plus 81. What does this simplify to? Well, just like in the previous step, we'll rewrite it in the form of the formula, as in a squared, and then we'll have a 2 times something, and then another term squared. So we first have 16x squared. 16 is 4 squared, and x squared is x squared. So this becomes 4 times x quantity squared. Now we have a minus, and we have 2. If we factored out 2 from 72x, what's left would be 36x. So, and we can double check that. So 4 squared is 16, x squared is x squared. 2 times 36x is 72x. We're good so far. And then finally, 81 could be written as 9 squared. So if we rewrote this in terms of the formula, this ends up being 4x. And now, because there's a minus right here, it's going to be the minus, the second form that I wrote on the previous slides. So this is minus 9 quantity squared. The final example we'll do in this video is x cubed plus 24x squared plus 144x. What can we do? Well, notice that all 3 terms have an x in it. So we'll first factor out an x. We're left with x squared plus 24x plus 144. And we verify this. X times x squared gives us x cubed. X times 24x gives us 24x squared. And x times 144 gives us 144x. Now we'll write this in the same form like we did in the previous slide. So this is going to be 2 times x squared plus 2 times something. Well, 24x, if we take 2 out, or we factor 2 out, that becomes 12x plus 144 could be rewritten as 12 squared. So now plugging this into the formula, we get x times x plus 12 quantity squared. And that's it. Another common type of factoring that you might see is called the sum of 2 cubes. And the sum of 2 cubes is exactly as it says. If we have something a cubed plus b cubed, so we have 2 numbers that are cubed and we sum them together, that can look like the form a plus b times the quantity a squared minus ab plus b squared. In addition to sum of cubes, we might have the difference of cubes. So instead of adding, we'll subtract. So this would be difference of 2 cubes. And that is if we have a cubed minus b cubed, that's equal to a minus b times the quantity a squared plus ab plus b squared. So notice the difference between these two. If one is plus and one is minus, the first term, if we have plus over here, this is plus. So it's going to be the same. If it's minus, it's minus. And then, when we have the a squared ab plus b squared, the next sign is going to be opposite. If it's plus, it becomes minus. If it's minus, it becomes plus. And then finally, it's positive. So you can think about it as if as the signs are going to be the same sign, both positives or both minuses, and then the opposite of what we have. So if we start with a plus, we have a minus. If we have a minus, then we have a plus. So same, opposite, and then the last one is always going to be a plus. So we had the sum of cubes and difference of cubes. This is somewhat similar to what we did in part 1 video. And in part 1, we learned what the difference of cubes is, a squared minus b squared. And if you recall, that is a minus b times a plus b. But what we didn't cover is we didn't cover a squared plus b squared. Well, in fact, if we have a squared plus b squared, it cannot be reduced. There's nothing that can be factored with a squared plus b squared. Only if it's a squared minus b squared, or if they're dealing with cubes. Now these formulas you will see every now and then, but it's not as important as the difference of cubes or the perfect squares, as we covered in the first video. These will come up every now and then, but it's not as important to remember as the other ones. Let's do an example. If we have x cubed minus 27, can we factor this? Well, the big hint here is we have x cubed. Can 27 be written as something cubed? So x cubed is just x cubed. Now 27 is actually 3 to the power 3. So x cubed minus 3 cubed. So we can use the formula. The formula for difference of cubes says that this factored becomes, remember, it's going to be this, since we have a minus, it's going to be the same, so it's x minus 3 times x squared, and now it's going to be the opposite of minus, which is a plus, and then we multiply together 3 and x, so plus 3x plus, and it's always going to be plus at the end, our last number, in this case, which is 3 squared. And there you have it. If you wanted to simplify 3 squared, you could write that as 9. But let's do another example. X cubed plus 8. Well, can we write this as the sum of 2 cubes? Well, we have x cubed, and 8 could be written as what cubed? 8 is 2 cubed. And so, again, using the formula, this would be x plus 2, we're using the same sign, times the quantity x squared, opposite sign, so minus 2 times x plus 2 squared. And this is your answer. In addition to the special types of factoring, the more general polynomials that you'll see will be something of the form x squared plus bx plus c. And you'll want to be able to factor this into some sort of form of x plus some number a times the quantity x plus some number b. We would like it to look like that. So let's try an example and we'll work through the process. We have x squared minus x minus 20, and we want it to look something like x plus a times x plus b. So how do we figure out what is A and what is B? Well, if we were to FOIL the right side and we did x times x and x times A, x times B, and A times B, we get x squared plus A times x plus B times x plus A times B. Okay, so how do we get this? We multiplied x by x, we multiplied A by x, we multiply x by b, and then a by b. This can be simplified a little bit. We'll group the two terms in the middle because they both have an x. So this could be plus, if I factored out x from those two terms, this is plus a plus b all times x plus ab. And now we can compare this with that. So the x squareds match up, but now what we need to do is figure out two numbers, a and b, such that if a plus b should equal -1, so we want two numbers where a plus b is -1, and we also want a times b to be -20. So we need a times b to equal -20. Well, how do we even begin solving this? We'll first list the integers whose product is -20. So what times what would give us -20? 20 and -1 give us -20. What else would give us -20? How about -20 and +1? That would give us -20. Anything else? Yeah, well, -20 can be got by 2 and -10, or -2 and 10. Anything else? What times what would give -20? Well, 4 and -5 would give us -20, or the opposite, -4 and +5. So these are all the possibilities of integers that give us -20. 20 times -1 is -20. -20 times 1 is -20. 2 times -10 is -20. -2 times 10 is -20. 4 times -5 and -4 times 5 all give us -20. Alright, now that we have this written out, what we're going to do is we're just going to take the sum. And we add the two numbers that are on this box right above. So what's 20 minus 1? Or 20 plus -1? That would be 19. What's -20 plus 1? That would be -19. What's 2 plus -10? That's -8. -2 plus 10 is +8. 4 plus -5, that's -1. And then -4 plus 5 is 1. So this first row, these are all possible numbers such that their product would be AB. The product is the product is -20. The second row right here, these are all the numbers that A plus B, or whatever A plus B would equal. Remember, we want A plus B to be -1. So which one of this row would give us -1? Right here. So we find out that our A and B have to be 4 and -5. Since we're adding, it doesn't matter which order, so this is just x minus 4 times x plus 5. and therefore we have just factored out our original x squared minus x minus 20 to be this. Let's work out another example. Say we have x squared plus 2x minus 24. What does that equal? How can we factor this into x plus or minus something, and then x plus or minus something else? Well, we look over here at this 24. What are the things whose product would give us, and this is a minus, whose product is negative 24? Well, we'll start with 1 and negative 24. We also have negative 1 and positive 24. What else can we have? 2 and 12 would give us positive 24, so let's make 2 and negative 12, and then negative 2 and positive 12. That also gives us 24. And do we have anything else? Well, how about 6 and 4? So maybe negative 4, positive 6, and then positive 4, negative 6. So these are possibilities whose product is 24. Now we want to look at the sum. And what number do we want the sum to come out to? If we call the sum, we want the sum to equal 2. So let's go ahead and look at this. This first one, 1 and negative 24 give us negative 23. Negative 1 and 24 gives us 23. 2 and negative 12 give negative 10. Negative 2 and 12 give us positive 10. Negative 4 and 6 give us positive 2. And 4 negative 6 give us negative 2. Since we're looking right here for 2, we find that it happened to be this term. So our two numbers are going to be negative 4 and positive 6. Let's take a look at another example. Say we have 7 times x squared minus 7 times x minus 42. What can we do? Well, notice we wanted to have just a single 1 in front of the x, but we have a 7. But this has a 7, this has a 7, and 42 is 7 times 6. So we can factor out 7. This is going to be 7 times x squared minus x minus 6. Using the method we did in the last two slides, can we factor this anymore? So we're going to go ahead and make the table, or if you feel comfortable with any other method, by all means use that. But we're going to look at numbers whose product is negative 6. So what times what is negative 6? Well, that would be 6 and negative 1. Negative 6 and positive 1. What else makes 6? Well, 2 and negative 3, and then negative 2 and 3. So those are all the integers whose product gives us negative 6. Now we go ahead and take the sum. So 6 plus negative 1 is 5. Negative 6 plus 1 is negative 5. 2 plus negative 3 is negative 1. And negative 2 plus 3 is positive 1. What number were we trying to find? From here, we were trying to find negative 1, so we know it's that. So therefore, our answer is going to be 7 times x plus 2 times x minus 3. And that's it. So what we did here is we combined something that we learned at the beginning of this section, where we found that 7 was a factor of all the terms. We factored out the 7, right here, and what was left after we factored out 7 was still a polynomial, but then we used the method to figure out that that polynomial could be factored further. The next method that we'll learn is grouping. And this usually happens when you have about 4 terms. So if you see something, x squared plus 8x plus 9x plus 72, oftentimes what might happen is you can group them together. You might group the first two and the second two. So let's do that. If we group the first two together, we have x squared plus 8x, and then we grouped 9x plus 72. How does this work? What does this first group have in common? We can factor out an x. So we factor out an x, and what's left is x plus 8. But what about the second group? The second group has what in common? They both have 9. Okay, we can factor out 9 from x, and 9 goes into 72 how many times? 8 times. So this is going to be x plus 8. Well, what do you notice? We have an x plus 8 and an x plus 8. So if you ever see that, that means we can rewrite this. In fact, these are all equal signs. Each of these terms are all equal. Since they both have x plus 8, what we could do is think about letting a, some capital A equal x plus 8. So this is x times a plus 9 times a. And now we could factor out an a. So this is going to be a times x plus 9. But what did we say a was? A was x plus 8. So this ends up being x plus 8 times x plus 9. And that's how we factor this when we have something with 4 terms. In this case, we group the first two together and the second two. We could have actually grouped another grouping. We could have grouped the first and third and the second and fourth. So let's do an example with that. So if we have x squared plus 8x plus 9x plus 72, if we rearrange this and we grouped the first and third term together and then the second and fourth term, so we could write this as x squared plus 9x plus 8x plus 72. Now from the first term, what can we factor out? The first term, they both have an x in common, so we get x times x plus 9. The second term, what do they have in common? Well, they both have 8 in common, and we're left with x plus 8 goes into 72 9 times. And so now, if you notice, both of these terms have an x plus 9. And so if you want to use the same method where I let capital A equal x plus 9, you can. Or if you can just factor it from here, you can notice that this would be an x plus 8 times x plus 9. Okay, and I did that because they both have this in common, so I'll pull out the x plus 9, and the first term, x plus 9, is multiplied by x, which was here, and then x plus 9 was also multiplied by 8, which from there. So we got the same answer, but by grouping it 2 different ways. But this is grouping method. Usually it'll happen when you have 4 different terms. Now we already covered what happens if we looked at something of the form x squared plus bx plus c, and we factored it into something that looked like x plus some a times x plus some b. But what happens if this were to change? Instead of it being a 1 in front of the x squared, it's just x squared by itself, What if it were some number like an a in front? So if we had a times x squared plus b times x plus c. Well, if we had that, we could write it in the form of capital A times x squared plus some ax plus some bx plus the capital C. When we have it after this form, we can then factor by grouping. So how can we get it in this form? How can we get it like this form on the right? Well, the method is going to be very similar to what we did the previous time. So let's do an example. Say we have 15x squared plus 16x plus 4. What do we do? Well, we're going to make the same type of table, and we'll have this table, but what goes here, instead of two numbers whose product is 4, we're going to say whose product is 15 times 4. Okay, so we want the product to be 15 times 4. And what's 15 times 4? That's 60. So what numbers whose product would give us 60? Well, we'll start simple. 60 and 1, that would give us 60. What else? Negative 60 and negative 1. So negative times negative is a positive. So negative 60 and negative 1 is another example. Alright, 30 and 2. That works. Negative 30, negative 2 also work. And let's see, anything else? Yeah, 15 and 4. Negative 15, negative 4. 5 and 12. And then again, negative 12 and negative 5. So, and then we move to 6, so 6 and 10, and negative 10 and negative 6, and that's it. Alright, now what we want to do is look for the numbers whose sum would give us 16. So let's go ahead and add all these up. 60 plus 1, so we're taking the sum. 60 plus 1 is 61. Negative 60 plus negative 1 is negative 61, 30 plus 2, 32, negative 30 plus negative 2, negative 32, and I'll just fill these in so we get 19, negative 19, 17, negative 17, 16, and negative 16. Well, we were looking for 16, so that happens to be this one right here. So our numbers are going to be 10 and 6. So we can rewrite this as equaling 15 times x squared plus 10x plus 6x plus 4. Now, what do we have here? We have a group of 4 terms. And we'll group. We can group the first 2 terms together, and then the next 2 terms together as well. The first 2 terms, what can we factor out? What do they have in common? Well, they all have 5 in common, and they also have x. So we can factor out 5x. And what's left is 5x out of 15x squared, we're left with 3x. 5x out of 10x is 2. And then we look at the next term. What do these terms have in common? This case is just 2, so we can factor 2 out, and we're left with 3x plus 2. And as you may notice, we have 3x plus 2, and 3x plus 2. And so again, if you want to use the method where we let 3x plus 2 equal a, you would see this is going to be 5a plus 2a, and how do we combine? Or if you can just skip right ahead, this simplifies to, so if they both have 3x plus 2, and then we look at what's left, we had the 5x, and it's multiplied by 2, so 5x plus 2. Plus 2. This is the newly factored term. So let's take a look at another example. We have 6x squared plus 13x plus 6. So how do we factor this? Well, we draw the table, and then we're going to look at numbers whose product is going to be 6 times 6, which is 36. So what times what gives us 36? Well, 36 and 1. Negative 36 and negative 1. Remember, we're always going to look at both the positive and the opposite signs. Okay. What else? 2 and 18. And negative 2 and negative 18. 3 and 12. Negative 3 and negative 12. 4 and 9. Negative 4, negative 9. 6 and 6. And lastly, negative 6 and negative 6. Alright, so now we take our sum. 36 and 1 give us 37. The next one we have negative 37. 18 and 2 give us 20. We get negative 20, 15, negative 15, 13, negative 13, 12, and negative 12. So, which one gives us what we want? We wanted positive 13, and that happens to be this right here. So, we know that we can rewrite this as 6x squared plus 9x plus 4x plus 6. And now we can group, and we'll just go ahead and group the first two and the last two. What can we factor out from the first two? They both have 3 and x. 3 goes into 6 2 times, 3 goes into 9 3 times. X into x squared and x, so we get 3x, and we're left with 2x plus 3 plus, and what do we have in this second term? They both have 2 in common, so we'll take plus 2, and we're left with x plus 3. Excuse me, we have 2x plus 3, because it was 4 over here, so we factored out 2 from the 4. So, what do? They both have 2x plus 3, and I'll go ahead and do the other method for those that aren't comfortable. If we let 2x plus 3, we let capital A be 2x plus 3, this is going to be 3x times a plus 2a. Everything has an a in common, so we factor out a, and we're left with 3x plus 2. But since a was from up here, 2x plus 3, this is going to equal 2x plus 3 times 3x plus 2. And there you go. That's the answer. So what we've done so far is gone through several techniques for factoring. And the order that you should factor, because these are the easiest going to hardest, is 1, look for common multiples. Or rather, common factors. Okay, and common factors, that deals with things like if you have 4x plus 8, we could factor out a 4. So that would be 4 times x plus 2. The next thing, if we can't factor out a 4, or you can't factor out some sort of value, the next thing is you look for the special cases. So you look for the difference of cubes, the sum of cubes, and the difference of squares. Mainly, so you look for the special cases, and that would be something like a squared minus b squared, a cubed minus b cubed, and a cubed plus b cubed. If that doesn't yield anything, check if you have a perfect square. Check for a perfect square. Meaning if you have something of the form a plus b quantity squared, or maybe it's a minus b quantity squared. If that doesn't work, then the next thing you do would be try factoring if you have something of the form x squared plus bx plus c, or if it's ax squared plus bx plus c. And then if those don't work, you can try grouping. And if grouping doesn't work, the last method that we can use is completing the square. And that's what we'll talk about for the remainder of this video. So if we had something of the form x plus a quantity squared, now that's a perfect square, and that ends up giving us x squared plus 2 times x times a plus a squared. Now it would be nice if things were of this form so that we could get a perfect square, but sometimes you're not given all of these things. You might just be given part of this, and you would need to figure out what else do we need to add to make it a perfect square. We could be given instead something that might look of the form x squared plus bx. If we could add something to it, we could make it look like a perfect square. So what do we need to add to make this a perfect square? Well, the first thing we do is we take this b right here and we multiply. So step one, we divide b over 2. Step 2, we then take that b over 2 and we square that number. This number that we just squared will add to the end over here. So we get x squared plus bx plus the quantity b over 2 squared. And that is a perfect square, which is x plus b over 2 quantity squared. So what did we do? We had our original x squared plus bx. We added this term that we got from step 2, so b over 2 squared, and that ended up making it a perfect square. X plus b over 2, and b over 2 was the value we got from step 1. So let's work an example. If we have x squared plus 18x, what do we need to add to this to make this a perfect square? Well, step 1, we take 18 and divide it by 2. The number that's in front of the x and divide it by 2, so we get 9. Step 2, what does step 2 do? It takes 9 and squares it. 9 squared is 81. So now we go back to our original. We have x squared plus 18x, and we add plus 81. And that is the perfect square, x plus 9 quantity squared, where the 9 came from step 1. So let's do another example. If we have y squared minus 12y, well, again, we're going to look at this negative 12, and so for step 1, we take negative 12 divided by 2, and we get negative 6. Step 2, we take negative 6 and square it, which happens to be 36. So now we go ahead and plug it back in. We have 12 squared minus 12y plus our number from part 2, or step 2, which is 36 plus 36. And that is equal to the quantity y plus the number from step 1, which is negative 6, so y minus 6 quantity squared. And there you have it. In section 8.8, we're going to be solving equations. If we had something like 4x is equal to negative 20, how do you solve for x? Well, we just divide both sides by 4, and so we get x is negative 20 over 4, or negative 5. Now you might see something more complicated like this. Negative 4x over 5 is equal to 1 over 8. Well, how would you figure out this? If we have something like this and there's just a fraction on the left and then a fraction on the right, what we do is what's called cross multiply. We multiply the diagonal and the diagonal. And so we get negative 4x times 8 is equal to 1 times 5. Well, negative 4 times 8 is negative 32 times x, and 1 times 5 is 5. To solve for x, we divide both sides by negative 32, and we're left with x is equal to negative 5 over 32. What about if we had something that looks like this? 3 divided by 2x minus 4 equals 2 divided by x plus 5. Well, similar to the other problem, since we had two fractions, we can cross multiply. Multiply this way, we'll multiply this way. So we get 3 times x plus 5 is equal to 2 times 2x minus 4. And now we'll multiply through the parentheses, so we get 3x plus, and then 3 times 5 is 15, equals 4x minus, and 4 times 2 is 8. So now we'll subtract 3x, and so we have 15 is equal to x minus 8. If I want to get x by itself, we add 8 to both sides, and we're left with x is equal to 23. Now what about if we were to ask to solve for x given that x squared minus 2x equals 0? Well, using factoring that we learned in the previous section, we know that we can factor out an x from this, and we get x times the quantity x minus 2 equals 0. Now if we have something times something is equal to 0, we know for something to be equal to 0, either one of these terms would be 0. So either x equals 0, or the other term, x minus 2 equals 0. Well, if x equals 0, we're done. But for x minus 2, we just add 2 to both sides. And so we get x is equal to 2. So our two possible answers are going to be x equals 0 or x equals 2. If we have another equation, x cubed plus x squared minus 12x equals 0, how do we solve that? Well, in this case, they all have an x, so we can first factor out. So we get x times the quantity, x squared plus x minus 12 equals 0. But what do we do about this? If you recall from factoring, that could be factored. So how do we factor this? We first look at the negative 12 and we figure out what numbers multiplied by each other would give us negative 12. So we write down the product of two numbers would be negative 12. So what times what would give us negative 12? Well, that would be 12 and negative 1, or negative 12 and positive 1. What else give us 12? Well, 2 and 6, and one of them, say maybe negative 2 and 6, and then negative 6, positive 2. What else? And negative 3 and 4, and then 3 and negative 4. Those are all the possibilities that would give us a product that's 12. Let's go ahead and take their sum. So we get 11, negative 11, 4, negative 4, 1, and negative 1. And now we look back up here, and we see that we wanted their sum to be positive 1 because it's x squared plus 1 times x. So we're going to use this. So this ends up factoring further, so we have x times x plus 4 times x minus 3 equals 0, where the 4 and negative 3 come from right here. So finally, now that we have something times something else equals 0, we know that either the first term, x equals 0, or x plus 4 equals 0, or x minus 3 equals 0. Well, for this first one, x equals 0, we're already done. For the next one, to solve for x, we subtract 4 from both sides, and then we get x is equal to negative 4. Okay, so we have one answer, we have another answer, and then this last one, to solve for x, we add 3, and so x equals 3. And so putting it all together, we get x will be equal to 0, negative 4, or 3. And notice, how many answers do we have? We have 1, 2, 3 answers. And what's the highest power that we have here? We have cubed. And so the number of different answers we'll have will be at most 3. If we had something that had x to the power of 5, the number of different answers we'd have would be at most 5. Sometimes you might have less, but you can never have more. Now if you see something that looks like this, the square root of the quantity x plus 4 equals 2, how would you solve this? If you're trying to solve for x, well, when we solve for x, we want to get x by itself. So in this case, if we have a square root, how do we get rid of the square root? Well, we square both sides. Taking the square root is the opposite, or taking the square, excuse me, is the opposite of the square root. So we would square both sides. The square of a square root gives us just the number that's inside right here. So we're left with x plus 4 equals 2 squared is 4. So if we subtract 4 from both sides, we're left with x equals 0. Now you might see something else that would deal with, instead of a square root, a cube root. So if we had something that looked like this, the cube root of the quantity 2x plus 5 equals negative 2. Well, to undo the cube root, what we want to do is cube both sides. Okay, so we raise this to the power 3, and we'll raise this to the power 3. So the cube root cubed just leaves what's on the inside. So we're left in the middle, or on the left, excuse me, with 2x plus 5. Now on the right, we have negative 2 to the power 3. What is negative 2 times negative 2 times negative 2? And I'm going to write this over here just so you can see. So that's negative 2 times negative 2 times negative 2. If we look at it, 2 times 2 times 2, and I have to finish the parenthesis, 2 times 2 times 2 is 8. But is it positive 8 or negative? Well, negative times negative is positive. So if these two would give us a positive, but what would a positive times the negative be? A negative. So if we have an odd number of negatives, it ends up being negative. So this is a negative 8. And how do we solve for x? Well, we need to move 5 on the other side. And so we get 2x is negative 8 minus 5 is negative 13. And then to solve for x, we divide both sides by 2. And so our answer is x is negative 13 over 2. In section F.1, we're going to discuss the distance and midpoint formulas. We'll begin by figuring out the distance between 2 points. So say we have an axis, x and y, and we plot 2 points, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and we have the first point at 2, 1, so this is going to be 2, 1, and our second point is going to be over here at 5, 5. What is the distance between these 2 points? One way to think about the distance is, let's just look down right here. So if we had something like this, we have a right triangle, and you know the distance of one side, call it A. We'll do this other side, B. Can you find C? Well, we know that that distance, C, can be related with A and B as in A squared plus B squared equals C squared. This is the Pythagorean theory. Now this can be applied to our 2 points over here by figuring out what is the change in the x-axis. So how far over in the x direction does it go, and how far up in the y direction does it go? Well, if we count, so we start off when x is 2, and we end up over here when x is 5. So this is 2, 3, 4, 5. We go across 3. So our change in our x is 3. And then if we look how far vertically we change, we start at 1 and we end at 5. So 1, 2, 3, 4, 5. We go up by a distance of 4. So drawing a triangle out over here, we have a distance of 3 across and 4 up. So if we want to figure out what this distance is, our C, we relate it as in 3 squared plus 4 squared is equal to C squared. Simplifying, 3 squared becomes 9, 4 squared is 16, equals C squared. 9 plus 16 is 25. 25 equals C squared. Solving for C, we take the square root of both sides. The square root of C squared is just C. And then the square root of 25 is 5. So 5 is our answer. Our length right here is 5. And this is how you can find the distance between 2 points. You figure out how far across in the x direction you go, how far across in the y direction, and then you use the Pythagorean theory. A squared plus b squared equals c squared. Now the book uses a fancy formula for this. So if we had 2 points right here, and our first coordinate was x1, y1, and our second coordinate was x2, y2, how do we find the distance between these 2 points? Well, if we look across and up, how far does the x direction change? Well, x goes from x1 to x2, so to find the change in x, we find, so change in x is given by x2 minus x1. The change in y, how far we go up, is going to be y2 minus y1. So if the distance between these 2 points, or we're going to say the distance is d, we can relate this length, which is x2 minus x1, and this length is y2 minus y1. The relation between all of this becomes, and let me move out a little bit, becomes d squared equals our change in our x, so x2 minus x1 quantity squared, plus y2 minus y1 quantity squared. Or you can think about it, this is our a squared plus b squared equals our c squared. And so solving for d, our distance, we take the square root. So our distance is the square root of x2 minus x1 squared plus y2 minus y1 squared. This is the formula that the book has. Now, you're not expected to know this formula, but this is where it comes from. It said what you should know is that the distance between 2 points is taken by looking at a squared plus b squared equals c squared. Now, you might get some problems to say, verify, given 3 points, that you have a triangle. How do you know that that triangle is a right triangle? Well, if you're given 3 points, let's move up over here. So if you're given 3 points and they form a triangle, what you want to do is figure out the distances between these 3 points, figure out those 3 distances, and you do that just by using the change in distance formula that I just explained. And once you have those 3 sides, is it possible to have a squared plus b squared equals c squared? Or, depending on what your sides are, maybe it's going to be b squared plus c squared equals a squared, where the longest side is the side that's on its own. If we have this relationship, then yes, you do have a right triangle. So we have the following 3 points: 5, 0, 7, negative 1, and 3, negative 4. Do these 3 points make up the vertices of a right triangle? Well, it looks like it might, but I'm not quite sure. How do we figure that out? Well, we need to first find the lengths of each side. So we'll look at these 2 points first of all. How far in the x direction do we change? From 5, 0 to 7, negative 1. In the x direction, we go over 2 points. Okay, so for that, our change in x is 2, and our change in y, we go from 0 to negative 1. Although this might not be drawn exactly to scale, but we change in the y1. So the distance squared is equal to 2 squared plus 1 squared. Or the distance squared is going to be 2 squared is 4 plus 1, which is 5. So our distance squared is 5. I'm going to call this D1. So we're going to say that this is going to be side 1, side 2, and side 3. Now let's look at the distance for side 2. What would D2 be between this point and this point? Well, how far do we go in the x direction? We go from 3 to 5, so our change in our x is going to be 2. So This one, we also have a change of x is 2. And how far do we go in the y direction? We go from -4 all the way up to 0. So in the y direction, we have a change of 4. So our distance squared for side 2, so d2 squared, is 2 squared plus 4 squared. 2 squared is 4, and 4 squared is 16. 4 plus 16 is 20. And finally, we look at our last side, right here, side 3, and we go in the x direction from 3 all the way to 7. So our change in x is going to be 4. And then our change in y, we go from -4 up to -1. So that's a change of 3. So we change 3. So our distance squared for side 3 is equal to 4 squared plus 3 squared. 4 squared is 16. 3 squared is 9. 16 plus 9 is 25. And now let's zoom out a little bit. Give me a little bit more room. So we have our three sides, 5, 20, and 25. Well, we look here, if d1 squared plus d2 squared, does that equal d3 squared? This is what the Pythagorean theory says, a squared plus b squared equals c squared. I chose this way because d3 is 25. 25 is our largest one, so that's going to be the one on its own. Now let's make the substitution. So d1 is 5, or d1 squared is 5, plus d2 squared is 20. Now does this equal d3 squared? D3 squared is 25. Well, 5 plus 20 is 25. So yeah, so this is a right triangle. The last topic I want to discuss in this section is related to the midpoint of a line, or the midpoint between 2 points. Well, what is the midpoint? Let's start off with something just on a straight line. So we have maybe the points 1 and 3. What's the midpoint of this? What's the midpoint between 1 and 3? Well, the midpoint halfway between 1 and 3 is right there. So the midpoint is 2. How do we know that? Well, 2 is the average of 1 and 3. We found the average, 1 plus 3 over 2. That's how we take the average. We add, and then we divide by 2. So that is going to be 2. What about, let's do another one. Say we have two other points, say 2 and 6. 2. What's the midpoint between 2 and 6? Well, just by looking at this, we can see that this would be the midpoint because that's 2 units away and 2 units away from either end. But we could also find, so this midpoint, the value is 4. We could find that by taking the average. 2 plus 6 over 2 is going to be 8 over 2 or 4. So this is how to find the midpoint if it's just on a straight horizontal line. But what about when it's different? So now we have 2 points, one at 4, and the other point is going to be at 3, 6. What's the midpoint of this line? Well, just like we did with the other example, we want to find the average. But since this has 2 coordinates, the other ones only had 1. It had just, say, like an x value, and we found the average of that. We have an x and a y, so now we're going to take the average of the x and the average of the y. Okay, so the average of the x we would take our two x values, which are going to be 1 and 3. So the average of the x is going to be 1 plus 3 divided over 2. 1 plus 3 is 4. 4 over 2 is 2. So the average x value is going to be 2. And then the average y value, take a look at our y values, which are going to be 4 and 6. So we add 4 plus 6 over 2. 4 plus 6 is 10. Half of 10 is 5. So the average y value is 5. So if we look at this, at the point, so 2 across and 5 up will be right here. That's where the average is. And in fact, just by eyeballing it, it looks right about at the midpoint, halfway through. So the midpoint is at the point 2, 5. We found that by just taking the averages of the x and y values. Now the book has a formula for this. So if we have 2 points, and the first point is, we're going to call it x1, y1. The second point is going to be x2, y2. The average, or the midpoint, is going to equal the average of the x values and the average of the y. So x1 plus x2 divided by 2. And then the y coordinate, it will be y1 plus y2 divided by 2. So this is the formula that they have in the book, but all that basically means is the average. So the midpoint right here, our midpoint is just the average x1 plus x2 divided by 2, y1 plus y2 divided by 2. In section F.2, we'll deal with graphs of equations. So how would you graph the equation y equals x plus 2? Well, one way of doing this is by plotting points. When we plot points, we draw a table, and we have one column that has the x values right here. Then we have another column that has the y values right here. And what is the y? Well, our y really in this case is x plus 2. So instead of y, we can just write x plus 2. So let's start picking points. If x were negative 2, what is y? Y is going to be negative 2 plus 2. In this case, that's 0. If x is negative 1, y is going to be negative 1 plus 2. Negative 1 plus 2 is 1. If x were 0, then y is going to be 0 plus 2, which is 2. If x is 1, y is 1 plus 2, which is 3. And if x is 2, then y is going to be 2 plus 2, which is 4. So let's plot this. Our first point, x is negative 2, y is 0, so we look at negative 2 in the x direction and 0 in the y direction. The next point is negative 1, and y value is 1, so we're going to go negative 1 in the x direction and positive 1 in the y direction. So our point is right here. The third point is when x is 0 and y is 2, so we go 0 in the x direction and 2 in the y direction. Next point is when x is 1, y is 3, so 1 across in the x, and we go 3 up. So we have that point right here. And then finally, our last point that we picked is when x is 2, y is 4, so we go 2 across in the x, and go all the way up 4. So now we have enough points that we can see that this is in fact a line. What about if we had the equation y is equal to negative x squared plus 1? What does that graph look like? Well, let's go back and make a table. So we have a column for x, and then a column for the y, which is negative x squared plus 1. So now we'll pick some values for x and plug that in to figure out what y is. And so we like to pick negative values as well as positive values. So again, we'll pick negative 2. So what is y? Y is going to be negative of x squared, and x in this case is negative 2. So we get negative 2 squared plus 1. Well, inside here, the negative 2 squared, that's going to be 4. But the negative in front makes that a negative 4. Negative 4 plus 1 is negative 3. We'll pick the point negative 1. And what do we get? So we get negative of the quantity negative 1 squared plus 1. Well, negative 1 squared is positive 1. But the negative in front means it's a negative 1. Negative 1 plus 1 is 0. Pick the point 0. So we have negative of 0 squared plus 1. That's just 1. If we pick the point 1, we have negative of 1 squared plus 1. And we get negative 1 squared is negative 1 plus 1. That's 0. And then if we pick the point 2, we have negative 2 squared plus 1. 2 squared is 4. Negative of that is negative 4 plus 1, or negative 3. So if we're to plot that, we take our first point when x is negative 2, y is negative 3, and so that's the point down here. Next we look when x is negative 1, y is 0. When x is 0, y is 1. When x is 1, y is 0. And when x is 2, y is negative 3. So in this case, this is not a straight line. You can see the line sort of curves up and curves down like that. In fact, this is what we call a parabola. The next topic we'll discuss are intercepts. Intercepts is when a graph crosses the x or y axis. So if we have axis, x and y, and we had a graph that did something like this, it crosses the x-axis. This is the x-axis. When it crosses once over here, another time over here, another time there, there, and there. Those are all x-intercepts. That's when it crosses the x-axis. So these values, they are called x-intercepts because it intercepts the axis. Now, if it crosses the y-axis, which it does right here because it crosses the y-axis, this value is called the y-intercept. Now notice, if it crosses the x-axis, so if it's an x-intercept and it crosses the axis, what is the y value? Well, the y value, if it were 1, 2, 3 or something, would be up here, but it's not. The y value has to be 0 for it to cross the axis. Otherwise, if it might be a point up here or down here, but y is 0 when we're on the axis. So when it crosses the x-intercept, we have that the y value equals 0. Similarly, if it crosses the y-intercept, the x value is 0. If x were positive, it would be out here. If x were negative, it would be out here. But when x is 0, it's right here. So when we have a y-intercept, the x value equals 0. So if we had, for an example, a curve that looked something like that, where are the x-intercepts and where are the y-intercepts? Well, the x-intercept is going to be this point, that point, and that point. So we have 4 x-intercepts because it crosses the x-axis 4 times. The y-intercept will be right here where it crosses the y-axis. Now, how would you know what the intercept is based off of an equation? So if we had an equation y is equal to x minus 5, what is the intercept? Remember, if it's an x-intercept, the y value is 0. So x-intercept implies the y value is 0, and the y-intercept implies that the x value is equal to 0. So we'll use these two points in helping us determine the x and y-intercept. So first off, let's look for the x-intercept. If we're looking for the x-intercept, that means that y is equal to 0. So we're going to substitute 0 in for y. So back into this equation, we get 0 is equal to x minus 5. And now we solve for x. To solve for x, we'll add 5 to both sides. And we end up with x is equal to 5. So if x is 5, when y was 0, our value for the intercept is x is 5, comma, 0. Because we assumed that y was 0. Now, if we solve for the y-intercept, we assume from over here that x is 0. So we plug 0 in for x back into our equation up here. So solving for y, we get y is equal to 0 minus 5. Simplifying this, we get y is equal to negative 5. So we have when x is 0, y is negative 5. So our intercept is going to be 0, comma, negative 5. These are our two intercepts. The x-intercept is 5, 0, and the y-intercept is 0, negative 5. Let's do one more example. If we have x squared plus y minus 4 equals 0, what is the x and y intercepts? Well, for the x-intercept, that means that the y value is 0. So let's plug that in. We get x squared plus 0 minus 4 equals 0. Or x squared minus 4 equals 0. Or x squared equals 4. Solving for x, since we have a square, what we do is we take the square root of both sides. So the square root of square, they cancel each other. That's always going to be the case. So the square root of x squared is just going to be x. The square root of 4 is 2. 2 times 2 is 4. However, when we take the square root, we're going to always add plus or minus. So we have plus or minus the square root of 4, which is plus or minus 2. So we have positive 2 or negative 2. So we have 2 zeros in this case. And so our x-intercept is either going to be 2 comma 0 or negative 2 comma 0. these are our two x-intercepts. Well, what about the y-intercept? Well, if we're solving for the y-intercept, that means that the x value is equal to 0. So plugging in 0 for x, we get 0 squared plus y minus 4 equals 0. Excuse me, that's a minus. So we get y minus 4 equals 0, or y equals 4. Therefore, y is 4 when x was 0, so our y-intercept is 0, 4. Sometimes you might have a graph that looks like this. So notice about this graph that it's symmetric over the x-axis. We see something up here and it's reflected down here. Something over here is reflected down here. Anything above the x-axis is reflected below, and vice versa. Okay. So a graph like this is what we call symmetric with respect to the x-axis. Now, if something is symmetric to the x-axis, we see that for any x value, say an x value over here, if we look at the corresponding y value, if the y is down here, it's also going to be at that opposite value. So the way we write it is we say that if x comma y is on the graph, then the negative of that, x comma negative y, is also on the graph. So we have a point, say up here, whatever this y value is, the negative of that is down here. Or we have a point over here, if this y value is negative, a negative negative makes it a positive. We also have graphs that look somewhat like this. This is a graph that would be symmetric with respect to the y-axis. And so we look, we have a value over here, it's reflected over the y-axis. The value down here, reflected, and so forth. And so we would write that, and we'd say that if we had a point x comma y, the x value, so if this is on the graph, then the negative of the x value is also on the graph. So if we have, say this point, maybe x comma 0, negative x comma 0 is also on the graph. Or if this point is over here, the negative of that is a negative is a positive. So these are two cases that you might see with respect to symmetry. Symmetry with respect to the x-axis and symmetry to the y-axis. Another type of symmetry that you might see would be symmetry with respect to the origin. And what this kind of symmetry looks like is something like that. This is what we call symmetry with respect to the origin. How can you tell if something is symmetric with respect to the origin? One way to determine if something is symmetric with respect to the origin is first by taking a look at this first quadrant. We'll look at that quadrant. So we have the line that looks like that. What we'll first do is we'll take the symmetric version of this with respect to the x-axis. So we're going to reflect it over the x-axis, and if this is the x-axis, it would look something like that. So the first step is to reflect it. We get a graph like that. Now the second step is to take this reflection and make it symmetric about the y-axis. So if this is what it looks like, reflected over here, we get a graph like that. And so now what we see is this becomes our new graph. This part right here came from a reflection over the x to get this, and then followed by a reflection over the y. So if that's what happens, it is symmetric with respect to the origin. In this case, we found the reflection with respect to x and then y, but you could also find the reflection with respect to y and then x first. And if we have a point xy that's on the curve, if it is symmetric with respect to the origin, then we get the point negative x, negative y is also on the curve. So if we think about it, say we have a point right here, maybe this might be the point 1, 1. The point negative 1, negative 1 would also be on that curve. So to recap, if we're going to test for symmetry, we first look at if it's symmetric with respect to the x-axis, we will replace y with negative y and hope we get the same equation. If we're going to test for symmetry about the y-axis, we replace x with negative x. And finally, if we were to test for symmetry about the origin, we're going to replace both x with negative x and y with negative y. So let's do an example. Say we have the equation y is equal to 3x. To see if it's symmetric about the x-axis, we replace y with negative y. So if negative y equals 3x, well, this is a different equation. Negative y equals 3x is not the same as y equals 3x. So that implies that it's not symmetric with respect to the x-axis. Next, we test if it's symmetric to the y-axis. So instead of writing x, we'll write negative x. So y is equal to 3 times negative x, or negative 3x. Well, this is the opposite. We had negative 3x instead of positive 3x. So again, this is not the original equation, so we get it's not symmetric with respect to the y-axis. And finally, we'll test out the origin. we replace y with negative y, so we have negative y is equal to 3 times, and we replace x with negative x. So we get this is equal to negative 3x, or negative y equals negative 3x. Well, if we multiply both sides by negative 1, that implies that y equals 3x. Well, y equals 3x was exactly what we started with. So since we ended up with y equals 3x, and that was what we started with, then that means that it's symmetric with respect to the origin. Now, if we had tested this and it wasn't symmetric to the x-axis, wasn't symmetric to the y-axis, and wasn't symmetric to the origin, then it would be neither. In fact, origin is spelled with an extra I. Now, there are a couple of key graphs that you'll need to know in this class. The first one is y equals x cubed. That graph is of this shape, like this. So anytime you see an x cubed and a y equal to that, we're going to get this shape. It might be slightly shifted, but it'll be this general shape. The next graph that you'll see often is x equals y squared. That graph looks something of this form. The next graph is y equals the square root of x. And that graph looks similar to the previous one, except it's just going to be with a positive y value. The next graph that we're going to see quite often is the graph of y equals 1 over x. And that looks something of this form. In section F.3, we'll be discussing lines. The first thing that we'll talk about is slope. The slope of a line is basically how steep a line is. The slope of a line can be thought of, and we're going to call slope an m. It can be thought of as the rise over the run, basically how high it goes over how far it goes across. The rise can be given in terms of the change in our y value, so y2 minus y1, and the run is a change in the x values, x2 minus x1. Now, what if we have a line where y1 equals y2? What does that mean? If y1 equals y2, that means that the line is not moving up or down. It's staying the same. So if y1 equals y2, this implies that the line is horizontal. Because if y1 equals y2, if we plug it into this equation, y1 equals y2, that if they are equal, an equal value minus itself is going to be 0. So it's a horizontal line, and the slope, m, is 0. So it doesn't go up at all. If, however, we have that x1 equals x2, that means that we have the same x values, and so this line is actually going to be a straight vertical line. But if we were to plug it into this equation, where x1 is equal to x2, and we subtract, we actually get 0 on the denominator. And one of the things we can never do is divide by 0. So in fact, the slope our m, as we might call it, is undefined. So if we have an undefined slope, that means we have a vertical slope. So let's do an example. Say we have a line with the following 2 points. What is the slope of this line? Well, the slope of this line is how far up it goes over how far across it goes. So we look at these 2 points, and what is the rise? We rise up 1, 2, 3, and we go over 1. So the slope, m, is equal to the rise, which is 3, divided by the 1, which is 1. So 3 over 1 is 3. And we take our notation, we go from left to right, and if we go left to right, we're going to go up. If it were -3, the line would be looking like it's going down. Now let's do an example where we have 2 points, and we need to find the slope. And the 2 points that we're given are going to be 2, 2, and 9, -4. So how do we calculate the slope? Remember, the slope is m is equal to the change in our y, y2 minus y1, divided by the change in the x, x2 minus x1. Which points do we want to designate as 1 and 2? Well, it's up to you. But I'm going to designate this first points as our x1, y1, and then the second point as x2, y2. But it's up to you as long as you're consistent. So y2 is going to be -4 minus y1, which is 2. Okay, so we had y2 is -4, y1 is 2, divided by x2, which is 9, minus x1, which is 2. So we have -4 minus 2, which is -6, divided by 9 minus 2, which is 7. So our slope is -6 over 7. Now, if we had another example, and I were to ask you to graph the line that has the points, or the point 2, 3, and the slope m is equal to 1/2, how would you do that? Well, we draw out our axis, x, y, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and we look for the point 2, 3. So we go across 2 and up 3. So we mark that point right there. And then, after we get our first point, we look at the slope. The slope is 1/2, meaning we rise up 1 and we go over 2. So we're going to go up 1 over 2 to this point right here. And that's our line, and we can keep going. We can also go in the other direction. Instead of going up 1 and to the right 3, or excuse me, to the right 2, we can go down 1 and to the left 2. So if we go up +1 and right +2, we could also go down -1 left negative 2. It's the same thing. Now the equation for this line can be given if we use the general form of a line that looks like this. Y minus y1 is equal to m times the quantity x minus x1. This is what we call the point slope formula. This is one simple way of writing the equation of a line. So if we have just one point, x1 comma y1, and we have the slope m, we can write the equation of the formula. So the equation of this line can be written as y minus our 1 point y1 is 3 from right here, and our x1 would be 2. So y minus 3 is equal to, our slope is 1/2 times x minus x1, which was 2. Now you can leave this as your final answer, and this would be acceptable for me on a quiz or on a test, but sometimes my math lab does not like this. So if we want to simplify, what we'll have to do is multiply the right side of the equation by 1/2. So we get y minus 3 is 1/2 x minus 1/2 times negative 2. 1/2 times negative 2 is just negative 1. Now if we add this 3 to both sides, we get y, oops, let's change it back to the pen, y is equal to 1/2 x, negative 1 plus 3 is positive 2. And this is the equation for our line. What if I were to ask you to plot the graph with the point negative 2, negative 4, and with a slope that's undefined? So recall, what did we say when the slope is undefined? An undefined slope implies that we have a vertical line. And so we look for the point negative 2, negative 4, which is down here, but our line is just a straight vertical. Given a line like this, what is the equation of this line? Well, the equation of this particular line, if it's a vertical line, is going to be x is equal to whatever the x value is. In this case, the x value is negative 2. So this is the equation for this line. Typically, lines will be given in the form of y equals, except when it's a straight vertical line. If we're given a point of 5, negative 1, and we said that the slope m is equal to 0, what does that line look like? Well, in this case, we look at 5, 1, 2, 3, 4, 5, and negative 1. So we look right here, and our slope is 0, so we're not moving up at all, we're moving just straight across. So this is a horizontal line, because m equals 0 implies horizontal. And the equation for this is going to be y equals whatever the y value is. So y in this case is negative 1. So the equation for the horizontal line is y equals negative 1. In addition to the point slope formula, which was y minus y1 equals m times x minus x1, we can write the equation of a line in the form of y equals m times x plus b. So this first one is point slope formula. This second method is what we call the slope intercept line. And here our slope is m, but b is the intercept. B is the y intercept. A third formula that we have is a times x plus b times y equals c. And this is where a, b, and c are really any real numbers. This formula is what we call the general form. So you have the general form, slope intercept, and the point slope form. So let's take a look at an example. Say we're given 2 points, points 7, 5, and -4, 7. What is the equation of this line? We'll first find it with the slope intercept form. So what is the slope? So we'll let this first line, or this first point, be our x1, y1, and the second point be our x2, y2. So our slope, recall the formula, is m is equal to y2 minus y1 over x2 minus x1. So this is 7 minus 5 over -4 minus 7. This simplifies to 2 divided by -11, or just -2 over 11. So our slope is -2/11. Now, to find the intercept, we need to plug it back into an equation. We'll plug it into the point slope formula. And we can pick any point. We can either pick 7, 5 or -4, 11. We can pick any one we want. I'm going to pick the first one because there's only positive values. But you can pick the second one if you want. So that equation was y minus 5 is equal to our slope, which is -2 over 11, times x minus 7. We'll simplify this, so we're going to multiply -2 over 11 on the right side. So this becomes -2 over 11 times x minus, and now we're going to multiply -2 over 11 times -7. Well, the negative and minus make a positive. 2 over 11 times 7 becomes 14 over 11. So we have y minus 5 equals this. We want to get y by itself because remember the formula was y is equal to mx plus b. We already have the mx right here, -2 over 11 times x, since our slope was -2 over 11. But we're trying to find b. And so what we need to do is add 5 to both sides. If we add 5, we add 5. So we get y is equal to -2 over 11x plus 14 over 11 plus 5. Now how do we add 14 over 11 and 5? What we need is a common denominator. The common denominator would be 11. So to write 5 with a denominator of 11, we can write it as 5 times 11 over 11, because 11 over 11 is just 1. So this would cancel to just being 5. Or if we multiply 5 by 11, we get 55 over 11. So now instead of writing this 5, we'll write 55 over 11. So I'm going to change this to 55 over 11. Now we simplify 14 over 11 and 55 over 11. 14 plus 55 is 69 all over 11. So this is y is equal to negative 2 over 11x plus 69 over 11. This is our equation in slope-intercept form, where 69 over 11, this is where it crosses the y-axis, and our slope is negative 2 over 11. Now, how do we write it in general form? Well, in general form, we want to put all the x's and y's on one side of the equation. So what we'll do is we'll add 2 over 11x to both sides of the equal sign. So on the left side, what we get is y plus 2 over 11x is equal to 69 over 11. Now this is an acceptable form for the general form. However, let's just divide or multiply both sides by 11, because this dividing by 11 just doesn't seem that nice. So if we multiply the left side by 11, and then we multiply the right side by 11, the left 11 times y becomes 11y plus 11 times 2 over 11. The 11 on the top and the 11 on the bottom cancel, so we're just left with 2x. This equals 69 over 11 times 11. Our 11's cancel, and we're just left with 69. And then the last step is to write the x before the y, so we end up writing 2x plus 11y is equal to 69. And that is the general form. Now, if we're given an equation, y equals negative 4/3 x plus 4, can you tell me what the slope is and what's the intercept? Well, this is written in the equation in the form of slope-intercept. The slope being negative 4/3, and 4 is the intercept. So this is the slope m is equal to negative 4/3, and then the y-intercept is equal to 4. Can we plot given this information? Sure. So we know that it crosses the y-axis at the point 4. And it has a slope of negative 4/3. So it rises down 4. So we're going to go down 1, 2, 3, 4, and it goes across 3. 1, 2, 3. To right here at this point. And so we draw our line. And that's it. What about if we have another example? If we have negative 5x plus 7y equals 9. What is the slope and intercept of this equation? Well, in this case, it's not as simple because this is written in the general form. It'd be really nice if it were in the slope-intercept form. Well, let's see if we can write it in slope-intercept form. That would be y equals something. So first of all, let's move this 5x to the other side. So we'll add 5x to both sides. So we have 7y is equal to 5x plus 9. Now this actually is the line through the 7 and not a negative 7. And if we want to find y by itself, we just divide by 7. Divide by 7, so we get y is equal to, now if we're dividing, we can split this up into two fractions. 5x over 7 plus 9 over 7. So we have 5x over 7 plus 9 over 7. And from this form, we can see what everything is. Our slope is of the form m equals 5 over 7. And then our y-intercept is equal to 9 over 7. Two lines are parallel if they have the same slope. That means if we were to plot two lines, and the slope of that line, another line having the same slope would look like that. Or something like this, if it went in that direction. So say we have a line of the form x plus 2y equals 6. Can you find a parallel line find a line that's parallel to this equation, but also contains the point 0, 0. Well, so what do we have? We know this point right here, and it's parallel to that line. What does it mean to be parallel? That means it has to have the same slope. So what we can do is find the slope. Let's change this equation into and move x on the other side. So we have 2y is equal to negative x plus 6. Solving for y, so we're going to divide by 2. We get y is negative 1/2 x plus 3. And I got this by I split negative x over 2 and then 6 over 2. 6 over 2 is 3. So what is the slope over here? The slope is negative 1/2. So change back to the pen. M is negative 1/2. We have our slope is negative 1/2 and the point is 0, 0. And we can use any form that we want. I'm going to use the point slope formula, which was y minus y1 equals m times x minus x1. In this case, our point y1 and x1 happen to be 0. So this is just y is equal to m. Our slope was negative 1/2. So y is negative 1/2 x. And that's our parallel line. Two lines are perpendicular if they form a 90-degree angle. Meaning we have a line like this, and another line crosses, and we have a 90-degree or a right angle. Now, in other words, if we have two lines, and the slope for the first line, we'll call it m1, and the slope for the second line is m2, if we multiply m1 multiplied by m2, it should equal negative 1. Or another way to think of this is if we divide, m1 is equal to negative 1 over m2. So if we're given a line that y is equal to negative 3x plus 2 and the point 3, 2, and you're asked to find a line that's perpendicular to this line and contains the point 3, 2. How would you do that? Well, if it's a line that's perpendicular, what do we need? We need to know the slope. So the slope of this first line, m1, is equal to negative 3. Now, since m1 could be written as negative 1 over m2, we could also write m2 is equal to negative 1 over m1. So in this case, m2, our second slope, would be negative 1 over negative 3, or just positive 1/3. So now we have a slope of 1/3, and we have the point 3, 2. So therefore, we know that the form of the line is going to be using the point slope y minus 2 is equal to 1/3 x minus 3. And so this is the answer in point slope. If you wanted to find the answer in slope intercept, what we would do would be multiply 1/3 through. So this becomes y minus 2 is 1/3 x minus 1/3 times 3 is 1. And now we add 2 to both sides. So we get y is equal to 1/3 x, and negative 1 plus 2 is just plus 1. And this is your answer. Or you could have left it in the first form. To check if two lines are parallel, perpendicular, or neither, you would check their slopes. So if we had a line that was 3x minus 2y equals 12, and then another line 2x plus 3y equals 6, we would need to find their slopes. So to find the slope, we would write it as, we would put the y on one side and the x on the other, so we get negative 2y equals, and I subtract 3x plus 12. And the second equation, I would subtract the 2x, so we get 3y is equal to negative 2x plus 6. Now to find the slope, what I need to do is get y by itself. So this first one I'm going to divide by negative 2y. So we get y is equal to negative 3x divided by negative 2, and then we had plus 12. And then we also had y is equal to, now we divide by 3y. So negative 2x plus 6 divided by 3. Now the second number that's kind of running off the screen is not that important. We're only concerned with the numbers related to x. So for the first equation, I'm going to write this as our first slope is just negative 3 over negative 2, or 3/2. The second slope m2 is negative 2/3. Now, it's clear that m1 and m2 are not the same, so they're not parallel. But if they're perpendicular, remember, it's perpendicular if m1 times m2 is equal to negative 1. So let's check that. Does 3/2 multiplied by negative 2/3, what does that equal? Well, the 3's cancel, so do the 2's, and we're left with negative 1. So yes, these two lines are perpendicular. In section F.4, we'll be discussing circles. So what is a circle? Circle is just something like that. How can you define a circle? Well, to define a circle, what you need is, first off, the center of the circle and the distance from the center to the edge, or what we call the radius. So if we say that the center of the circle is at some point, we'll call this h comma k, and if the radius is given by r, then the equation for a circle with radius r and at the center h comma k is given by the following equation. Is x minus h quantity squared plus the quantity y minus k squared is equal to r squared. This is the equation of a circle. This equation is of the form of a standard form. Notice that if our center is at the origin, so really if hk is equal to the origin, which is 0, 0, plugging in 0 for h and 0 for k, this first term is just going to be x squared. The second term is just going to be y squared, because there's k is 0. So it's just going to be x squared plus y squared is equal to r squared. Now if our radius is 1 and we're at the center, so if the radius is 1, then we have x squared plus y squared is equal to 1 squared, or just 1. And this is what we call the unit circle. So if I were to give you that a circle has a radius equaling 5, and it was centered at the point 3, negative 2, can you give me the equation in standard form of the circle? Remember, the equation for the circle is of the form x minus h quantity squared plus y minus k quantity squared equals r squared. In this case, our hk is given by 3, negative 2. So we make that substitution first. X minus h is 3, so x minus 3 quantity squared plus y minus k is negative 2, so this is really y minus a negative 2 quantity squared equals r squared. R is our radius, which here is 5. So this is equal to 5 squared. Simplifying this, we get x minus 3 quantity squared plus, when we have a y minus a negative 2, the minus negative becomes a plus. So this is y plus 2 quantity squared equals 25. And that's your equation. So what does this graph look like? Well, we have a graph whose center is at 3, negative 2. So the center is right here, and the radius is 5. So we'd count up 5. So going up from negative to 5, we'd also go down negative 5. We go to the right 5. And then from the center, we also go to the left 5. So each one of these, we counted up 5, we counted down 5, to the right 5, and to the left 5. Now this one down here is kind of squished because I ran out of room. But so when we connect the dots, you see it is sort of like a circle. Now if I were to give you the equation of a circle, say something of the form maybe x plus 1 quantity squared plus y squared is equal to 16, can you tell me what the center of this circle is and what's the radius? Well, we'll start with the radius. 16 can also be written as 4 squared. So we know just by this that the radius is equal to 4. But what about the center? Recall that the form in standard form is going to be x minus h quantity squared plus y minus k quantity squared equals r squared. So what is h? So h is what's next to this x, which should be this number. Since we have a plus instead of a minus, we could rewrite this first one as x minus a negative 1 quantity squared. That way we have a minus gives us a plus. That's where we get the plus 1, but it's still of this form, x minus h. So therefore, h is equal to negative 1. And now what about our k? Y minus k. Well, I don't see a k right here. In that case, that means that k should be 0. So our center is at the point negative 1, 0. And so let's graph this circle. We have a center at negative 1, 0 with a radius of 4. So we'll go to the right 4. So we'll count off 1, 2, 3, 4. Count to the left 4. 1, 2, 3, 4. We'll count down 4. 1, 2, 3, 4. And up 4. 1, 2, 3, 4. And our graph looks something like that. So the standard form for the equation of a circle is given by x minus h squared plus the quantity y minus k squared is equal to r squared. Now there's another form for writing the equation of a circle, and this is given with the equation x squared plus y squared plus ax plus by plus c equals 0. This is what we call the general form. If you're given that a circle is centered at the point 2, 6 and has a radius equaling 3, what is the equation of this circle? Well, using the standard form, the equation of this circle would be x minus 2 quantity squared plus y minus 6 quantity squared equals 3 squared. Or maybe we'll write it as equals 9. Now this is standard form. How could you write it in the general form? Recall that the general form, we'll write it up here, is x squared plus y squared plus ax plus by plus c equals 0. So what we'll do is we'll expand the squares, x minus 2 squared and y minus 6 squared. And recall that if we have something of the form, we'll write it as a plus b quantity squared, that's the same as saying a plus b times a plus b. And if we multiply that out, we have a squared, because we'll do a times a, so we get a squared, plus a times b, so we get a plus ab, and then we have our second term, b times a, so we get ba, or maybe we'll write it as another plus ab, and finally we get b times b, which is b squared. Simplifying, we get a squared plus, well, we have ab twice, so we have 2 times ab plus b squared. Now there's a formula. If you remembered this, you notice we can just go straight from a plus b quantity squared to this right here. So this is just a, the quantity squared a, and then we have b squared back here, and then this is going to be twice of this first two made. It's important to note, because I see this mistake quite often, that the quantity a plus b squared is not equal to a squared plus b squared. It's not equal to that, because we have this extra thing right here, 2 times a times b. So now that we have that, what is x minus 2 quantity squared? Well, that's going to be x squared minus, and if we're going to use this formula, 2 times a times b, this is going to be 2 times our first term is x, and our second term is 2. So 2 times x times 2 plus the second term squared plus 2 squared. And then we look at the next term, x minus y squared. So the first term is going to be y squared minus 2 times y times 6. So minus 2 times y times 6. And finally we're going to do plus 6 squared. And that is equal to 9. So let's simplify. So we have x squared minus 2 times x times 2 is really just 4x plus 2 squared is 4 plus y squared. And now we have 2 times y times 6, or that's 12y plus 36 equals 9. Alright, so let's do some moving around. So our x squared and our y squared, those will come first. So we'll have x squared plus y squared. So I already took care of that, x squared and y squared. And then the next terms, if we're looking up here in the top right, so we have x squared, y squared, and now we look at the ones with ax and then by. So the terms with x is right here, and the term with y is right there. So this is going to be minus 4x minus 12y. So now we took care of those two. And now we'll combine our constants, our 4 and our 36. So that gives us 4 plus 36 is 40. So we get 40 equals 9. And the last thing to do is just move this 9 over. So what we'll do is we'll subtract 9. Subtract 9. And so finally we get x squared plus y squared minus 4x minus 12y plus 40 minus 9 is 31 equals 0. So this is our equation in general form. What about in the opposite direction? If you're given the equation of a circle in general form, can you find the center and radius? So let's do an example. We have x squared plus y squared minus 14x plus 16y plus 97 equals 0. First thing we'll do is we'll move the 97 to the other side. So we'll subtract 97. And then we'll also group the x's, the terms with x's together, and then the terms with y's. So we'll have x squared minus 14x plus y squared plus 16y is equal to negative 97. So we'll group these by putting them within a parentheses. Now, we look at this term with a single x and the term with a single y. And what we'll do is we'll take that term in front, so negative 14, and we'll divide that by 2 and then square that value. So negative 14 divided by 2 is going to give us negative 7. Negative 7 squared is going to be 49. And then we look at the terms of the y. The number in front of the y is 16, so we'll do the same steps. We'll take 16 divided by 2 and square it. 16 over 2 is 8. 8 squared is 64. So what we're going to do is we're going to take these numbers 49 and 64 and we're going to add it to our equation. 49, since it came from the x terms, will be added right here. And 64, since it came from the y term, will be added right here. But whatever you do to the left side of the equation, you must do to the right. So if we added x squared minus 14x and we add plus 49, we're going to have to add plus 49 to the right side. So on the right side we have minus 97, we'll do plus 49. And now for the y term, so we have plus y squared plus 16y, and here we're going to add the term with the y, so the 64. So we add plus 64, and since we added 64 to the left, we add plus 64 to the right. And if we add 64 minus 97 plus 49, we end up with 16. Now the next part is a little bit tricky, but what we'll do is we look at this, and this, because of what we just did in the previous two steps over here, it actually ends up being a perfect square. This is going to be of the form x minus some number squared, and then we'll have y plus some number also squared, gives us 16. So what is that number? Well, the number that goes right here actually is just that number that we used over here. So that's going to be 7. Since it was a negative 7 up here, we subtract. The next number right here ends up being that 8. So y plus 8. And that's the equation in standard form. So the center is 7, negative 8, and the radius, well, radius squared is 16, so the radius is 4, since 16 could be written as 4 squared. In section 1.1, we'll be discussing functions. Well, what is a function? A function is some sort of box that takes an input and spits out some sort of output. So you can think about it like this. Say maybe like this machine, we'll call this machine our function f. And what goes into this machine, maybe we'll say x goes into the machine, and it goes in, gets a function, and outputs f of x. So this x that goes in right here, this is what we call, what goes in is what we call the domain. And what comes out, this right here, that value, that will be part of the range. So the domain is all of the possible inputs, and the range would be all the possible outputs. Now the thing with a function is that if you have one input, you can only get one output. So you cannot have two or more outputs for the same input. And we'll go over that in just a moment. So if you see something, an equation that looks like this, y squared equals 13x plus 4, this is not a function, because of the y squared. But if you saw something like this, x cubed plus 2x squared plus 5 equals negative y, this is a function because y only has a power of 1, and that's okay. So say if you had for your input 3 different meat options, pork, beef, or fish, and say for your output you had 3 different side options, rice, fries, or salad. Now we could connect pork with rice, beef with fries, and then fish with salad. This would be a function, because every single time you have an input, you get exactly one output. So you have an input, you know exactly where you're going, one output and one output. So this is a function. If instead we said pork goes to rice and beef will also go to rice, but fish goes to salad, is this a function? Well, think about it. A function means that if you have an input, you know exactly where you're going. Well, if you have fish, you know you're going to salad. If you have beef, you know you're going to rice. And if you have pork, you also know you're going to rice. So this is a function. But what about if we had this? If you had pork, you might get rice or you might get fries. If you have beef, you get fries. Then if you have fish, you get salad. Well, for it to be a function, for every input, you know exactly the output. You have one output. So fish, you know you're going to salad. Beef, you know you're going to fries. But because pork, you don't know are you going to rice or fries, there's 2 outputs. So in this case, it's not a function. Sometimes you might be given things as a set in ordered pairs. So you might have 3, 5, 6, negative 2, and 2, 12. Is this a function? Well, think about it. Our x would be our input, and our y value would be our output. So if we have a 3, we know we're going to get a 5. We have a 6, we know we're getting a negative 2. And we have a 12, or excuse me, we have a 2, we know we get a 12. So yeah, this is a function. If, however, we had 3, 5, and then we had 3, 12, and then 6, negative 2, this is not a function, because if we're given with a 3, we might go 3 to 5, or we could go 3 to 12. Since there are 2 y values, 2 outputs, if you start off at 3. So if we were to draw this in the terms of what we were doing before, we'd have 3 and 6, for our inputs, and then we would have 5, 12, and -2 for the outputs. 3 can go to 5, or 3 can go to 12, and then 6 goes to -2. So if we listed it this way, you can see that it's not a function. If we were to graph or plot the points, we can also see. So we have 3 and 5 right here. We have 3 and 12. Well, we ran out of room for 12, but let's just say that 3, 12 is up there. And then we have 6, -2 down here. What you notice is that if you have 2 points lining up vertically, that would make it not a function. If we had an equation like this, x squared plus y squared equals 1, what is that? Well, we can solve for y, so we'll get y squared, and we subtract x squared from both sides, would equal 1 minus x squared. To solve for y, we take the square root. So y is equal to, when we take the square root, we're going to have plus or minus. So y is plus or minus the square root of 1 minus x squared. So notice that when we plot our y, we're going to have the positive and the negative of that. So what that looks like is this. We're going to have this part, and this is where y is the square root of 1 minus x squared. And then we're going to have this part down here where y is the negative square root of 1 minus x squared. But for any input, any x value we might have, say an x value right here, we have two y values, a positive and a negative. So this is not a function. So this is not a function. And to tell if something is not a function, we do what's called a vertical line test. So we draw a vertical line and see, does it cross the function twice? It crosses up here once and crosses down here a second time. So if it crosses more than once, it's not a function. And you can tell that it's not a function by looking at it by the power of y. If y has a power of 2 or 4 or any other even number, it's not a function. Now, as I mentioned before, a function can be thought of as a machine. So if we have something like f of x takes the input x and outputs, say in this case, 3x plus 2. So it takes an input, which is our x, and what does it do? It multiplies 3 by that input and adds 2. And this is regardless of whatever the input is. It's always going to have the same process. So if our input was 5, what the function does is it multiplies 3 by that input, so 3 times 5, and we add 2. Well, 3 times 5 is 15. 15 plus 2 is 17. And this works for anything. You know, if we put as our input -2, then we have 3 times our input, so 3 times -2, and add 2. 3 times -2 is -6. -6 plus 2 is -4. But this can be more than just that. What if our input was a variable? So we have f of some variable a. What does the function become? Well, it's the same thing. So we're going to say 3 times the input, so 3 times a plus 2. And that's our function, 3a plus 2. It can really be anything you want. So think about this way. What about if our input was just a plain box? F of a box. What does that do? Well, we take 3 times the box and add 2. So we could do something else. Maybe if we have our input is x plus h, what would that be? Again, so our input is just going to be this, x plus h. And what do? We multiply what's inside here by 3. So this is going to be 3 times x plus h plus 2. And that's how we deal with a function. You might have, for another example, our function f of x is x squared minus 1. So what does this do? This takes our input, squares that value, and subtracts 1. So what if we said f of negative x? What is that? Well, we put negative x in for our input. So this is going to be negative x, and what happens to our input over here? We take the input and we square it. So this is going to be negative x squared minus 1. And what's negative x squared? A negative times a negative is positive. So this is just going to be positive x squared minus 1. Okay? And we can do, another number. We could do, say, maybe f of 3. F of 3 takes our input, squares it, and subtracts 1. 3 squared is 9. 9 minus 1 is 8. We could also put, maybe, if our input was the square root of x. So what does this do? We take our input, the square root of x, square it, and subtract 1. Well, what is the square root squared? They cancel each other and you're left with x minus 1. Now that we've defined a function, we can find its domain. If we have a function that looks something like this, f of x is equal to 5x minus 4, what's the domain of this function? Now remember, the domain is all the possible input values. So it's all the possible x values. Well, in this case, x can be anything. So our domain is all real numbers. But what about if our function, instead of writing f, I'll write a different value, g of x. G of x is 3 over x minus 7. What is the domain? Well, the domain are the possible x values, and we look for when can it not be possible. Well, we have a fraction, and what can we never divide by? We can never divide by 0. So we cannot have, so x minus 7 cannot equal 0. Or in other words, x cannot equal 7. So our domain is all numbers except x equals 7. Okay, so all numbers are all real numbers except x equals 7. Well, what about if we have another function? H of x is equal to the square root of x minus 9. Square roots can never be negative. So in this case, what's inside the square root, x minus 9, has to be greater, or the, so if we add 9 to both sides, we get x has to be greater than or equal to 9. And that's the domain for this problem. X has to be greater than or equal to 9. Now say we have two functions. F of x is 5x squared minus 4, and g of x is 3x squared plus 2x plus 12. What would we do if we were to ask, what is f of x plus g of x? Or written in another way, f plus g of x. All this is this is adding two functions right here. So if we're going to add these two functions, we're going to take this first function and just add it to the second. So we get 5x squared minus 4 plus 3x squared plus 2x plus 12. Now we can combine some terms. Our x squareds, we get 5x squared plus 3x squared, so we get 8x squared. And then we get so we combined our x squareds. Now we look at our x, so this is plus 2x. And then we look at our last numbers. Negative 4 and 12, that gives us 8. And that's it. This is just f plus g of x, the sum of two functions. What's the domain for this? Well, what are all the possible x values? We're not dividing, and we don't have a square root, so our domain is going to be all real numbers. And what about if we had two more functions? F of x is negative 3x plus 8, and g of x is going to be 6x minus 9. Well, if we were to ask, what is f minus g of x? Now that is the same thing as saying f of x minus g of x. And so we just go through and figure out what is f of x and subtract g of x. So we have, this is going to be negative 3x plus 8 minus the quantity 6x minus 9. Remember, since we're minusing a whole quantity, we need to distribute the negative. So this is negative 3x plus 8 minus 6x minus a negative 9, so this is plus 9. Make sure that you put this parentheses, otherwise you might forget that this 9 becomes positive. Alright, now we group our terms, our x's, so we have negative 3x, negative 6x, that gives us negative 9x. Then we have 8 and 9, and that gives us 17. And there we have it, subtracting two functions. And the domain for this function, just like the other one, since we don't have any dividing by 0 or a negative in a square root, the domain will be all real numbers. Well, we've added and subtracted functions. Now we're going to multiply functions. And it's going to be basically the same step. So if we have two functions, let's say f of x is negative x plus 8, and g of x is 3x minus 4. If we were to find the product of these two functions, we would write it as f times g of x equals f of x times g of x. So we just multiply these two together. So we're going to have negative x plus 8 multiplied by 3x minus 4. And we're going to go ahead and FOIL this out. So we're going to multiply negative x times 3x, negative x times negative 4, 8 times 3x, and then 8 times negative 4. So let's do that. Negative x times 3x is negative 3x squared. Negative x times negative 4 is plus 4x. 8 times 3x is 24x. And 8 times negative 4 is negative 32. So we get this is negative 3x squared plus 4x plus 24x is 28x minus 32. And so there we have the product. And again, because we're not dividing by 0 and we don't have a negative square root, the domain is going to be all real numbers. And finally, the last thing that we're going to cover in this section is the quotient, or when we divide two functions. So let's write out two functions. F of x is negative 3x plus 4. G of x is going to be x plus 7. So if we wrote out the quotient, f divided by g of x, we mean by that f of x divided by g of x. So this is our f function, negative 3x plus 4 divided by our f function divided by our g function, x plus 7. And this is it. That's our function. However, since we are dividing by 0, or we could potentially be dividing by 0, we have to make sure for our domain that x plus 7 cannot equal 0. So our domain means that x cannot equal negative 7, or all values except negative 7. In section 1.2, we're going to talk about the graphs of a function. So if you look at a graph, how can you tell if it is a function? Recall that a function, if you have one input, it gives you exactly one output, not two outputs. So if we had a function and you look at the ordered pair, we have an x as our input. What it outputs is the y value. So if you have one input x, you're only going to have one output y. So in terms of the graph, what that means is if you had a graph that looks maybe something like this, for every x value, there's exactly going to be one y. So in this case, if x is right here, there's one y value down here. Or if x is down here, there's only one y value. Now, this is a graph, but if we looked at a similar graph, and we had something that looks like this, well, if we have one input, an x value right here, we have two y values, one up here and the y value down here. So there's two different outputs. So this is not a function. So our first one is a function, and the second one is not a function. So how can we tell? Well, if you're given the graph, if you draw a vertical line, and this vertical line only crosses the graph once throughout the whole graph, so we could draw another vertical line, and we still see it only crosses the graph once, then it's a function. If a vertical line crosses the graph two or more times, then it's not a function. So right here, we cross twice. Now, you can cross 0 times. So over here, we might have 0 crossings. Or maybe at this point, we have just one crossing. But, I'm going to write this down. If a vertical line crosses the graph two or more times, then it's not a function. So let's take a look at some more examples. If we have a graph that looks like this, is that a function? Well, we look at vertical lines, and and how many times does the graph cross the vertical line? Just once. What about if we had something like this? Well, this is not a function, so this first one is a function. The second one is not a function because we have one example where it crosses 3 times, so that's not a function. Now we might have a graph that looks something like this. This is the graph of our function f of x. Would you be able to tell me what is f at 0? What does that mean? This means if the x value is 0, what is the y value? So let's look. When x is 0, our y value is 4. So f of 0 is 4. What about this? What is f of 11? So f of 11 would be when x is 11, which is out here, the y value is 0. A graph like this, what would the domain be? Remember, the domain is all the possible x values. Well, this function goes on in the x direction forever. So our domain would be all real numbers. What about the y values? Well, what y values does this cover? And that's the range. So the range is just the possible y values. And the range just covers, it only goes from -4 all the way up to +4. So we can write that either in interval notation between -4 and +4, or we can write it as y is going to be between -4 is less than or equal to y, which is less than or equal to 4. So this first one is a 4, not a y, or -4. Now, if you're given a function, let's say the function is f of x is equal to -4 times x squared plus 8x minus 9, and I asked, is the point 1, -5 on the graph? So is 1, -5 on the graph? Well, what does that mean? Is the point on the graph? So when I say is the point on the graph, that means looking at the graph, can we find that point? So let's zoom in on this graph a little bit. Zoom in a little bit more. And this is saying that at the point when x is +1, is y -5? And yes, the point 1, -5 is on the graph. So yes, it is. But if we didn't have the graph, is there a way to tell? Well, what this is saying, so when x is 1, so if x equals 1, is y equal to -5? How can you tell that? Well, without the graph, we can plug in the x value into f of x and see if it equals the y. So f of 1 equals, plugging it into the equation right here, f of 1 is equal to -4 times 1 squared plus 8 times 1 minus 9. So -4 times 1 squared is -4. 8 times 1 is 8 minus 9. 4 minus 8, or excuse me, 4 plus 8 minus 9 is equal to -5. Well, that's the -5 we're looking for. We're trying to look to see if it is. So yes, our answer is yes, it's on the graph. In section 1.3, we're going to look at properties of functions. Now, if you remember from the earlier sections, if we saw a graph that looked like this, we said the graph that was this, we called it symmetric about the axis, about the y-axis. A graph that's symmetric about the y-axis is something that we call an even function. So we're going to start talking about even functions. So a function is even if it's symmetric about the y-axis, now if you notice from here that if we had a point, say over here, and we had an x value. Let's call this x. The corresponding y value, that would be f of x. Now if we went to the opposite side and we had negative x, the corresponding y value up here is also going to be f of x. So if a function is even, it also has the property that f at negative x is equal to f at x. Now why do we want to know if a function is even? Well, sometimes if we're trying to graph it and we know the function is even, we only need to graph 1/2, and since we know it's symmetric, then we can graph the other half quite easily. One other thing to note about even functions is that the function will look something of the form and only have terms with x squared, x to the 4, x to the 6, and so forth, or even an x to the 0. What is any number raised to the 0 power? Well, any number raised to the 0 power is 1. So we call that a constant. So constant numbers. So if it has constants, such as 3, 4, 5, or x to any even powers, that's what will be a function, an even function. This is only if we have a polynomial, so just powers of x. So an example of that might be f of x is x to the 6 plus 2x squared minus 3. So we have x to an even power, x to another even power, and then a constant, negative 3. So all of these would make it an even function. But if your function has other things in it like square roots, or if there's a fraction dealing with x, then this doesn't apply. You have to check if it is even by checking that out. So let's do an example for that. So if we have the function f of x is equal to 3x squared. Is this even? Well, we know it's even because it only has an even power of x. It doesn't have x to an odd power. So yeah, it is even, but if you wanted to check, what we do is we first put negative x into our function and hope that it comes out to be positive, or f of x. So we're going to do 3 of negative x, or 3 times negative x squared. So we just plugged in negative x into our function. What's negative x squared? Well, negative times negative is positive, so this is 3 times x squared. What is 3x squared? Well, 3x squared is just f of x. So notice that f of negative x equals f of x. That's exactly what we said on the previous slide, so that the function is in fact even. Now if we can find even functions, the other functions that there are called odd functions. An odd function looks something like this. Now we saw a function that looked like that before. So an even function was symmetric about the y-axis. What kind of symmetry is this? Well, odd functions are symmetric about the origin. What does it mean to be symmetric about the origin? Well, you can think about it as being reflected about the x-axis and then y-axis. So think about this part right here. If it's symmetric about the x-axis, it would be flipped down to look something like that. And when we have a shape like this that's reflected then about the y-axis, we get this shape. So this is an odd function, and it's symmetric about the origin. Now, what that means is, again, we'll take a point, say x, and what is the y value? The y value is our f of x. Now if we go to a negative x out here, what's the y value? Well, that y value, notice, it's going to be the same distance as that, but in the negative. So that value is negative f of x. So we would write that f of negative x is equal to negative f of regular x. Okay, the difference between odd and even is this negative right here. And another way of determining if a function is odd or even, or excuse me, odd, is that if it only has odd powers of x. Okay, and by odd powers, we mean x to the 1, which is really just x, x cubed, x to the 5th, and so forth. So an example might be something like f of x is 3x cubed plus x. This is an odd function because there are only odd powers, 3, and that would be a 1. An example of an odd function would be f of x equals 2x cubed plus x. Well, what are all the powers of x? The powers are 3, and this is x to the 1. So these are all odd powers, so we know that it is an odd function. But we can test it the other way just in case. F at negative x is equal to 2 times, and we're going to substitute negative x in when we see x up here. So this is going to be 2 times the quantity negative x cubed plus negative x. So this is going to be, what is negative x cubed? A negative times a negative times a negative is a negative. So negative 2x cubed. Negative x times negative x times negative x is negative x cubed. And then 1 times negative x, excuse me, plus a negative x is just a minus x. So this is negative 2x cubed minus x. Well, we can actually factor out a negative from this. And if we factor out a negative, we're left with 2x cubed plus x. Because a negative in the plus would give us our minus up here. Well, what is 2x cubed plus x? That's what our function was, our f of x. So this is equal to negative f of x. F of negative x is negative f of x, so therefore we just showed that this function is odd. Now we'll look at if a function is increasing or decreasing. Well, if we had a graph and it looked like this, how can you tell if the function is increasing or decreasing? Well, if it's increasing from this point to this point, we'll say this first point is x1 and the second point is x2. How do you know if it's increasing? Well, by looking at the graph, yeah, it's going up. So that is increasing. But what is the y values? Well, the y value here is our f value. So that's f at x1. And then this would be our f at x2. So if it's increasing, So if it's increasing, that means that f at x2 is bigger than f at x1. Alright, and that's assuming that our x2 value is bigger than x1. Okay, so that's the book's definition, but it should be fairly intuitive. And of course, if it's decreasing, so say we start at this point, and we go down here, it would be decreasing if we had a point for the first one, x1, and this is our x2, our f at x1 is a larger value than our f at x2. So it's decreasing if f at x1 is greater than f at x2, assuming that x2 is greater than x1. So the difference here is that f of x1 is greater than x2, or f of x2 is greater than f of x1. If it's constant, that means it's not moving at all. So if it's constant, that means it's flat. The function is not increasing, it's not decreasing, it's flat, and so f of x1 equals f at x2. Now if you're given a plot of a function, and we had a plot like this point up here is what we call a local maximum. It's called a local maximum because, well, it's the maximum value in this range. So in between here, it's the maximum value. There's nothing higher than that. And so it's a local maximum because you never really know what goes on outside of that range. Maybe the graph continues and it goes up higher. So a local maximum is just anywhere around here, there's nothing else that's higher. If we have a point that continues down here, that would be called our local minimum. And for similar reasons, it's a minimum because there's nothing else that's lower than here in that region. But we don't know if there's another local minimum or not. Now functions can have multiple local maximum and local minimum. So if we had something that looked like this, all of these peaks are called local maximums. So these are all local max. And then these 2 points down here are what we call the local minimums. Now, these endpoints, they're not local max or local mins because we don't know what's further on beyond that. Does it keep going? So this is really not what we call a minimum. A local minimum is if there's anything else below it or anything else around it is higher. Well, we don't know if it keeps extending. So just the low ends of these points. Now if we define our interval for a function, let's just say we have the function that looks like this, and we define the interval to be between these 2 points, and I'll just call these 2 points A and B. So if we're on some interval between these 2 points, what we define to be the absolute maximum and the absolute minimum is anywhere in the boundary between A and B. The tallest or the highest point would be the absolute max, and the lowest point would be the absolute min. So absolute max and absolute mins, the key thing to note about there is that they can contain the endpoints. So what is the absolute max in this function? Well, they look pretty close, but that's probably the highest peak. And so this would be the absolute max. Now what is the absolute min? Well, it looks like right here, right at the end point, that would be the lowest point. There's nothing else lower than that, so that's going to be our absolute min. So what are our local maximum and local minimum points? Well, local max and local mins are at the peaks or at the dips. So we have these 2 points are local max, and these 2 points are local mins. This point right on the end, well, that's not a local max, because remember, it has to be at a peak. And it's not an absolute max because there's a value higher. So this end point ends up being nothing. Now you might come across some graphs that might look like this with some circles along the way. And they might be filled or unfilled circles. A filled circle means that we include the point. An unfilled circle means we don't include the point. And I'll circle that as well. So what is the absolute maximum of this? Well, normally the absolute maximum looks like this point is going to be the highest, so that would be the absolute maximum, but we are actually not including it. So what is it? Well, you could get really close to it. Anywhere over here is higher than that point, but there's no place because you can get infinitely close to it. So if it's unfilled like this, as you might see on some of your homework problems, the answer would be there is no absolute max. You could have local max. These two values, or excuse me, just this value would be a local max. A local min would be two values down here, 1 and 2. So these would be your local mins. And in fact, this point happens to also be the absolute min, because there's nothing lower than that. And if you have a graphing calculator, your graphing calculator has a function in plotting to find the local max and local mins. The last topic of this section is called the average rate of change. And the average rate of change can be found by taking the change in y divided by the change in x. Or another way to think about it is to write, in terms of the function f at some point b minus f at some point a divided by b minus a. And this is assuming that b and a are different points. So this is the formula for finding the average rate of change. So, for example, if you're asked to find the average rate of change for a function, f of x equals 4x minus 8, and you're going to find the average rate of change from the point 1 to 2, how do you do that? Well, the average rate of change would be f at 2 minus f at 1 divided by 2 minus 1. We're just using this formula right here. So we plugged in f at the second value minus f at the first value subtracted by the second x minus the first x. So what is that? Well, here's where it takes a little bit more steps. How do you find f at 2? So we'll do some work down here. What is f of 2? Well, the function is given right here, so it's going to be 4 times our input minus 8. So f at 2 is 4 times 2 minus 8. 4 times 2 is 8. 8 minus 8 is 0. So f at 2 is 0. What's f at 1? Well, f of 1 is going to be 4 times the input. Again, we're reading from here. 4 times the input, which is 4 times 1, minus 8. So 4 times 1 is 4, minus 8 is negative 4. So we're now going to complete this. F of 2 is 0, and f of 1 is negative 4. So this is 0 minus negative 4 divided by 2 minus 1. 0 minus negative 4 is positive 4. 2 minus 1 is 1. So 4 over 1 is 4. And that's your average rate of change. In section 1.4, we'll discuss some more functions. We'll start with some functions that you should have memorized. If you see the graph of a function, and it were to look something like this, this is what we call the square root function. This is of the form y is equal to the square root of x. If you're to look at a function and its graph looks something like this, kind of like an S shape, this is the cube root function. And that's y is equal to the cube root of x. If you had a function whose graph has this V type of shape, that's the absolute value function. And that's when the graph, or the function, looks of the form y is equal to the absolute value of x. If you had a function whose graph is just a plain horizontal line, that's what we call the constant function. That's where the graph y is equal to just some constant. Let's say b, like y is equal to 2 or y is equal to 3, but some value that's not in a variable, so no x involved. That's what a horizontal line is. In fact, all these y's are really our functions. F of x should be equal to that. F of x. And this is f of x. And this one too is also f of x. Now, if we had a graph that just looks like a straight line that goes up, that's the identity function. That's the function f of x is equal to x. Now, instead, if the graph were to look like that, kind of like that U shape, some of you might know that's a parabola, but that's the function f of x is equal to x squared. That's a square function. Now, if the graph were to look something like that, that's the graph of a cubic function, or f of x is equal to x cubed. And then the last graph that we'll talk about that you should know what it looks like is if we had a graph that looked like this. So let's say those are our axes, and the graph did something like that. That's what we call the reciprocal function. That's where f of x is equal to 1 divided by x. The next thing we'll look at is what we call piecewise functions. A function is called piecewise because it's a function that we take in pieces. For example, we might plot a function that might go like this, and then at a certain point stop and continue down here, and we have a different function that might go downwards and stop and continue right here, and maybe be like that. So we start off at a certain point, and we have one line that has a positive slope. And once we get to this point, it's an open circle because we're not including that point, because remember, a function, it can't be a function because it can only have one output. And so the output at that particular x would be down here. So we have that one x goes down here, and we have a different line, and now this line has a negative slope until we hit to this point, and instead of having two of the y values, it's not including here, and it jumps up to here. And now we have a horizontal line, a constant slope. So this is a single function that's in three pieces. One that increases, and then one that decreases, and one that has a constant slope. So let's do another example. If we were given the function f of x is equal to, and we write a piecewise function like this. We write the first part of the function, x plus 1, and we're going to say, what are the x values? And this is if x is less than 1. And then we write the next part of the function, and we'll say that's going to be negative 3. And this is if x is greater than or equal to 1. Basically, what this means is that we have the function f of x equals x plus 1 when x is less than 1, or we have f of x is equal to negative 3 when x is greater than or equal to 1. What does that graph look like? Well, we can plot these, and we'll start with this first one. So if we're to plot f of x equals x plus 1, we have, this is of the form slope-intercept. It has an intercept of 1, it intercepts the y-axis at 1, and it has a slope of 1. So we have a y-intercept of 1 and a slope of 1. So it goes up 1 over 1, or down 1 to the left 1. So that graph looks something like that. This is the first one. F of x is equal to x plus 1. What does the second graph look like? The second graph, f of x equals negative 3, is the horizontal line down here at negative 3. F of x equals negative 3. But we're looking at our constraints. We're constrained to the fact that x has to be less than 1 for this first graph. So where is that? When x is 1, that's right here. If x has to be less than 1, that means anything to the left of this is what we're using. And let me change the size of this pen. So anything to the left of here is what we have. And now we look at the next graph. F of x equals negative 3. That means that x has to be greater than or equal to 1. So when x is greater than or equal to 1, we're going to be on the other graph. And so, let me change the pen back. So we're going to include that point, and then we're going to go over like that. That's what the graph looks like. And let me move over, and just so you can see it sort of on its own. That graph would look something like this. That's sort of an idea of what the graph would look like. Where the first one, this part right here, or this part right here, comes from the first line saying that f of x is equal to x plus 1, but we're less than x is 1, and as soon as x is greater than or equal to 1, we're at the second line. So let's take a look at one more example. If f of x were equal to x plus 3 if, let's say that x is going to be between -8, so -8 is less than or equal to x, and x is less than 4, or -6 if x equals 4, or -x plus 5, and that didn't come up too well, -x plus 5 if x is greater than 4. So here we have three different things. So let's check this out. What does the graph look like? We're going to plot one line, a second line, and then a third line. So let's get started. So the first line is going to be y equals x plus 3, right here. X plus 3, that has an intercept of 3, a y-intercept of 3, with a slope of 1. And so that line, we go down 1, over 1, down 1, over 1. When I draw the line, I'm going to draw it with a dashed line. Okay, we're going to draw it with a dashed line like this. Alright, so that dashed line sort of went a little bit high. But now that we have our first line, this one right here. Now we draw the second line. The second line is y equals -6. -6 is down here, and we'll also draw that in a dashed. So we have down there. And finally we'll draw the next line, which is -x plus 5. So that has an intercept of 5. And so intercept of 5, maybe that would be up here, but has a slope of 1 or -1. So we start from here, go over 1, down 1, 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 and so forth. And so we'll also put a dashed line for that. And so now we have our three lines. Our first line right here, our second line, and then our third line that looks like that. Now the first line, we said the first line is going to be between -8 and 4. So I didn't draw all the way up to -8, didn't have enough space, but we'll go up to 4. So 1, 2, 3, 4. So it goes all the way up to 4. Well, where does that first line meet 4? Way up here. Alright, so now that we know where that is, we'll go ahead and make this solid, or excuse me, this dashed line a solid all the way up to 4. Now the next thing is we look at the next point, -6. So we're looking at this dashed line down here, and what x values do we use? Oops, excuse me, I forgot. When we're up here at 4, it doesn't include 4, so we have to make sure that we put an open circle. Now we can return to the -6 down at this line. And what's the x values we're using? Well, in this case, it's just 1 point when x is 4. So we're going to look where x is 4 over here, and we see where it intersects, which is right there. And if it's just a single point, we represent that point with just a circle. And finally, we now look at the last line, which goes like this. And where does that last line use? We use the points where x is greater than 4. So we start from 4, and we go further on. So we're going to do 4 and on. And since it doesn't include 4, we put another open circle. And this is what our graph looks like. So if you use dashed lines, you can fill it in once you figure out exactly what you're doing. In section 1.5, we're going to look at graphing techniques using transformations. In 1.4, we looked at several different functions that you should have memorized. For example, if we had a function that looked like this, what is that? That's a square function, and the equation of this function is f of x is equal to x squared. What happens if we were to take this function and move it down 1, 2, 3? We move it down 3. Well, first of all, let me retrace this. And now I'm going to move this down by 3. So we're going to take this and we're going to move it down 1, 2, 3. Alright, now notice my axis kind of went with this, but no, it still went down 3. So what was once over here is down 3. What was over here got moved down 3. What was over here got moved down 3. So what was happening is that it took whatever the y value is, or the f of x value, and subtracted 3. So this equation is now f of x. We started with f of x is x squared, but whatever we did, we always subtracted 3 from that. So that's the new equation. F of x is equal to x squared minus 3. What about if we were to raise it up by 3? We take this and move it up by 3, or maybe just up by 2. Let's say 2. Well, if we moved it up by 2, the graph would look something like that. So if we took a y value and we went up by 2, and we took the y value here and went up by 2, and over here and went up by 2, that new equation is f of x is equal to x squared plus 2. So if we have vertical shifts, then what we have is that our function y is equal to f of x, and we add plus some value k, and this means we're going to go up. So this goes up by k, and this is assuming that k is really a positive value. If we instead did y is equal to f of x minus k, then that goes down by k. So I'm going to pull up this website, www.desmos.com/calculator. On the left side, we input an equation, say y equals x squared, and it will graph it. You can put y equals x squared plus 2, y equals x squared minus 2, and it'll graph that as well, and you can put in multiple equations. Now right now, this is not allowing me to work on this, so I'm just going to have to explain it. So if you hit this plus value right here, you can go ahead and add extra graphs. But the one thing that is really useful is if you were to write our function f of x is equal to x squared, and you put in some variable, you add plus c, what will appear is a slider. It says add slider. You double click on that, and then the slider will give you different values for your c, and you can see how the graph changes as c goes between -10 and +10. So now let's go back and look at the equation y equals x squared. And we already covered what happens if we move it up or down, but what happens if we move it to the left or to the right? So if we took this graph and we moved it, say, to the left by 2, it would look something like this. This is the graph moved to the left. Now what's the equation for this line? This line, if we moved it to the left, it's not y equals x squared minus 2, it's not that, because remember, when we subtract 2, that actually moves it up and down. So if we're moving it to the left or right deals with x. So what's going to happen is that this is going to be related to whatever the x is. In this case, the x deals with something that's squared. So we're going to have x, and we're moving it 2. Now, the case with left or right shifting is that if you move to the left, normally going to the left is minus. But left or right, it's going to be the opposite sign. So we're actually going to add plus 2 if we move it to the left. So this is y, or f of x, is equal to the quantity x plus 2 quantities squared. If whatever where our root function is, if it's the square root of something, or the absolute value, or the reciprocal, what's happening to the x, that's the number, that's where we add our number. Now in this case, it is the opposite sign. We're adding if we're going to the left. Now let's try and make some sense of this. Our original function, let's look at this point right here. At the origin, this is the point 0, 0. That's the origin. That same corresponding point would be this point right here, shifted over. So what is that point right there? That's the point -2, 0. If we substituted -2 in for x, -2 plus 2 ends up being 0. And that's what we wanted. We wanted the y value to be 0. So putting -2 plus 2 gives us 0. And that's sort of why this way is backwards. Now let's go ahead and do another shift. Let's do shift 1, 2, 3 to the right. So in this case, if we shifted it over 3 to the right, we might have the graph look something like that. If we moved it over to the right, what is the equation for f of x? Well, the root equation is y equals x squared, so this is something squared, and this is going to be x. We moved it over 3, so we're going to have 3 over here, but if we move it to the right, then it's going to be minus. So for horizontal shifting, what we have is, if we have our function y equals f of x, the horizontal shift becomes y is equal to the quantity, or excuse me, f of the quantity x minus h, and that means we're going to shift it over. If we're subtracting, we're going to shift it to the right. If we have y is equal to f of x plus h, it's a shift to the left. So if it's minus, it's to the right. If it's plus, it's to the left. And this is, of course, assuming that our h is positive. So now we know what happens if we wanted to have a vertical shift or a horizontal shift. We started off with some sort of function, and I'm just going to keep using y equals x squared for these videos. Y equals x squared. What happens if we wanted to shift this to the left, 1, 2, 3, and down 2, 1, 2? We wanted that to be our new vertex. So if the graph, the parabola, looks something like that. Moved over the first step, left 3, and 2, we're going to go down by 2. What do? Well, we start off with our original function. F of x is x squared. So if we're going to go left by 3, left by 3, what does that mean? If we're going to go left, then that's going to be, our function is going to look like this. F of x is equal to, left deals with what's inside or what's happening to the x. So we're going left by 3, x and 3, and to the left, do we add or subtract? Remember, it's the opposite way, so if we're going to the left, we're actually going to add 3. So this is going to be x plus 3 quantity squared. Now the next step, if we go down by 2, going down, we just tack it onto the end. Since it's down, it's going to be a negative. So that becomes f of x is equal to x plus 3 squared. Down by 2, we subtract 2. So this is the new equation for our parabola that was shifted to the left and then down. So now we can do a combination of things. Instead of just going up and down, left or right, we can do up and down and left or right. In the first video, we covered shifting horizontally and vertically. Now we're going to look at what happens if we stretch or compress a graph. So we write our graph, x and y, and then we do our standard parabola, and that's f of x is equal to x squared. Now what happens if we had a parabola that looked something like that? What we started off with, say a value right here, so whatever this f of x value is, and it goes all the way up here. So maybe this is something, well, this distance and this distance becomes, I don't know, maybe about 4 times as high. So what was this distance? Now, to get up here, it's about 4 times that height. And we can look through all of these y values, and whatever this distance is, maybe 4 times would be way up here. So we could say that this graph is f of x, it's about 4 times as steep, so that's just going to be 4 times x squared, since it's 4 times as steep. So if the graph from out here becomes steeper, we're multiplying it by an integer, by a number. 2 times as steep, 3 times as steep, 4 times as steep, or you could even do it by 1.5, but as long as the number is greater than 1, that means it's becoming steeper. So up here we have something that's getting steeper. The opposite of steep, maybe we would call it flatter. So if the graph were getting flatter and it looks like this, this also is what a parabola. This is also a parabola, but it's much flatter. And so again, we'll take a look at this point. This is about half the height that we have here. This distance is half of what the original f of x was. So maybe this equation, f of x, is just going to be 1/2 times x squared. And so that's because it's getting flatter. Now the book uses the words compressing or stretching. It compresses, so this line, if we compress it together, it gets pushed into something like this. I like to say steeper instead of compress. And then if we took our parabola and we stretched it across, it would be something like that. That would be if it's stretched. Or I like to say it's flatter. If you look at the book, they'll say the words compressing and stretching. but I prefer steeper and flatter. What they say for stretching, I say steeper. So that some people might not make sense. But so for the book, what they say is a stretch, I say is steeper. And then what they say is compressing, I say is flatter. So I like my terminology better than the books. And so we're going to go with that for the rest of this lesson. So if it gets steeper or flatter, or if we're looking with the book terminology, compressing versus stretching, then what we have is, if we look at our equation, y is equal to, now in this case we had the coefficient in front, some coefficient a times f of x. If a is greater than 1, then that means it's going to be steeper. So if a is greater than 1, it's steeper. And then if a is going to be between 0 and 1, so say like 1/2 or 1/4, so if a is between 0 and 1, that's going to be a flatter graph. Now let's say we had a function that does something like this. We'll say this is our function f of x. Now this time we'll use the book terminology. So if we were to compress this in the horizontal direction, meaning we're going to push inwards on the sides, what would happen? Well, if we were to compress it, we pushed inwards, this graph would have the same height, but it would finish a lot quicker. It'd be compressed. So maybe in this case we're doing it about half as fast. And so if we did that, that graph would look something like this. F of 2 times x. And that's because we had a horizontal compression. If we were to stretch it, and let's go ahead, let's move this up a little bit. And that one too. So if we were to then stretch it, and so we would have something that looks like this, it would take twice as long to complete. And I kind of ran out of space here, but if that were the case, our function would look like f of 1/2 times x. So if it's going to be stretched and it's going to take twice the space, it's going to be 1/2 of that. If it's compressed, it's 2 times x. So putting this together in terms of the horizontal stretching or compressing, if our function looks like y equals f of a times x, if a is greater than 1, we have a horizontal compression. If a is between 0 and 1, so 0 is less than a is less than 1, we have a horizontal stretch. Now let's go ahead and take a look at a different kind of function. Let's look at a function like that. What is that function? This is f of x is equal to, this is the square root function, so the square root of x. If we were to flip this function over the x-axis, what would that look like? Well, if we flipped it over, it would look something like that. When we flip it, what happens to the y value? What was once a positive value is now negative. So what was once positive is now negative. So our function f of x becomes negative square root of x. So if we have something that is a reflection about the y-axis, what your function will look like is going to be y is equal to the negative of f of x. That's what would happen if it was a reflection about the y-axis. And now the last piece that we'll talk about in this chapter, in chapter 1, is what happens, and again, we'll start again with the equation f of x is equal to the square root of x. So we have this function. What happens if we reflect it about the y-axis? If it's reflected about the y-axis, it looks like that. So we have the graph that looks like that. But what happens to the x value? Say we have an x value out here, it goes up there. Well, if we reflected it, it goes back here. And what's the x value there? It's the negative x value. So if it's reflected about that axis, our function f of x is actually equal to the square root of negative x. So if x was, say, 5 out here, well, that corresponding value would be negative 5. And so if we have a reflection about the y-axis, then our function is going to become y is equal to f of negative x. In section 2.1, we're going to talk about properties of linear functions and linear models. Well, first of all, what is a linear function? A linear function is exactly what it might sound like, a line. When we talk about lines, we talk about straight lines, lines that look like this. If something does this, we say that's a curve, not a line. So what's the equation of a linear function? Well, the equation of the linear function will look something like this. F of x is equal to m times x plus b. And you may recall, this is what we call slope-intercept form, where m is our slope and b is our y-intercept. If something is not linear, if a function is not linear, we say it's nonlinear. So two things are either linear or nonlinear. Now, so if linear equations are of the form y equals mx plus b, where m is the slope and b is the y-intercept, then we can look at any type of linear line. We might have a line that says y is equal to 2x plus 1. That means it has a slope of 2, so our slope will denote it with m. Slope is rise over run. And how far does it go up? It goes 2 over 1, because 2 over 1 simplifies to just 2. And it intercepts, the y-intercept is equal to 1. So this should just be a review, but we'll go ahead and just do an example. So if the intercept is 1, it's going to cross the axis right here. And if the slope is 2 over 1, that means we go up 2, 1, 2, and then we go over 1. And we'll be right there. we know that this is a positive number, and positive numbers, the slope goes this way. If it were negative, a negative slope is in this direction. So in addition to going up and to the right, we can go down and to the left. So let's go ahead and go down and to the left. Down to the left 1. And so we're at this point right here. And now we have 3 points, and we can connect the dots. And we see this is a straight line, crossing the y-axis right here at the point 1, and with a slope of 2, up 2 over 1. If you might recall, in section 1.3, we discussed the average rate of change. Back then, we said that the average rate of change was the change in y over the change in x. So then we gave the formula that the average rate of change between 2 points A and B was f of b minus f of a divided by b minus a. And this worked for any curve, linear or nonlinear. But what is the change in y over the change in x? The change in y over the change in x is really just the slope. The slope of a line, where you have the line is y is equal to mx plus b. The slope is the average rate of change. So if you see a question that says find the slope or find the average rate of change, and it's a linear line, you just find the slope. So let's go through some few examples. If we have f of x is equal to negative 5/2 x plus 6, g of x is equal to 13x minus 4, and h of x is equal to 2 over 7x minus 3 over 4, what is the average rate of change for each of the functions? Well, the average rate of change is just the slope. So these are the average rate of change. Negative 5/2 for our first function, 13 for our second function, and 2 over 7 for our last function. It's just the average rate of change is just the slope. Now again, y equals mx plus b. This is the form of a linear equation. We can tell if this equation is increasing, so it is increasing if our slope m is a positive number. It is decreasing if our slope m is negative. So we covered when m is greater than 0 and when m is less than 0, but what about if m is equal to 0? In that case, it's a constant. So it's constant if m is equal to 0. So let's zoom out. So what does an increasing function look like? Increasing function basically is something that goes like that. And that's what a positive slope looks like. If we had a decreasing function or a negative slope, it looks like this. And then last but not least, if we have a constant slope, the line is just straight horizontal. Excuse me, if we have a constant function, it's just straight horizontal. So let's go ahead and take a look at some examples. F of x is equal to 2/3 x plus 1. 2/3 is greater than 0. That implies it's an increasing function. So if we're to plot that, it has an intercept of 1 and it rises up 2 and over 3. And so that is an increasing function. If g of x is negative x plus 2, the coefficient in front of x is really a negative 1 times x. So negative 1 is less than 0, which means it's decreasing. So if we were to plot that, our intercept is at 2, and it decreases. So it goes down 1 to the left 1, down 1 to the left 1, and there you go. That function is decreasing. And let's do the last one. If h of x is 0 times x plus 4, well, 0 times x is just 0, so h of x is just 4. H of x is just a constant number. That's why it gets its name. So if we were to plot 4, 1, 2, 3, 4, no matter what x is, our y value, or our h of x, is always going to be 4. And so that's the constant. Now if you're asked to find the zero of a linear function, so if we had something like f of x is equal to x plus 5, finding the zero basically means we set our f of x equal to 0. So if we were to find the zero of f of x, we just set 0 instead of f of x equals x plus 5, and then we solve for x. So we subtract 5 from both sides, and we get that x is equal to negative 5. If you were asked to find the zero of g of x is equal to 3x minus 12, instead of writing g of x, we write 0, so 0 is equal to 3x minus 12, and then we add 12 to both sides, so we get 12 is equal to 3x, divide both sides by 3, and we get x is 12 over 3, which is 4. Alright, now we have a word problem. Don't freak out. Let's just look at this word problem and see what is it really asking for. So we have a moving truck company, and it rents their trucks for one day, and for each day it charges $39 per day. Plus, you have an additional 11 cents per mile. Write an equation that relates the cost and the miles driven. So let's figure out what we have. So it's going to cost us $39 regardless of miles. So if we drove 0 miles, if x were 0, it would still cost us $39. So we can write it as our cost is going to equal $39. It's always going to be $39. Now look at the 11 cents per mile. So if we drove it 1 mile, and x is what we're going to call our miles. So if x is 1, or 1 mile, how much do we add on? We add on 11 cents for that. So if x equals 1, we drove 1 mile, the cost would be $39 plus 11 cents. What about if we drove 2 miles? Well, the cost would be $39 plus, now instead of 11 cents, we drove 2 miles. So 11 cents for the first mile plus 11 cents for the second mile, or 11 cents times 2. What about if we drove 3 miles? Well, the cost would be 39 to begin with, plus how many miles? 11 cents for the first, plus another 11, plus another 11. So this is going to be 11 cents times 3. Do we notice a pattern? Well, this first one is 11 times 1. So if we drove 1 mile, it's 11 times 1. 2 miles, 11 times 2. 3 miles, 11 times 3. What about if we drove just some arbitrary x miles? Well, this would be 39 plus 11 times x. And what do you know? This right here is an equation. It's a linear equation. Now, usually we see the x term first, so if I rewrote this, our cost, which is really a function of x, is equal to 0.11x plus 39. So that's all it is. That's how we find what the equation is. The second part of this question is saying, what is the cost of writing this if we drive 210 miles? So that is saying, if x equals 210, what is our cost? Well, we plug in 210 for x. So this is going to be c of 210 is equal to 0.11 times 210 plus 39. And we find that this is equal to $62.1 or $62.10. So let's try another word problem. So let's say we call an Uber, and the Uber will charge you $2.70 as soon as you get inside the car. And then for each mile you drive, it'll be $1.60 charge. So what is the cost of this trip? So the cost, say we drove 0 miles. So if we drove 0 miles, the cost is just going to be $2.70. If we drove 1 mile, how much is the cost? Well, we get $2.70 just by getting the car, and we drove 1 mile. So this is going to be plus $1.60. If we drive 2 miles, the cost will then be, we start out with $2.70, and then we drive 2 miles, so $1.60 for each mile, so $1.60 times 2. Because you drove, for the first mile it's $1.60, for the second mile you get another $1.60, so $1.60 times 2. 3 miles, it would be $2.70, plus $1.60 times 3, and I think you might now see a pattern. This up here, we could rewrite it as 160 times 1. In fact, up here, 160 times 0, any number times 0 is just 0. So we could have written it as 160 times 0, because 160 times 0 is just 0, which would just been 270. So if you notice the pattern, we start off, if we drove 0 miles, it's going to be 160 times 0. If we drove 1 mile, 160 times 1, 2 miles, 160 times 2, 3 miles, 160 times 3, and so if we drove x miles, it would be $2.70 plus 160 times x miles. Or if you wanted to write it the other way around, 160x plus 270, you're welcome to do that. But because addition is commutative, meaning 1 plus 2 is the same as 2 plus 1, this answer is fine. And finally, if we had another word problem, to convert a temperature from degrees Celsius to degrees Fahrenheit, you multiply the temperature in degrees Celsius by 1.8 and then add 32. So say if we wanted to find what the function f is for the Fahrenheit, what we're going to do is we're going to multiply our Celsius by 1.8 and then we add 32. And that's our function for f. But what about if I took this one step further and then I added onto this question, what is the temperature in Fahrenheit if it is, let's just say, maybe 35 degrees Celsius. 35 degrees Celsius, that seems kind of cool. If you're used to only the English system and not the metric, what is 35 degrees Celsius in Fahrenheit? Well, that is 1.8 times our Celsius, so times 35 plus 32. Now if you did this on a calculator, you would find that this is equal to 95 degrees Fahrenheit. So that's pretty hot. Even though 35 degrees Celsius doesn't seem like a lot, it ends up being 95 Fahrenheit. In section 2.2, we're going to build linear models from data. And so here we're going to use data in all of these problems. So you might see an example that deals with the weekly hours that a child watches TV. So this is the weekly watching of TV in hours versus their grade in school. And this is their percentage. And so if they watch 6 hours of TV per week, their grade would be 92.5. If they watch 12 hours of TV per week, their grade is going to be 87.5. If they watch 18 hours of TV per week, their grade will be 72.5. If they watch 24 hours of TV per week, their grade would be 77.5. If they watch 30 hours of TV per week, their grade would be 62.5. And finally, if they watch 36 hours of TV per week, their grade would be 57.5. So now that we have the data, what can we do with it? Well, we can do what's called a scatter diagram, and basically that is where you plot the different points. So one axis, maybe we'll say our x-axis, let's call that the weekly TV. And let's call our vertical axis, our y-axis, the grade. Okay, so our grade is going to be in percent, and then our weekly TV is going to be in hours. And we'll go ahead and tick off. We'll do increments of 6. So that'd be 6, 12, 18, 24, 30, and 36. Then our vertical axis will be the grade, and we'll make them increments of 10. So we get 10, 20, 30, 40, 50, and we'll write 50 right here, 60, 70, 80, 90, and then 100 up there. We'll graph the first point, which is when 6 is our x-axis, or the weekly TV, the grade is going to be 92. So at 6, we're going to be somewhere, maybe around there. When we're at 12, so we look at the next point, when we're at 12, we're at 87.5. And 12, 87.5 right here, kind of just eyeballing that. When we're at 18, we're at 72.5. So this is what, 50, 60, 70 would be over here. So 72.5. And that goes right about here. Then we look at the next point. When we're at 18, or excuse me, when we're at 24, we're at 77.5. So at 24, 77.5 would be maybe a little bit higher, like right about here. And then we look at when we're at 30, we're at 62.5. So we look for 30, and it's 50, 60, so it would be somewhere about here. And the last point would be 36 and 57.5. And so that might be something like that. So now we graphed all the different points. What can this graph tell us? Well, looking at it, we see that it sort of forms a line, kind of like a straight line. Now it's not exact because this is coming from data. So data is not always exact, so it's not going to be a perfectly straight line. As you see, if we were to connect the dots, it kind of has that zigzag. And right here, if you notice between these 2 points, 18 hours has a lower score than 24 hours. So that just might have been that the kids that were sampled did particularly well or poor. But that's what happens when you have data. It's not always the nicest. But in general, when you look overall, you see there's this trend going down like that. And the trend looks like a straight line. What can we infer from this? We can infer that the more hours you watch TV, that the lower your score may be. So those that have a lot of TV watching, their scores are pretty low. Those with fewer TV watching, their scores are pretty high. Now the last example, when we plotted our points, the points looked something like this. And we saw that it was kind of like a clear line. Now, if we had another plot that did like that, we could also have plots that look like that with different points. Both of these are examples of linear relations. Now you might see other types of plots, such as something like this. And you can see that sort of looks like a parabola. So that would be an example of a nonlinear relation. And nonlinear relations take different forms. So we might have something else that looks like this. And we can see from here, it's starting to come down and then it levels off like that. So this is not a straight line, it's not linear, but you can see that there's a pattern. So it'd be nonlinear. Another example might look something like this. And from there, that kind of looks like another parabola, just upside down, the opposite of this. So if you can sort of get an idea of what the graphs look like, you can tell it has some sort of function, and this would be a nonlinear function. Now the last type that we would deal with, I need a little bit more space, and so if we had something like this, and we go ahead and plot the points, and the points look like that, well, what kind of function is that? Well, it's definitely not linear. You can't really tell if there's a straight line anywhere, and it's not really, there's not a clear picture of what's going on. So this is what we would say has no relation, or just none. And, excuse me, this right here above should be written, instead of non-relation, that should be non-linear relation. Non-linear relation, linear relations, and none. Now remember our first example in this video where we looked at weekly TV watching versus the grades, and we saw that there's some sort of linear function or some sort of linear relation that we got. Now you can actually figure out an equation to estimate this linear function. Your calculator has a function that does that, but I'm not going to go into detail since people may have different calculators. But I would suggest you go to the NoAL Center and look for help, or check out online and see how to do this. But if you can find it, it will make your life a lot easier. For those that don't have graphing calculators, how can you estimate what this line looks like? Well, the easiest way to do that is just pick 2 points, and 2 points that might represent what the line actually could be. So let's say that the line might be something like that. So now we have a line. How do you figure out the equation from the line? Well, to find the equation of a line, you need 2 things. You need the slope, and you need either an intercept, or you need a slope and a point. So let's go ahead and pick 2 points out from this line. I'm going to say the point right here, and I'm going to write it in blue. This point, that might be the point, let's say 6, 100. Even though our data said the point 6 corresponded with 92.5, that could have just been a fluke. So we're going to say 6, 100. And maybe the point down here, let's say that would be on this line, that point would be 36, 50. So again, 36 corresponded with 57.5, but we're just going to call it 50. So we have 2 points. What's the equation of that line? Let me give myself some space to work with, and let's do that. We have two points. The equation of the line, first of all, let's find out the slope, m. The equation of this line, m, is equal to the change in your y coordinates divided by the change in the x coordinates. So that would be 50 minus 100 divided by 36 minus 6. 50 minus 100 is negative 50. 36 minus 6 is 30. So negative 50 over 30, which simplifies to negative 5 over 3, or let's write it as a decimal, negative 1.67, or we'll approximate because it goes on forever. So our slope would be that. Now we have a slope. If we use the point slope formula, mainly y minus y1, and let's pick 100. So y minus 100 is equal to negative 1.67 times the quantity x minus 6. That's the equation for your line, this right here. That's the equation that would give us the line. Now if you wanted to write it in slope-intercept form, so let's move that a little bit smaller. If we wanted to write it in slope-intercept form, we would add 100 to both sides. So adding 100 to both sides, we get y is equal to negative 1.67x. Negative 1.67 times 6 is 10, positive 10. So this is plus 10. So this right side so far, negative 1.67 times x is negative 1.67x. Negative 1.67 times negative 6 is positive 10, and then if we added 100, then we get plus 100. And so therefore, writing it all out, we get y is equal to negative 1.67x plus 110. Now, this is not exact because we're sort of eyeballing it and guessing, but if you're to do it on your calculator, or if you're to plug it in on some computer software, what you would actually get for the best fit line is the following. You would get y is equal to negative 1.67x plus 99.5. Now that was pretty close to what we got. We got the slope right. Oh, the decimal point didn't really appear. We got the slope right, negative 1.67, but the values that we picked maybe weren't the best. And that might just be because of the drawing. If you can do it on your graphing calculator, I highly encourage you to learn how, because solving it will be fairly simple. You just know how to plug in the values and out pops the equation, and the equation is the most accurate. But if you don't have a graphing calculator or you don't know how to do it, you can pick two arbitrary points that look like it might be on the line and then estimate it from there. But from there, to do that, you have to first draw the line, figure out the points, figure out the slope, and then figure out the equation. But it's up to you. In section 2.3, we're going to talk about quadratic functions and their zeros. Well, what is a quadratic function? quadratic function is a function, say f of x, and it's of the form a times x squared plus b times x plus c, where a, b, and c are real numbers. So you might see something, for example, g of x might be negative 2x squared plus 3x minus 12. It has the form some number times x squared plus some number times x, and then plus just a constant. So this is what a quadratic function is. A quadratic equation is something of this form. Ax squared plus bx plus c equals 0. So it's basically if we set the quadratic function equal to 0. So this is what we call a quadratic equation. And we're going to discuss this and how to solve for the zeros. What do we mean by solving for zeros? We mean what are the x values that when we plug it into this equation, it equals 0. If we have a function, let's say this quadratic function is f of x is equal to x squared plus 2x minus 8. What are the zeros of this function? The zero of this function is when we set the function x squared plus 2x minus 8 equal to 0. When this happens, when it's equal to 0, that's equivalent as saying when the y value is 0. And so on a graph, if we look at a graph, when is the y value 0? The y value is 0 when it crosses the x-axis. So the x-intercept is equivalent to finding the 0. So how do we solve this? Well, one way is take a look at this. Can we factor it? Well, let's try. Let's see. What times what would give us x squared? So that would just be x and x. Now, what would give us negative 8? The values that would give us negative 8 are the products are going to be 1 and negative 8, negative 1 and 8, 2 and 4, negative 2 and 4, and then 2 and negative 4. Of these, what 2 would give us a sum of positive 2? Because we're trying to find the sum of positive 2. Well, the only one that would do that is right there. So we have x minus 2 times x plus 4. So now we factored into two terms. This times this term. Now if these two terms are being multiplied, if something is multiplied by something else and it equals 0, in order for something to be 0, one of the terms must be 0. For example, what I mean by that is you do 8 times 0 is 0. Anything times 0 will give us 0. You could have 1 million, and if you multiply that by 0, it's still going to be 0. So when we have two things multiplied by each other equals 0, then either what we're going to have is this first term, x minus 2 equals 0, or the second term, x plus 4 equals 0. So if x plus 2 equals 0 over here on the left, what do? Well, to solve for x, we add 2 to both sides, and we get x is equal to 2. And for the next one, if x plus 4 equals 0, to solve for x, we subtract 4, and we get x is equal to negative 4. And these are the two zeros of this quadratic function. So x equals 2 and x equals negative 4, those represent, if you recall, what we said over here is that the zeros are also the intercept. And so, let's zoom out a little bit. I graphed it right here, and we can see that the graph of this equation crosses the x-axis right here when x is -4, and again here when x is 2. So if you can graph the equation, you'll also find a way of figuring out what the zeros are. Now we said a quadratic function is of the form f of x is equal to ax squared plus bx plus c, where a, b, and c can be any integers. Well, what about if b, or actually in fact any real numbers? So they don't have to be integers, they could be like 1/2. But what if b is 0? So if b equals 0, then what do we have? F of x is just simply ax squared plus c. So let's do this with some actual numbers. So if we have a function, say g of x, and that function g of x is equal to x squared minus 49, how do you solve for the zeros? Well, to solve for the zeros, we set that equal to 0. And now we add plus 49 to both sides. And so we get x squared is equal to 49. Now to solve for x, we take the square root. So we take the square root of both sides, so we get x is equal to, the square root of 49 is going to be 7. But remember, when we take the square root, we have two answers, plus or minus. So x is either equal to positive 7 or negative 7. In fact, when dealing with quadratic equations, since we have a square over here, we can have up to two different answers. And again, we'll check this, and let's go ahead and take a look at the graph. And so we said that it crosses the axis at positive 7 and negative 7, and you can see right here, if I zoom out, it does cross twice. The two intercepts are going to be at negative 7 and positive 7. So it checks out. We could have graphed it, and this would have found the x-intercepts are the same as the zeros. Now if we had another function, let's say h of x is equal to the quantity x minus 6 squared minus 25, how would you solve for the zeros? Well, we first set it equal to 0. And now we'll add 25 to both sides. So this is starting off to be similar to the last problem because we didn't have any of the x terms. All we had was just a squared. So I moved 25 over, and what's left is x minus 6 quantity squared is equal to 25. Now what do I do from here? Well, we have 25 can be written as 5 squared. And so now we have a squared equals a squared, which was just like the other side, or the other slide. And so when we take the square root, take the square root of both sides, we get x minus 6 is equal to the square root of 25, which is 5. But remember, it's going to be plus or minus 5. So we have two different things to do. We have x minus 6 is equal to 5, or x minus 6 is equal to negative 5. So we'll work with this left one first. We add 6 to both sides. We end up with x is equal to 11. Or if we add 6 to this side, we end up with x is equal to 1. And so these are our two zeros of this function. Now what about if we had a function of this form? F of x is equal to x squared minus 2x minus 15. If you're to solve for the zeros of this, well, we set this equal to 0, how can you solve that? Now one way of solving this particular equation is through factoring. But if you don't know how to do factoring, or you forget, or you just can't see it right now, that's alright, because there are other ways of solving this. Sometimes you can't even factor it. So what can we do? Well, in this case, what we can do is complete the square. So first of all, let me add 15 to both sides. So we have x squared minus 2x equals 15. To complete the square, what we do is we look at this number, negative 2. So we take negative 2, and what do we do with that? Well, we divide that number by 2. So negative 2 divided by 2 gives us negative 1. Now we take that negative 1 and we square it. And negative 1 squared is just positive 1. So we're going to add that number, positive 1, to both the left and the right sides. 15 plus 1 is 16. Now if you look at the left, what is this? This is a perfect square. And that perfect square is x minus 1 quantity squared. Remember, this negative 1 came from this negative 1 that we got right here. So we have, let me write it out where we have a little bit more space. So we had x minus 1 quantity squared is equal to 16. Well, how do we solve that? Just like the last slide, notice 16 is a perfect square. 16 is 4 squared. So we can take the square root of both sides, and we'll get x minus 1 is equal to, the square root of 16 is 4. But since we take the square root, it's plus or minus 4. So I'll take the square root up here, just so you can see that. So we have x minus 1 is 4, or x minus 1 is negative 4. So if we add 1 to both sides over here, we get x is equal to 5. If we add 1 to over here, we get x is equal to negative 3. And these are our two zeros of the function. But let's take a moment and write it another way. So we had x squared minus 2x minus 15 equals to 0. So that's what we started with. Can we factor this? In fact, in this case we can factor it, so what would it be? What times what gives us negative 15? Well, that'd be negative 15 and 1, 15 and negative 1, and then we get 3 and negative 5, and negative 3, and positive 5. And since we want the sum to be negative 2, that means we get 3 and negative 5. So that would be x plus 3, x minus 5. And if I move up a little bit more so we have space, since we have two things multiplied by each other equaling 0, either the first thing is 0 or the second thing is 0. So we get x is equal to negative 3 or x is equal to 5. Either way, we ended up with the exact same answer as the first way completing the square. Sometimes factoring doesn't work, so another way of solving for the 0 of a quadratic function, and if that quadratic function we're trying to solve for looks like ax squared plus bx plus c equals 0, one way of solving for this is called the quadratic formula. And the quadratic formula says that the 0 of this, or the answer to this equation, will be x is equal to negative b plus or minus the square root of the quantity b squared minus 4 times a times c, and all of this will be divided by 2 times a. Now, one way of memorizing this, and this is the way that I use, is to think about it as the tune of row, row, row your boat. So I think of this as x equals negative b plus or minus the square root b squared minus 4ac divided by 2a. But notice here that we have a square root. What happens when we have a square root? Well, when there's a square root, the thing inside must always be greater than 0. And so we must have that b squared minus 4ac has to be greater than or equal to 0. If it were less than 0, that means there would be no real solutions. So let's do an example. So if we had a function, let's say g of x is equal to x squared minus 3x minus 15, what is the zeros of this function? So we go ahead and set it equal to 0, and remember, the quadratic formula said that if we had something that was of the form ax squared plus bx plus c equals 0, what we get is our solution is x is equal to negative b plus or minus the square root b squared minus 4ac all divided by 2a. So in this case, what is our a? Well, our a is really 1. It's 1 times x squared. Our b is going to be negative 3, and our c is negative 15. So, using the quadratic formula, x is equal to negative b, and I'll just write it over here on the side. So a is 1, b is negative 3, and c is negative 15. What's negative b? Well, regular b is negative 3. So negative b is negative 3. So negative b is just positive 3. And then we have plus or minus the square root. B squared is going to be negative 3 squared. So negative 3 squared is 9 minus 4 times a. A was 1, so that's 4 times 1 times c, which is negative 15. This is all going to be divided by 2 times a, and a is 1. So let's simplify this. So this is equal to 3 plus or minus 9. Now we have a minus, and then there's a negative over here. So minus and negative give us a plus. So that's going to be 9 plus 4 times 15. What is 4 times 15? Well, 4 times 15 is 60. All divided by 2. So we have, this is 3 plus or minus the square root of 9 plus 60 is 69 divided by 2. And that's your answer. You can leave your answer in plus or minus. If you don't like the plus or minus, you could write it in two forms. You could write it as x is 3 plus the square root of 69 over 2, or 3 minus the square root of 69 over 2. But that's your answer. Let's do another example. So we have a function f of x is equal to 4x squared minus 25x minus 21. And we're trying to solve for the 0, so we're going to set that equal to 0. The quadratic formula, if you recall, was x is equal to negative b plus or minus the square root b squared minus 4ac divided by 2a. So let's write this up. X is equal to, what are our a, b, and c? A is 4, b would be negative 25, and c would be negative 21. So we get x is equal to negative b, so negative 25 is positive 25, plus or minus the square root of 25 squared minus 4 times a, so 4 times 4 times c times negative 21 divided by 2 times a, so 2 times 4. So let's simplify this a little bit more. we have 25 plus or minus the square root. 25 squared is 625. And then we have a minus, a negative. So minus and negatives gives us a plus. Now 4 times 4 times 21 is equal to 336. This is going to be all divided by 8, because 2 times 4 is 8. So we get this is going to be 25 plus or minus the square root of 625 plus 336 is equal to 961, all divided by 8. Well, now look at this square root of 961. The square root of 961 is actually equal to 31. So this simplifies to 25 plus or minus 31 divided by 8. So move this up a little bit. And so we get two possible solutions. 25 plus 31 over 8, or 25 minus 31 divided by 8. What's 25 plus 31? That'd be 56 divided by 8. And 56 divided by 8 is 7. And then 25 minus 31 would give us negative 6. So this equals negative 6 divided by 8. And negative 6 over 8 is, that can be simplified into negative 3 over 4. So here we have the solutions to the equation. Now if we had two functions, f of x is equal to 6x plus 7, and we had g of x is equal to x squared, where do these two functions intersect? Well, if we were to graph this, we'll plot the first equation. F of x has an intercept at 7, so we go ahead 1, 2, 3, 4, 5, 6, 7. There's our intercept, and it has a slope of 6, or 6 over 1. So we go ahead and plot that, so we go 1, 2, 3, 4, 5, 6, and we go over 1. We could also go down 6 and back 1. And so what we get is a line that looks like that. Now the other equation, g of x equals x squared, well, that is a parabola. So the parabola looks something like this. And so we see it crosses right here at one point, but it keeps going up, and well, if we extended it, it'll probably cross somewhere way up there. So there's 2 points. But what is this first point? What is that intersection? Well, we can figure that out. So how do we solve this equation? Well, what we do is we set them equal to each other. We set 6x plus 7 equal to x squared. And now how do we solve this? We subtract 6x from both sides. So we get 7 is equal to x squared minus 6x, and then I subtract 7. So we get 0 is equal to x squared minus 6x minus 7. So I put everything all on one side of the equation, and now this looks like what we've seen before. How can we solve this? Well, first of all, let me make this a little bit smaller. One way is using the quadratic formula, but a lot of people don't like that. Well, what's a simple way? Maybe we can factor this. So what times what would give us negative 7? That would be 1 and negative 7, or negative 1 and positive 7. Of these two choices, which would give us negative 6 when we add them together? Well, that's the first one. So that's just going to be x plus 1 times x minus 7. So we either have x plus 1 equals 0, or x minus 7 equals 0. And finally, if we subtract 1 from both sides, we get that x is -1. Or if we add 7 to both sides, we get x is 7. So these are our two answers. X is 7 or x is -1. And that's the value where they cross. In section 2.4, we're going to discuss properties of quadratic functions. You might want to take a minute to refresh yourself from section 1.5, where we looked at transformations of graphs. Now the function y equals x squared, if you graphed it, it looks like that. Now what happens if we were to translate this graph and we shifted it over 1 to the left and 1 down? So we take the equation y equals x squared and we move it 1 to the left, and when we move it 1 to the left, that makes it y is equal to the quantity x minus 1 squared, and if we move it 1 down, that's going to be minus 1. So that's the equation for this graph. Well, we can write this equation in another form. If we expand the x minus 1 squared, and so you can use the formula for a square, or if we want to write it as the quantity x minus 1 times x minus 1 and minus 1, and we FOIL it, we get x squared minus x minus another x, so minus 2x plus 1, because -1 times -1 is plus 1, minus 1. So this simplifies to x squared minus 2x. So now, if you're given something that starts off with x squared minus 2x, how do you know that it looks like this graph? It turns out that there's a formula. So, if we had some function f of x is equal to a times x squared plus b times x plus c, what we can do is we can rewrite it, and if we were to rewrite it in this form of a times the quantity x minus some number, and we'll call that number h, quantity squared, plus another number, and we'll call that k. Well, this h, that determines if it goes left or right, and k determines if it goes up and down. Well, how do you find what h is, and how do you find what k is? Well, it turns out there's a formula, and the formula says that h is going to equal negative b divided by 2 times a. And it's going to say that k is equal to 4 times a times c minus b squared divided by 4 times a. So now let's go ahead and take a look at that example that we had. If we had f of x was equal to x squared minus 2x. Well, what are the values that we have here? A is equal to 1 because the coefficient in front of the x squared is 1. The next number, b, is equal to -2 because that's the coefficient in front of the x. And finally, c is 0. There's no number that comes after it. So this is what a, b, and c is. So we can figure out what h would be. H is negative b over 2a. So that's going to be negative. B is -2, so we get a negative divided by 2 times a, which is 2 times 1. So we end up with negative negative 2, which is just positive 2, divided by 2. So we get h is 1. And then we'll move up a little bit more. And how do we find k? So we'll find k, which is 4 times a times c. So 4 times 1 times 0 minus b squared. b is negative 2, so minus negative 2 quantity squared, all divided by 4 times 1. And so this is equal to, well, 0 times anything is 0, so that's gone. And then negative 2 squared is going to be positive 4, but there's a negative in front, so that's just going to be negative 4 divided by 4. So we get k is negative 1. So if we were to rewrite it in terms of what we're given, we see that from this equation up here, our f of x could also be written, so our f of x is right here, could also be written as a, which is 1, times the quantity x minus h. H is 1 from down here, so that would be x minus 1 quantity squared plus k. In this case, k is negative 1, so plus a negative 1. So given this, we're able to plot it. But in this case, we actually knew what it was where we started with, so which was up here. So now we figured out how we can go from having an equation that looks like that into something that we actually know how to plot. So the key here is learning what this formula is for h and what the formula is for k. Now when you have a parabola, it looks like this, the very bottom of the parabola is something that we call a vertex. So if the equation of this parabola is f of x is equal to a times x squared plus bx plus c, the x coordinate for the vertex will be, so the x value of the vertex is negative b over 2a. Now the y value for the vertex, well, if you do want to remember the formula, the y value is what we talked about in the last slide, and that's going to be 4ac minus b squared divided by 2a. But that's pretty hard to remember. That's a lot. One way to think about it is if you already know what the x value is, and you know that this is the function, the y value can also be thought of as just putting in f of whatever our x is. So f of negative b divided by 2a. That's another way of figuring out what the y value is of the vertex. Once we know what the vertex is, then we know where the graph goes. We know if it moves left or right or up or down. And finally, there's something that's called an axis of symmetry. The axis of symmetry is what goes right up over here, and we looked at parabolas, and sometimes a parabola is reflected over the y-axis, but not all the time. It is symmetrical about something, and that's what we call this axis of symmetry. So what goes to the right of the axis will be mirrored right here. And how do we figure out what the axis of symmetry is? Well, it's just a straight vertical line at the x value for the vertex. So the axis of symmetry is given by this point. X is equal to negative b divided by 2a. And the vertex is right here, given with the point negative b divided by 2a, comma, f of negative b divided by 2a. So let's do an example. If we have f of x is equal to x squared minus 10x, what is the vertex? Well, to find the x value of the vertex, we're going to take negative b divided by 2a. But what's b and what's a? Well, in this case, a is the coefficient in front of x squared, so a is equal to 1. And b is the coefficient in front of x, so b is negative 10. So the x value for the vertex is going to be negative b, which is negative 10, over 2 times a, or 2 times 1. So negative 10 is positive 10 divided by 2, or 5. And what's the y value? Well, the y value is just f of 5. We plug in 5 for x. So that's 5 squared minus 10 times 5, which is 25 minus 50, or negative 25. So the vertex is equal to 5 comma negative 25. So right now we already know what the graph might look like with an idea of the vertex. What about the axis of symmetry? Well, the axis of symmetry is given by the line x is equal to whatever the x value is for the vertex, which is 5. So let's take a look at what the plot looks like. So we have a parabola, and it's facing up, and we know it faces up because the coefficient in front of the x squared is positive. If the coefficient is positive, then it faces up. If the coefficient is negative, it faces down. So it faces up, and then it has, we looked at the vertex. The vertex is going to be 5, negative 25, so we go across 5 and down negative 25, and that's the vertex. And it points up, and if we look at the axis of symmetry, the vertical line where x is equal to 5, it's reflected over that axis of symmetry. Let's take a look at another example. If we had the function g of x is equal to negative x squared plus 14x plus 2. Well, what way is this parabola facing, up or down? The negative over here means it's going to be facing down, but we need to figure out where the vertex is. So to find the vertex, the x value, we know the x value is negative b over 2a. What are the values for a, b, and c? Well, a, since it's dealing with the x squared, so the value for a is negative 1. The value for b is in front of the x, which is 14. And then the value for c is 2. So the x value of the vertex is going to be negative b, so negative 14, divided by 2 times a, 2 times negative 1. And we have a negative over negative, they cancel, so we're just left with 7 for the x value. The y value of the vertex is going to be g evaluated at 7. So that's going to be negative of 7 squared plus 14 times 7 plus 2. So we have negative 49 plus 98 plus 2, which is 51. So our vertex is going to be 7, 51. And then the axis of symmetry is going to be the line x is equal to 7. You can take a look at this graph again. And so, looking here, we see that it's facing down because it was a negative. The axis of symmetry goes straight up and down here when at the value when x is 7. And the vertex is 7, comma, and some very big number, which I will assume is 51. Now we're going to look at graphing a quadratic function. So if we had a function f of x is equal to x squared plus 2x minus 3, how do we graph this? Well, first let's find the vertex. You know the x value of the vertex is going to be negative b over 2a. In this case, b is 2, so this is negative of 2 divided by 2a, so 2 times 1. So this is just negative 1. The y value of the vertex is going to be f of negative 1. So that's going to be negative 1 squared plus 2 times negative 1 minus 3. Negative 1 squared is 1. 2 times negative 1 is negative 2 minus 3. And so we get that is equal to negative 4. So the vertex is going to be negative 1, negative 4. And the axis of symmetry is going to be x is equal to negative 1. That's just the values. Now to plot, let's try to figure out some points to plot it. Well, if we can figure out what the intercepts are, then we'll have some extra points. So we'll take a look at, first of all, the y-intercept. Remember, the y-intercept, if you think about a graph where it crosses the y-axis, the value of x is going to be 0. So the y-intercept, that's when x is 0, so we plug in 0 for our function. F of 0 is equal to 0 squared plus 2 times 0 minus 3. So the y-intercept is going to be negative 3. So that's for y-intercept. And then the x-intercept is when y is 0. It crosses the x-axis when the value of y is 0. And so, if you recall from section 2.3, the x-intercept is just the value of the 0. So we're going to set 0 equal to our function x squared plus 2x minus 3. And let's solve for that. Oops. So how can we figure out what that 0 is? Well, this looks like we can factor this function, so what can this be factored into? So we have x and x, and we have negative 3. So we're going to have 3 and 1, and which one would be positive and which one would be minus? Well, it'd be positive for the 3, and then minus for the 1. So we get that x plus 3 equals 0, or x minus 1 equals 0. And so we get, now move up a little bit more, we get x is negative 3, or x is equal to 1. And these are the x-intercepts. So go ahead and plotting this all together, what we have is we have the vertex, which we see is negative 1, negative 4. We have the y-intercept. It'll cross the y-axis at negative 3. And then it also crosses the x-axis at negative 3 and at 1. So if we connect these dots like that, and we know the axis of symmetry is this, so whatever goes on the right side of this axis of symmetry gets reflected on the left side. So that's one way of plotting a function. Notice that this crosses the x-axis 2 times. Sometimes we can get different numbers of x-intercepts. So if we had a parabola that looks like this, it has 2 x-intercepts. But if we have a parabola that crosses right here, there's only 1 x-intercept. And finally, if we have a parabola that does that, we have 0 x-intercepts. And that's basically, we just took the parabola, this parabola, and if we moved it up, we only got 1, and if we moved it up even higher, we got 0. How do we know when we have 0, 1, or 2 x-intercepts? We look at what's called the discriminant. The discriminant, if we have an equation y is equal to ax squared plus bx plus c, the discriminant is b squared minus 4ac. Now b squared minus 4ac, that might be familiar if you remember the quadratic formula. The quadratic formula was x is equal to negative b plus or minus the square root of b squared minus 4ac all divided by 2a. This right here, that's the discriminant. But let's move back up to here. So if the discriminant is greater than 0, so b squared minus 4ac, if that is greater than 0, then we get 2 roots, where it crosses the axis 2 times. If the discriminant equals 0, b squared minus 4ac equals 0, you only get 1. So you get, it crosses 2 times over here, so you get 2 intercepts. Here you just get 1 intercept. And then finally, if b squared minus 4ac is less than 0, you get none. And think about this. Let's go back so we can see this equation. If b squared minus 4ac is less than 0 in this case, when can the square root be less than 0? Never. You cannot take the square root being less than 0, and that's why it's none. And we'll look at this case. If the square root equals 0, so if it's 0 in here, we get negative b plus or minus 0, which is just negative b divided by 2a. Negative b over 2a is just one answer, not 2. And then, if it is greater than 0, then we'll have negative b plus the square root, or negative b minus the square root, all divided by 2a. So the previous example that we did, the function that we used was f of x is equal to x squared plus 2x minus 3. What's the discriminant of this? Well, the discriminant, if we say a is equal to 1, b is equal to 2, and c is negative 3. The discriminant is going to be b squared, which is 2 squared, minus 4, and I'm reading off of here what the discriminant is, 4 times a, 4 times 1, times c, times negative 3. So this is going to be 4 minus 4 times negative 3, which is negative 12. 4 minus negative 12 is 4 plus 12, or 16. 16 is greater than 0, so we know when it's greater than 0, we're going to have 2 x-intercepts, which is what we saw in the graph in the previous slide. So if you want to plot a quadratic function of this form, ax squared plus bx plus c, there are 2 methods we can do. So the first method, we'll do step 1. What we do is we complete the square. And when we complete the square, we'll have it written so it's of the form f of x is equal to a times the quantity x minus h squared plus k. And now when it's of this form, we can tell based off of h and k how it moves. And so we can use, change back to my pen, we can use transformations. So that's one method of plotting. The second method is as follows. So first step, we'll determine if the graph is up versus down. And you can tell if it goes up or down based off of a. So if a is greater than 0, it goes up. If a is less than 0, it's down. So now we know if it goes up or down. Step 2 says we'll find the vertex. And the vertex was negative b over 2a, and then f of whatever that value is, f of negative b over 2a. In addition to finding the vertex, we'll also find the axis of symmetry. The axis of symmetry is the equation x is equal to negative b over 2a. So after we find the vertex and the axis of symmetry, we'll determine the intercepts. Both intercepts, both x and y intercepts. The y-intercept, that's just plugging in 0 for x, so that would be f of 0. The x-intercept, that is when we find the zeros of the function. Now, when we do this and we find the x-intercepts, we need to figure out how many x-intercepts there are. And so we'll first of all look at the discriminant. So if b squared minus 4ac is greater than 0, then we have 2 x-intercepts. If b squared minus 4ac equals 0, then we have 1 x-intercept. And last, if b squared minus 4ac is negative, then there are none. There are no x-intercepts. And lastly, we use all these points that we have, the vertex, the intercepts, and plot the graph. If we had a graph that looks something like this, and we said it crossed the y-axis, so the y-intercept is 0, 3, and the vertex is given by the point 1, 4, can you find the equation of the line? Well, the equation of the line can be given in the form f of x is equal to a times the quantity x minus h squared plus k. What is h and k? Well, h and k is the vertex. So we know this is a times x minus 1 quantity squared plus 4. So we have everything but a. How do we figure out a? Well, we use this information and we know a point, and we can plug that point in. So if our y value is 3, that would be what our f of x is. So 3 is equal to a times, if x is 0, we plug in 0 minus 1 squared plus 4. So we get 3 is equal to a times 0 minus 1 squared is just 1. So that's just a plus 4. If I subtract 4 from both sides, we get a is negative 1. And so therefore our function is now going to be f of x is equal to negative the quantity x minus h squared plus 4. So you can figure out the equation of a line, or excuse me, of a quadratic function based off of knowing just the vertex and a point. And finally, if we have quadratic functions, they either look something like this or something like that. If we have a quadratic function that looks like this first one right here, we know that this point right there, that would be the minimum. And if we had a function like that, on the right, the top point would be the maximum. Well, both of these points happen to be the vertex. So the vertex will either be a max or a min. It all depends on which way it's facing. It's a max if it faces down, and when it faces down, recall a is negative, where that a was coming from f of x, equals ax squared plus bx plus c, or it's a min if our a is greater than 0. So it's min if it faces upwards, it's a max if it faces downwards. The last thing we'll discuss is word problems. Now, let's look at this word problem. The manufacturer of a company found that the revenue, R, is this equation right here. R of P is equal to negative 5P squared plus 1,830 times P, where P is the unit price per dollar, or unit price in dollars. What price would maximize the revenue, and what is the maximum revenue? Now what this is doing, this is actually has a lot of words, but we'll break it down and see what's actually going on. What we want to do is we want to maximize the revenue. The key word is maximize. When you read word problems and you find maximum or minimum, so maximize something or minimize something, maybe you might see something that would be minimize the cost or maximize the revenue. That's what you're looking for, the maximum or minimum. And well, look at this equation. This is p squared. So that's going to be a parabola. It's either going to look something like this or something like that. If it's this first one, this would have a maximum. If it's the second one, it would have a minimum. Well, look at the equation right here. The equation says negative 5p squared. And if you recall, if our function is f of x is ax squared plus bx plus c, if a is greater than 0, then that means it moves up like this, and we have a min. If a is less than 0, the parabola goes down, which means that we have a max. And the max and min are at these points right here. And what are these points called? These points, if you remember, are the vertex. So we'll look and make sure that this equation is one that has a max. Well, since it has a negative in front, yes, it does have a max, and that max would be at the vertex. So we'll find that. To find the vertex, we find the x value is going to be negative b divided by 2a. So if our equation is r of p is equal to negative 5 p squared plus 1830 times p, this negative 5 right here, that's our A, and then our B is equal to 1830. So we go ahead and plug those values in, and so our x value for the vertex is going to be negative b, so negative 1830 divided by 2 times negative 5. So this is negative 1830 divided by negative 10, or just 183. And what was 183? That was like our x coordinate, but in this case, instead of it being x, instead of using x and y, we're using p and r. So 183 actually represents our p value, which is dollars. So $183 per unit. At that price, it would maximize the revenue. Well, what is the revenue? Well, we just plug that back into our equation. So the y value of the vertex is going to be r evaluated at 183, which is negative 5 times 183 squared plus 1830 times 183. And so this becomes 167,445. And that is the revenue we make if we set the price of each unit at $183. Well, let's take a look at this on the graph. So what that graph would look like would be something like this. Now these values are going to be very, very high. That value up there, that y value is 1,670, 445, and the x value across is 183. So if you looked on your calculator, you would have to zoom out a lot in order to see this. But if you did, you could see that the maximum of this, or the vertex, the very height of the parabola, is going to be, this point is 183, 167, 445. So let's do another example. The cost of running a shop that sells bentos is given by this function. C of x is 2 times x squared minus 26x plus 500. This is where x is the number of bentos sold. And that could be because if you sell just a little bit of bentos, it might cost a lot just to operate. If you sell too many bentos, then you might have to start getting new machines and so forth. So there's sort of a perfect number that you want to minimize the cost. So what do we need to do? Well, if we were to graph this, we see that this is a parabola. We see this is x squared, and the 2 in front is positive. So that means the parabola faces up like that, which means that we have a minimum value. So if we sell too many units, so if x gets too big, they'll need to buy more equipment to keep up with the demand. They might have to hire more people, and that costs more money. So if it gets too big, it costs a lot. But if you don't sell enough, say you only sell 5, you're not going to be able to make ends meet. So there's sort of a little perfect number right here that would tell us. And that number is the vertex. Because this is a minimum. We want to find the minimum or the lowest cost. So what we do is we're given the function c of x is 2x squared minus 26x plus 500. Well, 2 is our a value, negative 26 is our b, and 500 is our c. So the x value for the vertex is going to be, x value is going to be negative b over 2a. Since b is negative 26, negative b is negative negative 26, or positive 26 divided by 2 times a, 2 times 2. So this is 26 over 4. Simplify a little bit more, that'd be 13 over 2. So the y value of the vertex, we just plug it in. So the y value, plug it into c of 13 over 2. And what is 13 over 2? 13 over 2, well, that represents the number of bentos sold. So number of bentos. So if they sell, that's just over 6, between 6 and 7 bentos, that's where they'll maximize their profit, or excuse me, minimize their cost. So to find the actual cost, we plug in 13 over 2. So that's going to be, and I'll write it on the next line, 2 times 13 over 2 squared minus 26 times 13 over 2 plus 500. And this equals 415.5. But if we round it, that's about $416. So all we did was we took the equation that we're given and we found the vertex to find either the maximum or the minimum. The x value would give us the number of units and the y value would give us the cost. Just like in the previous problem, the y value gave us the revenue and we wanted to maximize that. In this case, we want to minimize cost. In section 2.5, we're going to talk about inequalities involving quadratic functions. Earlier, we were able to solve a quadratic function in the form x squared minus 4x minus 21 equals 0. But what if it weren't equal 0? Instead, if it were, let's say, less than or equal to 0, how would we solve that? Well, like before, we can factor it. We could first pretend that it's equal to 0. So how would we find the zeros? We factored it. We could use a quadratic formula or whatever method you want, but factoring is the easiest. So we factor x, and what values would go here? Well, either 21 and 1 or 3 and 7. So you can look at 21 and 1. Let's say 21 and negative 1, negative 21 and 1, 3 and negative 7, or negative 3 and positive 7. And since the sum here is negative 4, it's going to be 3 and negative 7. So x plus 3, x minus 7. And if we thought of it as equal to 0, this is important, we just think of it as equal to 0 for now. We get the two answers, either x plus 3 equals 0, or x minus 7 equals 0. So therefore we get x is equal to negative 3, or x is positive 7. These are our two possible answers. But now we're looking for a range. We're not looking when it's equal to, but we want to find a range. So this is where I like to write it out on a number line. And we have negative 3 over here. Then we have 7 over here. So we have some range that's going to be less than negative 3, a range that's between negative 3 and 7, and then a range that's greater than that. So for the range to the left, we just picked some point. You can pick any point you want. If you want to pick negative 3.1, that's to the left of here. If you want to pick negative 20, that's to the left. But I'm going to keep it simple, and I'm just going to pick negative 4. Now I want to pick a number in here, and again, you can pick anything you want. You can pick negative 2.99, you can pick 6.99, but an easy number to work with is 0. And then to the right of 7, I'll also pick 8. So these numbers represent numbers that are in their respective areas. So now I'm going to move this up a little bit. And now we want x squared minus 4x minus 21 to be less than or equal to 0. So x squared minus 4x minus 21, we want that to be less than or equal to 0. So what we're going to do is we're going to pick numbers that we are testing into that equation. So we're going to put negative 4 squared minus 4 times negative 4 minus 21, and what do we get? Well, negative 4 squared is positive 16. Negative 4 times negative 4 is also positive 16. So 16 plus 16 is 32. 32 minus 21 is 11. So this is equal to 11. But we wanted it to be less than or equal to 0, what we said over here. 11 is not less than or equal to 0. So since it doesn't satisfy that it's less than or equal to 0, what we're going to do is we're going to cross off that region. So I'm just going to put a big X right here. And now we test the next point. We test the next region, which is this one right here. So our value we're using is 0. So we're going to test 0. 0 squared minus 4 times 0 minus 21 is equal to, well, that's negative 21. And negative 21 is in fact less than or equal to 0. So what we want to do is we're going to use this region right here in the middle. And last, we check out the last point. So we check out the last region, this region over here, and the value we're going to use is 8. Move up just a little bit more. So we put 8 in, we get 8 squared minus 4 times 8 minus 21, and that is equal to 11, and 11 is not less than or equal to 0. So again, we're going to say that this region is not included. So the only region that we have is this this middle region. And what's the range in that middle region? It's going to be between negative 3 and 7. But remember, since we have less than or equal to, since it could include the points, it could equal negative 3 or 7. So this is our answer. This is what we get. Let's try another example. Say we have x squared plus 3x is greater than negative 2. What do we do here? Well, first of all, let's move everything to the left side, everything on one side of the inequality. So we add plus 2. So we end up with, our equation is x squared plus 3x plus 2 is greater than 0. And we can think of it, again, as the equal sign. So x squared plus 3x plus 2 equals 0. How do we find the zeros? Well, again, we can factor. So we get x and x. And what make 2? 2 and 1, or negative 2 and negative 1. But because it's 3, it's going to be x plus 1, x plus 2. So therefore, from here we get that x is equal to negative 1, or x is equal to negative 2. Those are the 2 points that we have. Again, we'll go ahead and we'll draw the number line, and we're going to have negative 2 and negative 1. We'll pick a point in each region. So to the left of negative 2, we'll call negative 3. Between negative 1 and negative 2, well, that'll be negative 1.5. And then last, to the right of negative 1, I'm just going to pick 0. These are just numbers that I picked, but if you wanted to pick something else, if you wanted to pick negative 10 to be on the left here, you want to pick negative 1.75, that's fine. If you wanted to pick 15 on the right, by all means go ahead. These numbers I've picked are easier and they're not as large. So what do? We go ahead and we're going to test it into the inequality. We have x squared plus 3x plus 2. We want that to be greater than 0. We go ahead and test the first region, negative 3. So we get negative 3 squared plus 3 times negative 3 plus 2. Well, negative 3 squared is 9. 3 times negative 3 is negative 9, so that's 0 plus 2, which is equal to 2. And in fact, 2 is greater than 0. So that's what we wanted. So we have this first region right here. This first region is included. And then we go ahead and look at our next point. So the next point is negative 1.5. Negative 1.5 squared plus 3 times negative 1.5 plus 2, which equals negative 0.25. Negative 0.25 is not greater than 0. So we know it's not going to be in that region. So we cross that middle region off. And so we'll now look at the last point that we have. The last point is the right region, and our point is 0. Do 0 squared plus 3 times 0 plus 2, and we get 2. And we know that 2 is greater than 0, so we're good. So we go ahead and we say that that last region right here is a go. We now have two regions. We have the region on the right and the region on the left. The region on the left, this is when x is less than negative 2. And then the region on the right is when x is greater than negative 1. So these are our two answers. X is less than negative 2 or greater than negative 1. Unlike the last problem we did, it's not greater than or equal to or less than or equal to. Because notice, our original equation just had a strictly greater than sign. So we'll do a word problem, and this says a rocket is propelled upwards from the ground. The height in meters after t seconds is given by this equation for h. During what time interval will the rocket be higher than 117.6 meters? Basically what this is saying is the height of the rocket looks something like this, where this axis is our time, and then the vertical axis is the height. We want to know when the height will be above 117.6 meters. So when are we going to be in this region over here? Well, we have one inequality, or we have one equation. We want that, which is negative 9.8 t squared plus 78.4 t. We want that to be greater than 117.6. And now we can solve this. So how do we do this? Well, first of all, we can move 117.6 to the other side. So we'll subtract 117.6, subtract 117.6, and what are we left with? We're left with negative 9.8 t squared plus 78.4 t minus 117.6, and that's greater than 0. But how do we solve something like this? Let me move this up. These numbers are not something that we're familiar with. So let's get rid of these coefficients, or of these fractions. What I'm going to do is I'm going to divide everything by negative 9.8. Divide by negative 9.8. Divide by negative 9.8. And then I'm also going to divide 0 by negative 9.8. Remember, when we divide by a negative number, this sign changes. So instead of being greater than, it changes to less than. So don't forget when we divide by a negative. So what do we get? Negative 9.8 divided by negative 9.8, we're left with t squared. 78.4 divided by negative 9.8, we're left with negative 8t. And then negative 117.6 divided by negative 9.8, we're left with positive 12. And now this is less than 0. So let's factor this. This is something that we know how to factor. And so I'm just going to go ahead and just write equals 0. What do we have? This is going to be 12. What makes 12? Well, 2 and 6, negative 2, negative 6, 3 and 4, and negative 3, negative 4. And since we want, and also 1 and 12 and negative 1, negative 12. Since we want negative 8, we're going to use t minus 2 and t minus 6. That means t is equal to 2 or t is equal to 6. Scooting this down, we're going to go ahead and write our number line, which is 2 and 6. Points we'll pick, I'm going to pick 0 because 0 is an easy number to work with. I'll pick 3. 3 is small, a smaller number is nicer, especially when we start to square. And then I'm going to pick 7. Now I'm going to go ahead and plug this into the inequality. T squared minus 8t plus 12 is less than 0. The first point is 0, we test. So 0 squared minus 8 times 0 plus 12, that's just equal to 12. And 12 is not less than 0. So I'm go ahead and mark off no to this left region right here. And then the next region we look at, the middle one, we pick 3. So we get 3 squared minus 8 times 3 plus 12, and that's equal to negative 3. And negative 3 is in fact less than 0, so we're good for that region, and we'll go ahead and say yes to there. The last point we pick is going to be 7, so we put 7 in, 7 squared minus 8 times 7 plus 12 equals 5, but 5 is not less than 0, and therefore that last region is not included. We now know that we're in the middle, and our solution is going to be, our time will be between 2 and 6. So between 2 and 6 seconds. In section 2.8, we'll discuss equations and inequalities involving the absolute value function. What is an absolute value? Well, an absolute value technically means the distance from a point to the center, or the origin, on a number line. So if this is 0, and we had some point 1, 2, 3, 4, we had a point negative 4, the absolute value of negative 4, how far is that from the origin? So we'd go 1, 2, 3, 4. The absolute value of negative 4 is 4. Similarly, if we went positive 4, 1, 2, 3, 4, the absolute value of positive 4 has a distance from the origin, 1, 2, 3, and 4. But notice what we have here. If the number inside is greater than 0, the absolute value is just going to be that number. In this case, if the number is less than 0, it's going to be the opposite of that number. So if we had something like this, the absolute value of u were equal to a if u is positive, then the absolute value of u is just equal to a, what we had here. The absolute value of 4 is just 4. So if the absolute value of u, or excuse me, if u is negative, then the absolute value of u, when we said it's negative right here, it's the opposite sign. So what's the opposite sign of a? Well, the opposite sign of positive a is negative a. This is one way of thinking about absolute values. But as long as you remember that when it's negative, it's always going to be the opposite. It's going to be positive, and if it's positive, it's the same as positive. Now, if we had the absolute value of x is equal to 3, what is x? Well, x could equal 3, but if it's negative, we could also say that x could equal negative 3. So when we take the absolute value, it's really just taking the plus or minus, the positive 3 and the negative 3. How about this example? The absolute value of x minus 3 plus 6 equal to 13. What's x? Well, the first thing we'll do is we'll subtract 6 from both sides. What's left on the left is just the absolute value of x minus 3. And what's left on the right? Well, 13 minus 6, which is 7. And now this looks like what we did on the top. Similarly, so we'd have x minus 3 equals 7, or x minus 3 is negative 7. And we can solve this like we normally do. We add 3 to both sides, and we get x is equal to 7 plus 3, which is 10. Or, if we add 3 to both sides here, we get x is equal to negative 7 plus 3 is negative 4. What about if we had this? Solve for x when we have 1/3 times x minus 7 is equal to 4. What do we do? Well, with the absolute value, we always write it as the number inside the absolute value equals 4, or the number inside the absolute value is negative 4. And then, in this case, we'll add 7 to both sides. We add 7 to both sides. And what do we have? We have 1/3 x is equal to 7 plus 4 is 11, or 1/3 x is equal to negative 4 plus 7 is positive 3. And how do we solve for x now? Well, we have 1/3 times x. We could either divide by 1/3, but I don't like to divide by a fraction. What I prefer to do is multiply both sides by 3. When we multiply both sides by 3, 3 times 1/3 cancels out, and it's just left with 1. We'll do the same thing on the right side. We multiply both sides by 3. So we're left with x is equal to 33, or x is equal to 9. Now what about if we have an inequality? If we had something that looked like this. The absolute value of u is less than a. Well, if we had something that looks like that, it's actually going to be, this is the same as u is going to be between negative a and positive a. And the same would hold for it, instead of using less than, it's less than or equal to. That's going to be the same as u is bounded between negative a and positive a. However, if absolute value of u is greater than a, that's the same as saying u is less than negative a, or u is greater than positive a. Similarly, if we had u is greater than or equal to a, it's the same as saying u is less than or equal to negative a, or u is greater than or equal to positive a. So notice what we have here. if we start off with the absolute value being less than some number, that means it's going to be small. It's kind of bounded. So it's bounded in between these two numbers. But if the absolute value is greater than, then that means it goes either less than negative a all the way to negative infinity, or greater than positive a all the way towards positive infinity. We'll take a look at some examples. What if we had the absolute value of x is less than 2? Well, remember, it's less than, the absolute value is less than something, which means that it's going to be between negative 2 and positive 2. And how do we graph that? Well, on the graph, we'll write it as, start at 0, we get negative 2, 2. If it's between these two numbers, we'd write it between negative 2 and 2. I like to write with the open circles, but if you have to write it the other way like the book does, you can write it with the parentheses. There are two ways of writing it, graphing it. This is one way of expressing it with the less than or equal to signs, and another way of writing it is if we were to write it in interval notation. Negative 2, comma, 2. Another example that we'll do is, what is x if we have the absolute value of x is greater than or equal to 3? Remember, this is greater than or equal to. So if it's greater than or equal to, we're going to have two different solutions. We'll have either x is less than or equal to negative 3, or x is greater than or equal to positive 3. And that's your answer. If we were to write this in interval notation, what does it mean when it's less than or equal to negative 3? Well, that goes all the way to negative infinity. So it starts at negative infinity to negative 3, and since it includes negative 3, we'll include it like that, union, and we start from 3 to positive infinity. So we go from 3, parenthesis, to infinity. We use this shape, the bracket, because it includes the point, and we use the parenthesis because it doesn't. Now on the number line, what does this look like? If we're starting from negative 3 to negative infinity, or being less than or equal to negative 3, if we do it with the dots, we go from negative 3 all the way to the left. And then we go from positive 3 all the way to the right. Or, if we want to write it the other way, with the brackets, we go from negative 3 all the way to the left, and then we go from positive 3 all the way to the right. These are 4 different ways of expressing your answer to that. What about if we have the absolute value of x plus 2 is less than 16? The key here is saying that it's less than. What happens when it's less than? If it's less than, then we know that negative 16 is less than whatever's inside the absolute value. So that would be x plus 2, and that's also going to be less than positive 16. Now, what do? We want to find x, so we subtract 2. A common mistake here is to forget to subtract 2 from everything. If we're going to subtract 2 from this middle, we subtract 2 from the left, we also subtract 2 from the right. Negative 16 minus 2 is negative 18. So we get negative 18 is less than x, is less than 16 minus 2 is 14. And so that's your answer. X is going to be between negative 18 and 14. If we wrote it in interval notation, it would be negative 18 with parentheses, comma, 14 with another parenthesis. What about on the number line? Well, these numbers are kind of big, so I'm just going to go all the way up to negative 18, maybe 0, and then we'll go up to positive 14. Since it doesn't include the point, we have the open circle, and does that. Or, if we prefer to write it with a parenthesis, we'll do that, and it connects in between. So the key in these problems is to recognize, is it going to be less than or equal to or greater than or equal to, and you have to decide which one it is, and your answers will be according. But other than that, inequalities will be treated the same steps that we did with the equalities when it's equal to. Mainly, we would subtract 2 from both sides and we'd solve for x. In Chapter 3, we'll discuss polynomial and rational functions. The first section, 3.1, will go over polynomial functions and models. We'll begin with what is a polynomial function. A polynomial function is some function written f of x is equal to some coefficient or some number. It could be positive or negative. Some number, we'll say a sub n, times x to some power n. That could be like x squared, x to the fourth, but x to some power. And then we have another coefficient, a sub n minus 1. This is just something different than a sub n, times x to another power, and it goes down. So if the first one was x squared, this is x to the 1. Or if this is x to the 5th, this could be x to the 4th. And it would go carry on until we get near the end, when we have a sub 1, x just to the power of 1, plus just another constant, a sub 0. Where the coefficients can really be any real number. And then the powers, that's x to the n, x to the n minus 1, well, the powers have to be integers that are not negative. So non-negative integers. And that means they could be 0, they could be 1, 2, 3, and so forth. So examples of a polynomial function will be something like this. F of x is equal to 5x cubed minus 3x. All the powers of x are 3 and 1, and 3 and 1, they're integers that are greater than or equal to 0. So, since that's fine, that's all that we really care about. These coefficients, they can be anything. They can be positive, negative, they could be integers, or they could be rational numbers, or even irrational. For example, we could have another function, say g of x. This could be maybe pi times x squared minus 3.2 x plus 40. Well, the powers of x are going to be x squared, x to the 1, and it's okay to have just a constant number at the end, like we had over here. So, since the powers of x are real numbers, or excuse me, integers, 1, 2, then it's a polynomial. Even though the coefficient is pi, or even a decimal, 3.2 and 40. So this is a polynomial. If we had another function, we'll say h of x, and that's equal to, let's say 3/2 minus 1/3 x. Is this a rational function? Yeah, it is. Normally we're used to writing the highest power first. In this case, the highest power is last, but the highest power is x to the 1, so that's fine. But our coefficients are just fractions, and that's okay. So yes, this is another example of a polynomial function. Now the degree of each polynomial is basically just the number of its highest coefficient, or the highest power. The highest power of f in this case is 3. So this is a degree of 3. In our case of g, the highest power of x is x squared. So this was a function of degree 2. And in this last example, h, the polynomial is x. And so is really x to the 1, so that's a degree 1. Now what about if we had a function f of x is equal to 1 plus 9 over x? Well, what's the power of x? We could rewrite this as 1 plus 9 times x to the negative 1. Anything to the negative 1 power is the same as saying 1 over x. Is this a polynomial? Remember, a polynomial has to have powers that are greater than or equal to 0. Since there's a negative in the power, this is not a polynomial function. Let's take a look at another example. G of x. If g of x were to equal x to the 5/4 minus x to the 6 plus 1, is this a polynomial? Well, 5/4 is not an integer, so this is also not a polynomial. What about if we had h of x equal to 2 times x minus 1 to the 11th power times x plus 1 to the 9th power? Is this a polynomial? Well, think about it. Yes, if it's all raised to a positive integer power, this is. What's the degree? Well, from right here, the degree, we only care about the highest power. So the highest power that's going to come out of this would be x to the 11. What's the highest power out of this next term? That would be x to the 9. What happens when we multiply x to the 11 times x to the 9? We add the powers. That would be 11 plus 9. So that would be x to the 20th. Alright, well, how about this? What about if we had a function f of x is equal to 1 minus x to the 5th divided by 7? Is this a polynomial? Well, if we were to rewrite this as 1 over 7, since we're divided by 7, we'll divide each of the terms in the numerator. So 1 over 7 minus x to the 5th over 7. Is this a polynomial? In fact, it is. We have our constant term with no x, that's okay. And then the power with x is x to the 5th. So yes, it's a polynomial function. And what's the degree of this polynomial? It's 5. So this is a polynomial whose degree is 5. Now recall, the graph of a function of y equals x squared, that's a parabola. And the parabola looks something like this. Alright, it touches 2 points, or it touches 3 points, 0, 0, negative 1, comma 1, and 1, comma 1. What about the graph of y equals x to the 4th? Well, y equals x to the 4th is actually going to touch the same 3 points, but it's going to be steeper. It's going to be steeper on the endpoints and then flatter on the bottom. And the same thing as our powers get higher and higher. If we had y equals x to the 6th, it's going to touch the same points, but at the ends it's going to be steeper and then flatter on the bottom. Something like that. So in general, if you had y is equal to x to some even power, you're going to have these 3 points. It will always touch these 3 points if it's just y equals x to an even power. You'll touch those 3 points, and it'll get steeper. It'll get steeper when n increases. The steepness will increase. So when n increases, it'll get steeper for the values when n is going to be greater than 1 or less than -1. So when it's basically outside of these 2 points, it gets steeper and steeper the higher your exponent goes. But if you're between these two values, instead of getting steeper, it'll be flatter when it's between -1 and 1. And sorry, I forgot to clarify, where n, that's really what we're talking about as the power. Now what about if we had y equals x cubed? What does that look like? Well, that looks something like this, where we have the point 0, 0, point right here, 1, 1, and then a point back here, -1, -1. What about if it becomes y equals x to the 5th? We're going to have these same 3 points, but it gets steeper when it's outside of -1 and 1, but when it's between the 2 points, it gets flatter. And so if we were to increase it even more, let's say y equals x to the 7, we'd be even steeper and flatter. So if it's y equals x to some odd power, we're going to have 3 points, -1, -1, 0, 0, and 1, 1, but as the power increases, it gets steeper when x is less than -1 or when x is greater than 1, or flatter when x is between the two. If we had a function f of x is equal to, let's say, x minus 3 times x plus 2 times x minus 1, the zeros of this function, we know that the zeros are x is going to be 3, -2, and +1. So these are the 3 zeros. This is a function. If we multiply it out, it has a degree equal to 3. So in this case, we went from given a function f of x to figuring out what the roots are and that we know the degree. Can we work the other way? Let's say we had a function, or say we had a function whose zeros are the following. X equals 5, x equals -4, and x equals 2. And that this function has a degree equal to 3. Well, what is that function? In this first case, if 3 was a root, we wrote it as x minus 3. So we can write this function g of x as, in this, since we have 5, this would be x minus 5. When -2 was a root, we wrote it as x plus 2. So if -4 is a root, this would be x, well, we could write it two different ways, minus -4, Or we could write it as, instead of minus and negative, x plus 4. And then since 2 is a root, what we wrote over here, when 1 was a root, it was minus 1. We'll do the same thing. So this would be x minus 2. And so here we have three things. We have one term multiplied by another term. That's a function of degree 3, which is what we wanted. So I'll just write this out nicely. X minus 5 times x plus 4 times x minus 2. Now if you wanted, you can multiply this all out and it'll get quite ugly, but you can leave it like this. It's fine to leave your answer in this form. But this here is the equation of the function whose roots, or excuse me, whose zeros are this: 5, negative 4, and 2. And it's a function of degree 3. Now what about if I told you that a function has zeros that are equal to 0, 6, and 5. And this function is degree 3. Well, we just write it, f of x would be x minus whatever the 0 is. So x, in this case, the first 0 is 0, so that's x minus 0 times x minus 6 times x minus 5. And what is this, x minus 0? That's just x, so that's x times x minus 6 times x minus 5. If we had a function g of x equals x squared minus 6x plus 9, well, that's factorable. In fact, this factors into x minus 3 quantity squared. So what are the zeros? We could write this as x minus 3 times x minus 3. The zeros of this are 3 and 3. So really, if you look at this, the only zero is just, this function has a 0 of 3, but what do we know is 3 happens twice. So when it happens twice, we say the 0 is 3 with multiplicity of 2. So 3 is a 0, but it happens twice. And notice that this function has a degree of 2. So if we said that a function has zeros of 3 with multiplicity of 2, another 0 that's negative 3 with multiplicity also of 2, and this function has a degree of 4, what is the function? Well, the function, we'll call it f of x, is going to be, since the first one is 3, it will be x minus 3, but since it has a multiplicity of 2, that would be x minus 3 times x minus 3, or we could just write it as x minus 3 squared. The squared, or the number of times you write it, relates to the multiplicity. And we look at the other one, when negative 3 is a 0, we would write it as x plus 3. And since it has multiplicity of 2, we can write it 2 times x plus 3 times x plus 3. Or we could write it as x plus 3 quantity squared. We said this has a degree of 4, and we can verify this. This squared is x squared, and this squared is x squared. And that would give us x to the 4. Or if we looked here, x would give us x to the 4. Now if we have a function, let's say h of x is equal to the quantity x minus 3 with some multiplicity. Let's say x minus 3 to the power 3. since this is an odd multiplicity, so 3, we're looking at an odd multiplicity, what happens at the point 3? Well, we know at 3 over here, when it's that value, it's a 0. And the 0 is when we have a function and it might cross the x-axis. So all these points, 1, 2, 3, they're all zeros. So the 0 is when it crosses the x-axis. So we know that x equals 3 is a 0. But how does it behave as the 0? If there's an odd multiplicity, it will cross the x-axis. Okay, so if it's odd multiplicity, it crosses the x-axis, like this. These are when it crosses the x-axis. Now I'll go ahead and I'll move up a little bit. If our function, say maybe g of x, is x minus 3 to the power 4, here 4 is a even multiplicity. So if the multiplicity is even, then what happens is that it just touches the axis. Okay, so we know that similarly 3 is a 0, but what happens? What does it mean when it touches the axis? It might come all the way down, touch the axis, and then go back up, or the other way. It might go from the bottom, come up, and touch the axis, and do that. Now, if you had a function that would be a combination, let's say we had a function f of x is x plus 2 squared, and maybe I'll use a different one, x plus 2 to the power 4 times x minus 1. What are the zeros? So the zeros, this is a power of 4, so the zeros are going to be one, and then negative 2, where the negative 2 is a multiplicity of 4. The graph of this looks something like this. It crosses at negative 2 right here, and it also crosses at positive 1 right here, or it touches the axis at negative 2 and positive 1. Since negative 2 is a multiplicity of 4, an even multiplicity, we know it's not going to cross, but it's actually just going to go up and touch it. And at 1, it's an odd multiplicity. Since it's just one time, we know that it crosses like that. And the graph kind of connects like that. That's sort of an idea of what the graph looks like. Now you might wonder, how do I know it's like that as opposed to, let's move this up a little bit, as opposed to, so we know right here it touches and it crosses, so crossing is okay, but do we know it touches from above or below? And that's what you have to figure out. So we look at what this is. What is the highest power? The highest power would be x to the 5th, and it's a positive x to the 5th. What happens if we have x to the 5th as it goes towards negative infinity? So if we look at x to the 5th when it's negative infinity, so a negative number raised to the 5th power actually ends up being a very, very small negative number, something way down here. And so we know from there it goes up, and then it comes back down, and continues to go up. Because you can also look at what happens on the right side. What happens when we have a very, very large number? That large number raised to the fifth power is another large number, and it goes up like that. So we'll do some more examples. If we had a function g of x equals 5 times the quantity x minus 5 times x minus 1 squared. What are the zeros and what are the multiplicities of each zero? And can you figure out if it just touches the x-axis or it crosses the x-axis? So the zeros are going to be, we're looking right here, 5 and 1. So the zeros are going to be 5 and 1. 5, it just has a multiplicity of 1s, because it only has 5 to the power 1. This next one, 1, it's squared. So 1 has a multiplicity of 2 times. Since 5 has a multiplicity of an odd number, what is that? If it's an odd multiplicity, it crosses. So at 5, it crosses. And since 1 has an even multiplicity, with even multiplicity, it just touches. Now when we plot a function, sometimes you see behaviors like this. These points are sometimes what we call turning points. Turning points, you might also know from earlier, we refer to them as the local max or the local min. And they're a turning point because we turn from going down to going up, or from going up and then going down. So these are all turning points. Now if you looked at a parabola, say y is equal to x squared, what does that graph look like? That graph looks like this. In fact, we have just one turning point for something that's x squared. If we were to plot y equals x cubed minus 2x, that graph would look something like this. In which case we would have 2 turning points. But if we plotted another cubic function, y equals x cubed, that graph looks like this. And there's no turning points. Because even though it looks like the cubic function, it doesn't have a max or a min. It just keeps going up and keep going up. So there's no turning points. So even though this is a cubic function, they both are cubic functions, one has 2 and one has none. But we can figure out what's the maximum number of turning points that a function has. So the maximum number of turning points in a function is 1 less than the degree of the function. So we think about it. The degree of this right here is a parabola, it's x squared. So at most, there's 1 turning point. If we looked at the cubic, the most it could have is 2 right here. But it could have 0 turning points. Say we have a function f of x is 5x to the 5th plus 3x to the 4 minus 7x squared plus 21x minus 3. This is a big function, but if you break it down, what is the general thing that's happening? you look at the highest power, the highest degree, which would be here, 5x to the fifth. So the power function of this is what we call y equals 5x to the fifth. It's basically just breaking it down to the largest power. So you might see another function such as g of x is x minus 3 squared. The power function of this is equal to y is equal to x squared, because we could expand this, and if we expanded it, it would be x squared minus 6x plus 9. And the power function gives us an idea of generally what's happening. If it's something that's squared or even, the graph, so if it's an even power, the graph will start at high in the negative, and when x is large, it will end up also high. In the middle, we might have something like this. You might have several turning points, but it'll always end up like that. If it was a negative in front, so say like it was y is equal to negative x to the 6 plus maybe 4x cubed, the negative in front of the 6, or x to the 6, would mean that it would start from a negative and then do something like that. But an even power function means that you're going to start and end on the same side. So even power function, you start and end the same direction. Now so think about a parabola. A parabola is an even power, and you start and end both pointing up or both pointing down. So what about if you have an odd power function? So if you have an odd power function, you can think about it as y equals x cubed. You start at one end and you end up in the other. You start going down, you end going up. You might have some turning points, but it always ends in the opposite direction. So you start and end in opposite directions. And if you forget how it goes, you can always just pick a point. So we can pick a point, say if this were looking at this function, pick a point when x is very large in the negative direction, maybe negative 100. Putting negative 100 in, so we get y is equal to negative of negative 100 to the 6. We're just looking at the power function right here. So negative 100 to the 6, this is a positive number. But since we have the negative in front, it ends up being a negative, and it's a very large number. So it's going to end up being way down here. And similarly, we'll look at this other end. So let's clear that for now. We'll look at the other end, and if x is positive 100, we would look at y is equal to negative of 100 to the 6. This is going to be a very big negative number, going way down here. So we see how it starts and how it ends. You could also test it for a cubic function. So let's do an example. Say we had a function whose zeros are the following: 1, 2, and negative 1, where the negative 1 has a multiplicity of 2. What would the graph look like? Well, what does the function look like to begin with? Well, the function would be f of x is x minus 1 times x plus 2 times x minus a negative 1 or plus 1 squared. That's our function. What's the power function here? So we have x, x, and an x squared. So the power function would be y equals x to the 4. So that means if it's x to the 4, it's either going to start from the same side, maybe with some things in the middle and end from top, or from the bottom and do that. But since this is a positive, there's no negative, we know it's going to be this first one right here. Now this function has a degree of 4. So we know that there's a degree of 4 because we have 1, 2, and then 2 over here. So it's a degree of 4. If it's a degree of 4, what's the maximum number of turning points? So the max number of turning points is going to be 1 less than 4. In this case, that's 3. So we already know that the graph will come up from the top, and it could have at most 3 turning points. So we could have 1, 2, 3, or the only way to end from the top and start from the top and end from the top would be just to have 1 turning point. So these are our 2 options. Now let's take a look at the zeros. I'm going to zoom out for a minute. What are the zeros? The zeros were 1, 2, and negative 1. So let's begin to plot that. So we had a 0 at 1. We had a 0 at 2. Oh, excuse me, this was a mistake. This should have been a negative 2. Excuse me. So we had a 0 at 1, a 0 at 2, and we had a 0 at negative 1. And we know that it comes up this direction, and it ends up in this direction. So we can sort of fill in the blanks, and we know that in order for that to happen, to cover all 3 points, it would be something like that. Now that's a terrible sketch, but it gives you at least some idea of what the graph might look like. Now, let's make this a little bit better. What were the multiplicities of the zeros? So negative 2 was a 0, 1 was a 0, and 2 was a 0, but negative 2 had a 0 of multiplicity 2. What happens when we have an even multiplicity versus an odd multiplicity? Well, an odd multiplicity means it goes through the axis, while an even multiplicity means it just touches. So we'll need to redraw this. So we have negative 2, 1, and 2, and we know it goes up at the endpoints because that's what our root function looks like. But at negative 2, it just touches, so it goes back up. And then at 1 and 2, it crosses, and that's a more accurate drawing of what the graph looks like. It's still a rough sketch, but at least it gives you some idea of how it goes. In section 3.2, we'll discuss the real zeros of a polynomial function. So we begin by assuming if f of x is a polynomial function. So f of x, we'll call that a polynomial function. Then what we have something called a factor theorem. So the factor theorem says that if f of x is a polynomial function, then the quantity x minus c is a factor of f of x. if and only if we have that f of c equals 0. So basically, what we need to do is, if we think that some number c is a 0, all we need to do is plug it in to the equation and see if f of that number is 0. Then we get x minus c is a factor. For example, f of x is equal to x squared minus x minus 6. This can be factored, and it can be factored into x minus 3 times x plus 2. And so we knew by factoring that there are two factors in this. The two factors were going to be x minus 3 was a factor, and x plus 2, that these are both factors. But if we didn't know for sure that they were factors, how could we have tested it? Well, we could test the points 3 and negative 2. Basically, to do that, we need to figure out what is f of 3 and what's f of negative 2. Well, f of 3, plugging it into this equation for f of x, is 3 squared minus 3 minus 6. So that's 9 minus 3 minus 6, which equals 0. Similarly, we can check negative 2. So we get negative 2 quantity squared minus negative 2 minus 6. So negative 2 squared is 4. 4 minus negative 2 is plus 2. So we get 6. 6 minus 6 is 0. So yes, in fact, f of 3 is 0 and f of negative 2 is 0. So we know that x minus 3 and x plus 2 are both factors. What about if we had another polynomial? And this one you might not be able to recognize what the factors are right away, so let's look at this. G of x is equal to x cubed plus 2x squared minus 6x plus 8. Is the quantity x plus 4 a factor? Well, we could try and factor this function g of x and figure it out, but we might not be able to, or it might have a difficulty. So what we can do is we can test if negative 4 can go into it. So we type g of negative 4 and figure that out. If it equals 0, this x plus 4 is a factor. If it's not a factor. So we go ahead and compute negative 4 quantity cubed plus 2 times negative 4 minus 6 times negative 4 plus 8. Negative 4 cubed is equal to negative 64. Oops, and this is a square. This is 2 times negative 4 squared. Negative 4 quantity squared is 16. 16 times 2 is positive 32. And then negative 6 times negative 4 is positive 24. And then we add plus 8. 32 plus 24 plus 8. Well, I know 32 plus 8 is 40. And then 40 plus 24 is 64. So we have negative 64 plus 64. This equals 0. Since g of negative 4 is 0, yes, we know that x plus 4 is a factor. And this works for any example. Let's do another one. If we have a function h of x is equal to x to the 4 plus 6x cubed plus 8x squared plus 44x minus 24, is the quantity x minus 6 a factor? Well, what we need to do is we need to test if h of 6 equals 0. What is h of 6? Okay, and we got 6 because it's the opposite of what that number is right there. So we put 6 in, 6 to the 4, plus 6 times 6 cubed, plus 8 times 6 squared, plus 44 times 6, minus 24. Now, putting this on the calculator, I ended up with this being 3,120. Last time I checked, 3,120 is not equal to 0. So since this is not equal to 0, we can conclude that x minus 6 is not a factor of our function. So all we have to do is plug in the number and see if it equals 0. If it's 0, then that's a factor. If it's not 0, it's not a factor. Now, in a polynomial, the number of real zeros that a function can have cannot be more than the degree of the polynomial. So if we have a polynomial of degree 2, we can have at most 2 zeros. If we have a polynomial of degree 11, we can have at most 11 zeros. We can have less than 11, but the most we could have is 11. Now the next thing we're going to talk about is what we call Descartes' rule of sign. And what Descartes' rule of sign says is if we write out the polynomial in standard form, basically from highest to lowest power. So if we write it out from highest to lowest power, we get that the number of positive real zeros is equal to the number of times the sign changes. If we're looking at our function f of x. Okay. And I'll go ahead and I'll explain this with an example, but let me say the other part of Descartes' rule is that the number of negative real zeros equals the number of times the sign changes if we deal with f of negative x. Okay, so let's go ahead and do an example so that you can understand what I'm talking about. Let's say we had a function f of x is equal to negative 4 times x to the power 9 plus x to the power 5 minus x squared plus 7. First of all, what is the maximum number of zeros that we can have? Well, the maximum number of zeros is the highest power, the degree of the polynomial. So the max zeros is just 9. So we can have at most 9 zeros. Now, using Descartes' rule, we wrote it in order from highest power, 5, to lowest power. So 9, then we had 5, and then 2, and then our constant, where that's really x to the 0 power. How many positive zeros can there be? The number of positive zeros could be, and let's count. So the sign changes from negative, it changes to positive, and then it goes from positive to negative, and then negative to positive. So how many times did we change? Changed once, twice, 3 times. So we could have number of positive zeros, we could have 3. Now, the thing to note for this rule is that this gives us the number of positive zeros or the number of negative zeros, but in addition to that, that's the maximum number, and then we can go down by 2. So we can also count down by 2. Okay. What do I mean by that? If there are 3 potential positive zeros, we could have 3 or 1 positive zero. If there were 8 positive zeros, there could be 8, 6, 4, 2, or 0 positive zeros. So we just count down by 2. Now how do we find the negative zeros? Now for negative zeros, remember we're going to plug in f of negative x. So we do that, we look at what is f of negative x. F of negative x is equal to negative 4 times negative x to the 9 plus negative x to the 5th power. I need a little bit more room, so I'm just going to move that over. Negative x to the 5th power minus negative x squared plus 7. I need a little bit more room. Plus 7. Well, what is this? What is negative x to the 9th power? Negative x to the 9th power is a negative number. So we have a negative number times negative 4, which ends up giving us a positive number. So we get 4x to the 9. And then we have plus negative x to the 5. Negative x to the 5 is a negative number because it's raised to an odd power. So that's minus x to the 5. And then minus an negative x squared, which ends up just being minus x squared plus 7. Now we're going to go ahead and do the same steps. And we say, how many times does it change from positive to negative? It's positive right here, so it goes once to negative, but it stays negative, so it doesn't change here. And it goes from negative to positive, so it changes once right here and then twice. So the number of potential negative zeros is 2. Or if there's not 2, it could be 0. We count it down by 2. So let's do another example. If we have a function g of x is equal to x to the 5th minus 3x to the 4 minus 13x cubed plus 30x squared plus 40x minus 12. What are the maximum number of zeros? Well, the maximum number of zeros is just the degree of the polynomial. So max number of zeros, in this case the degree of polynomial is a degree of 5. Now what about the potential number of positive zeros. Positive zeros. So how many times does it change sign? We start with a positive number. Once became a negative. We still stay negative. It changes again. Still stay positive, and it changes again. So we changed how many times? Once, twice, 3 times. So we have changed 3 times, or we count down by 2. So that'd be 3. So 2 minus 3 would be 1. What about potential number of negative zeros? Well, to do that, we have to check g of negative x. So that would be negative x to the 5th minus 3 times negative x to the 4 minus 13 times negative x cubed plus 30 times negative x squared plus 40 times negative x minus 12. So what do we get? We get negative x quantity raised to the 5th is just a negative of x to the 5th, because it's an odd power, minus negative x to the 4 is positive x to the 4. So this is minus 3x to the 4. Negative x cubed is negative of x cubed. And negative minus a negative gives us a plus 13x cubed plus 30 negative x quantity squared is just x squared. Then we have minus 40x minus 12. So how many times does this change signs? So we have negative, still a negative, okay. It changes once right here, negative to a positive. We're still staying at a positive. If it's a positive and then it changes to a negative, it changes again. And then we still stayed at negative. So how many times did we change? Once, twice. So the potential number of negative zeros is 2, or if we count it down from 2, we could also have gotten 0. Now we'll take a look at something that's called the rational zeros theorem. And by its name, you can probably figure out that it's a theorem that figures out what are potential rational zeros of a function. If we had a function, let's say f of x is some coefficient a and x to some n power plus b x to lower power, maybe we'll say x n minus 1 plus c, and then it gets lower, n minus 2, and we keep getting lower and lower until plus, we'll do a plus up here, plus, let's say, wx squared plus yx plus some z. So it goes all the way from some high power n and a lower power all the way to an x squared, x to the 1, and then finally some constant. So if this is what we have, factors of z of the last number, the constant, divided by factors of our first number, a, those are what we would call potential rational zeros. So these are potential rational zeros of f. Okay. So it's factors of the last term divided by factors of the first term. So let's do an example. If we have a function g of x is equal to 11x to the 4 minus x squared plus 5, what are potential rational zeros? Well, the potential rational zeros would be, what are factors of the last term? Factors of the last term, what makes 5? Well, 5 and 1. So 1 and 5, -1, and -5. What makes the first term? What makes 11? Well, what makes 11 is 1 and 11, -1, and -11. And so what we do is we take the numerator divided by one of these. So we will have 1 over 1 is an option. You can do 1 over 11. We can do 5 over 1, and we can do 5 over 11. And these are all positive. These are all the positives one, but we can also do the negative, and it sometimes is easier. Once we just figure this out, you just add plus or minus, and there you have it. So we can simplify this. 1 over 1 we know is 1. So we have plus or minus 1, plus or minus 1 over 11. 5 over 1 is just 5. So plus or minus 5, and plus or minus 5 over 11. That's all we had to do. Looked at the last term and found what is the multiples of that. What would make 5? And we looked at the first term, 11, and what makes 11. So we can do another example. Here we have a function, h of x is equal to -4x to the 4 plus 3x squared minus 4x plus 6. So we look at the last term, 6. What are the factors of 6? What makes 6? Well, we have plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. Those are all things that make 6. And then we also look at what makes -4. Well, we get plus or minus 1, plus or minus 2, and plus or minus 4. So the potential rational zeros are going to equal, now we take the numerator divided by denominator, and we're going to go through each term. So we do plus or minus 1 over 1, we have plus or minus 1 over 2, so I'm doing it this way, 1 over 1, 1 over 2, 1 over 4, and I'm going to keep going that way. So 1 over 2, and then plus or minus 1 over 4, and then I go with the 2, so we do 2 over 1, 2 over 2, 2 over 4, so we get plus or minus 2 over 1, 2 over 2, 2 over 4, and then now we do our 3's, we get plus or minus 3 over 1, plus or minus 3 over 2, plus or minus 3 over 4, and then we do our 6's, so we get plus or minus 6 over 1, plus or minus 6 over 2, and plus or minus 6 over 4. Now we can simplify and notice that some of these are actually repeats. 3 over 1 is 3, but 6 over 2 is also 3. So when we simplify, what do we get? 1 over 1 is just 1. So we have plus or minus 1. 1/2 is in simplest form, so we get plus or minus 1/2. Plus or minus 1/4. Now, 2 over 1 is just 2, so we get plus or minus 2. And now here we go, 2 over 2 is 1, we already have 1. 2 over 4 is 1/2, and we already have 1/2. Plus or minus 3 over 1, that's just 3, so we can add something else, so plus or minus 3. And then we also can add plus or minus 3/2. And we can also add plus or minus 3/4. And we have 6 over 1. So we have plus or minus 6 over 1 is just 6. And now again, 6 over 2 is 3. We already wrote 3. And 6 over 4, what does that simplify to? That simplifies to 3/2, which we already have. So this is quite an extensive list of potential zeros that we can have. But it may seem like a lot, but think about it. Right before we did this, if I were to ask you list the potential zeros of this function, you would have said anywhere from negative infinity to positive infinity. But now you narrowed it down to just these options. So we have plus 1, negative 1, plus 1 half, negative 1 half. So each of these are 2. So we get 2, 4, 6, 8, 10, 12, 14, 16 possible real zeros or rational zeros. That 16 is a lot better than saying anywhere from negative infinity to positive infinity. So now we're actually going to go ahead and find the real zeros of a polynomial function. And we're going to utilize everything we've learned up until this point. We're going to utilize Descartes' rule of signs. We're going to use the rational zeros theorem. So let's take an example. F of x is equal to x to the 4 minus 8x squared minus 9. What are the maximum number of zeros that we can have? Well, the max number of zeros is 4. That's the degree of this polynomial. What about the maximum number of, or the potential number of positive zeros? The potential number of positive zeros, how many times does it change? This is a positive, it goes to a negative, and that's it. So potential number of positive zeros is 1. What about the negative zeros? So I'm going to go ahead and I'm going to use the right column as scratch work. So to find negative zeros, we write f of negative x, and we plug that in. So that would be negative x raised to the 4 minus 8 times negative x squared minus 9. This simplifies to negative x to the 4th is still positive x to the 4 minus negative x squared, which is positive x squared. So this is x to the 4 minus 8x squared minus 9. And how many times does this sign change? From a positive, it changes once to a negative, and that's it. So there's potentially 1 negative 0. Alright, so we have, there's up to 4 zeros, and a potential number of them is 1 is positive and 1 would be negative. Now, what are the potential rational zeros? Potential rational zeros remember, the potential rational zeros are dealing with the last number, factors of the last number, divided by factors of the first number. Factors of the last number are going to be plus or minus 1, plus or minus 3, and plus or minus 9. And factors of the first number are just plus or minus 1. So potential rational zeros, if we divide, we'd have plus or minus 1 over 1, which is just 1, plus or minus 3 over 1, which is just 3, and plus or minus 9 over 1, which is just 9. So this would have just translated to plus or minus 1 over 1, plus or minus 3 over 1, and plus or minus 9 over 1. So now we have our potential rational zeros, and we have the maximum number of positive zeros and the maximum number of negative zeros. And we know that the total number of zeros we could have would be 4. So now, how do we figure out what the zeros are? Well, if these are potential zeros, if we plug them into our function f of x, it would be equal to 0. So let's plug that in. So we're going to test the point 1. We're going to test the point 1. So we'll put f of 1 is equal to 1 to the 4 minus 8 times 1 squared minus 9. So this is 1 minus 8 minus 9, which is equal to negative 16. Negative 16 is not equal to 0, so we know 1 is not a 0. So we can go ahead and test another point. We'll test f of -1. So we're testing the point -1. And what do we get? We get the quantity -1 to the 4 minus 8 times -1 squared minus 9. And we get that is equal to -16. And since that's not equal to 0, that also is not one of our zeros. So we'll try another point. We'll try 3. F of 3, that would give us 3 to the 4 minus 8 times 3 squared minus 9. In fact, this actually turns out, this equals 0. So we know that a 0 is 3. So 3 is a 0. Now, we already tested 1, -1, 3. We haven't tested -3, +9, or -9. But look here. Could +9 be a 0? We said that the potential number of positive zeros, we can only have 1. And this 3 already eliminated that 1. So instead, we don't even need to check 9 because we know that there's only one positive 0. And this could happen if we had more. If we found that 3 was our first 0 before we even tested 1, we could have crossed off these other ones. So now we need to figure out what's the -0. So we have two options to test from, -3 and -9. We'll go ahead and test f of -3. F of -3 would be negative quantity 3 to the 4 minus 8 times -3 quantity squared minus 9, and that also ends up being 0. So we know that -3 is also a 0 of this function. And since there's only one -0, we don't need to test this last one, -9. We know that it's just going to be 3 and -3. So this is a problem that involves a lot of steps. We went through and did everything that we did before. We figured out what's the maximum number of zeros. We figured out what are the positive and negative potential number of zeros. And then we found out potential rational zeros. And then we went through and tested each of these potential rational zeros. But instead of having to test all of them, we used this earlier information that once we hit the maximum number of potential positive, we stopped. So these are the zeros of the function, 3 and -3. And the last topic we'll talk about in this section is called the intermediate value theorem. The intermediate value theorem says that if we have a function, maybe something like this, a function that goes like that, and if the function is continuous and it doesn't skip, then if at one point, and this is the x-axis, if at one point f of some number a is less than 0 or negative, and some point, we'll call it b, f of b is positive, then in order for it to go from negative to positive, it has to cross the axis. And so at there we say that there exists a c where f of c is 0. And it could go the other way. It could say the function could go from this way. If we said f of a is positive and f of b is negative, then we have a 0 somewhere between a and b. We'll say that 0 is, again, c. F of c would be 0. So in words, what does this mean? If f of a and f of b are of opposite signs, meaning one is positive and one is negative, and if we're going to just assume that A is less than B, then there is a real zero. We're going to say then there exists some number C, where C is going to be between A and B, such that f of C is equal to 0. So we'll go ahead and we'll do an example. And the example would be if our function f of x is equal to 5x cubed minus 8x squared minus 9x plus 6. And I would say use the intermediate value theorem to determine if there is a 0 in the interval, and we'll say the interval would be 2 to 3. Is there a 0 in that interval? Well, we'll test what is f of 2. F of 2 would be 5 times 2 cubed minus 8 times 2 squared minus 9 times 2 plus 6, and this would give us an answer of -4. Okay, we can use our calculators for that, and then we'll test f of 3, so we get 5 times 3 cubed minus 8 times 3 squared minus 9 times 3 plus 6, and what we get here is this is positive 42. So since we go from a negative to a positive, we know that yes, there is a 0 in the interval 2 to 3. A 0 in that interval 2 to 3. Now I happen to know what that 0 is, and that 0 actually is 2.1741 and so forth. So that's the 0. You won't need to know that, but you just want to know, does a 0 exist in that interval? And yes, because we went from a negative number to a positive number, there was a 0 somewhere between 2 and 3. And that's it. If we have a function f of x is equal to x squared minus 4, we know that the zeros of this equation can be found by setting f of x equal to 0. So to find the zeros, we set x squared minus 4 equal 0. If we add 4 to both sides, we get x squared is equal to 4. When we take the square root and solve for x, we get x is equal to plus or minus the square root of 4. So x is equal to plus or minus 2. What if, however, our function were to look slightly different? Our function were to look like f of x equals x squared plus 4. How do we find the zeros to that? Well, similarly, we'll set x squared plus 4 equal to 0. If we subtract 4 from both sides, we get x squared equals -4. Now, if we're looking for real answers, we can't have anything, because when we take the square root, we get x is equal to plus or minus the square root of -4. And we can't take the square root of a negative number if it's real. However, imaginary numbers allow us to do this. We get that x is equal to plus or minus the square root of 4 times the square root of -1, which means that x is equal to plus or minus 2i. Another example would be if g of x were equal to x squared plus 9. Solving for the zeros, we get 0 equals x squared plus 9. Subtract 9 from both sides, we get -9 equals x squared. when we take the square root of both sides, we get plus or minus the square root of negative 9 equals x. The square root of negative 9 can be written as plus or minus the square root of 9 times the square root of negative 1. Square root of 9 is 3, so we get plus or minus 3, and the square root of negative 1 is I. So notice that our answers for x is x equals 3i, or x equals negative 3i. In fact, anytime you have a complex root to a polynomial function, its conjugate will also be a root. So for example, if we have a root that is a plus bi, if that is a root, then a minus bi is another root. In this example, we had 3i was a root, and so minus 3i was another root. This is known as the conjugate pairs theorem. From the conjugate pairs theorem, if I tell you that if negative 3 plus 2i is a root of the function f of x, then the conjugate is negative 3 minus 2i. Notice the plus over here becomes a minus. That's what we get a conjugate. Then the conjugate is also a root. So if I have a polynomial function and the degree of that function is equal to 4, so it's a degree 4 function, and if I tell you that two of the roots of this function are the following: 3 minus 5i and negative 6 plus I. Can you tell me what the other two roots are? Polynomial degree 4 means that there'll be 4 roots. Since two of our roots are complex, we know that the conjugate is also a root. So if 3 minus 5i is a root, then the conjugate 3 plus 5i is another root. If negative 6 plus I is a root, then negative 6 minus I is a root. So these are the 4 roots of some polynomial function. If we had a polynomial function of degree 5 and zeros of the function are 0, 1, 2, and I, can you tell me what the fifth 0 is? Well, if one of our functions is I, the conjugate to I is just the negative in front of the I. So negative I would be our fifth 0. What about if we had another function of degree 5 and the zeros are given by 1, I, and 2i. Can you tell me what the other two zeros are? Degree 5 will have a total of 5 zeros. If I is a 0, then its conjugate is negative I. If 2i is a 0, its conjugate is negative 2i. In real numbers, if we were to have zeros of a function be, for example, the 0 is 5 and 3, then our function might look something like f of x is equal to the quantity x minus 5 times x minus 3. Now, similarly, we can work with complex zeros. So in our first case, our first example, over here, we found that the zeros are 0, 1, 2, I, and negative I. So now we can write our function as f of x equals the quantity x minus 0, which is our first 0, times x minus 1, which is the second 0, times, move this over a little bit, times x minus 2 times the next 0, x minus I, times the last 0, times x minus negative I, or x plus I. Our second function, our zeros were 1, I, 2i, negative I, and negative 2i. So we can write our function f of x as equaling the quantity x minus 1 times x minus I times x minus 2i times x minus negative I, or x plus I, times our last 0, which is negative 2i, so x minus negative 2i, or x plus 2i. Now we'll look at, given a polynomial, solving for all complex zeros. That's the real as well as the imaginary zeros. So take, for example, a function f of x equals x to the 4 plus 5x squared plus 4. How do we factor this? Or how do we find the zeros? Well, this can actually be factored. If we were to let capital A equal x squared, then a squared is x squared squared, which is x to the 4. So we can rewrite f of x as, instead of x to the 4, we can write x to the 4 as being a squared. So f of x is a squared plus 5 times, instead of x squared, we're going to use our substitution of a. So 5 times a plus 4. Can we factor this? Yes, this factors, and this becomes capital A plus 4 times capital A plus 1. If we're solving for the zeros, then we set f of x equal to 0. So if f of x equals 0, we have this equals 0. What was a? We set a was equal to x squared. So we'll make that substitution again. Instead of a, we write x squared plus 4 times x squared plus 1 equals 0. So we're going to have either x squared plus 4 equals 0, or x squared plus 1 equals 0. Subtracting 4 from both sides from this left equation, and subtracting 1 on both sides of this right equation, we get that x squared is equal to negative 4, or x squared equals negative 1. When we take the square root of both sides, we get x is equal to plus or minus the square root of negative 4, or x is equal to plus or minus the square root of negative 1. And so our final answer, x is equal to plus or minus 2i, because the square root of negative 4 is 2i, or x is plus or minus I, since I is the square root of negative 1. So these 4 zeros are our zeros of our initial problem of f of x is x to the 4 plus 5x squared plus 4. Now let's take a look at another example. What if our function f of x were given x to the 4 plus 2x cubed plus 22x squared plus 50x minus 75. What are the zeros of this function? And these can be complex zeros. It doesn't look like this function is factorable like the last example, so we can try something else. What are possible zeros? Possible zeros are taking factors of the last term divided by factors of the first term. So possible zeros could be plus or minus 1, plus or minus 5, plus or minus 3, plus or minus 25, plus or minus 75. So these are possible zeros. How do we find out if one of these possible zeros is in fact a zero? Well, we can plug it in, and if f of a equals 0, then a is a factor of f. Hopefully you remember that from the last section. So let's go down the list. Let's try 1. So we'll try f of 1, and hopefully that will be a factor. F of 1 is 1 to the 4 plus 2 times 1 cubed plus 22 times 1 squared plus 50 times 1 minus 75. Well, what do we get? That's 1 plus 2 plus 22 plus 50 minus 75, and yes, this equals 0. So therefore we can imply that 1 is a factor. So if 1 is a factor, then we can actually factor it out. So let's do synthetic division. Recall our original function is x to the 4 plus 2x cubed plus 22x squared plus 50x minus 75. So we'll use synthetic division to factor it out. So 1, and we have 1, 2, 22, 50, and minus 75. So synthetic division, we bring the 1 down, we bring this number down, so we get 1, multiply 1 times 1, we get 1. Now we add down, 2 plus 1 is 3. And we multiply 3 times 1 to get 3, and we add down, 22 plus 3 is 25. We multiply 25 times 1, we get 25. And we add 50 plus 25, we get 75. 75 times 1 is 75. And so that last term is 0, which is a double check that yes, it is in fact factorable. So if we factored out 1, what we're left with, this is our constant term, 75. This is our term for x. 3 is our term for our x squared, and 1 is x cubed. So since we had f of x, we factored out x minus 1, now we're left with these terms. So we have the function x cubed plus 3x squared plus 25x plus 75. Now, to factor out the right side, this term right here, we could look for other factors, but notice that we can regroup that. So we'll write x cubed plus 3x squared plus 25x plus 75. Our first two terms we'll group together, and our last two terms we group together. What do the first two terms have in common? They both have an x squared, so we can factor out x squared and get x plus 3. The next two terms have 25 in common, and we can factor out an x plus 3. Therefore, this all becomes the quantity x squared plus 25 times x plus 3. So we can rewrite f of x as f of x equals x minus 1. Now instead of this long expression over here, we broke that down into this. So x minus 1 times the quantity x squared plus 25 times x plus 3. Solving for the zeros, we get that x minus 1 equals 0, or x squared plus 25 equals 0, or x plus 3 equals 0. And so therefore, we get x equals 1, or x squared equals negative 25, or x equals negative 3. Now, the x squared equals negative 25, this can be simplified. Solving for x, we take the square root, so we get x is equal to plus or minus the square root of negative 25, or x is plus or minus 5i. So therefore, our zeros of this function will be 1, negative 3, or plus or minus 5i. These are 4 zeros to our function. In section 3.2, we covered finding real zeros of polynomial functions. As a refresher, what is a real number? Real numbers are things such as integers, like 5, negative 32. It could be fractions, such as a third, negative 4 over 5. But in addition to integers and fractions, it can be things such as square roots. The square root of 7. It could be pi. Pi is a number, 3.1415, and continuing on forever. these are all examples of real numbers. Now we know that the square root of 9 is equal to 3. As we discussed earlier, when dealing with real numbers, the value inside a square root has to be positive or 0. It cannot be negative. So what about if we wanted to find the square root of negative 9? In fact, the square root of negative 9 does not have a real answer. So we have to look at something else, something other than real numbers. And this is what we look at and call imaginary numbers. Imaginary numbers have to do with the square root of a negative value. The square root of negative 1, we're going to define that to be equal to I. So I is the square root of negative 1. Now we can try and find what's the answer, or how to simplify the square root of negative 9. Negative 9 can be written as 9 times negative 1. If we're multiplying within a square root, we can split it up into two square roots. The square root of 9 times the square root of negative 1. Now the square root of 9 is 3. So this is equal to 3 times the square root of negative 1 is I, because we said that the square root of negative 1 is I. So we get 3 times I, or 3I, and that is how we find the square root of negative 9. So let's do some examples. What is the square root of negative 49? Well, we can write negative 49 as 49 times negative 1, which is the square root of 49 times the square root of negative 1. Square root of 49 is 7. The square root of negative 1 is I, because recall that the square root of negative 1 is equal to I. That's what we defined it to be. This right here. What about the square root of negative 25? What is that? So similarly, we'll write it out as the square root of 25 times negative 1. So we have this is the square root of 25 times the square root of negative 1, because we're multiplying. The square root of 25 is 5, and the square root of negative 1 is I. A complex number is a number that combines real and imaginary numbers. So a complex number might look like something of the form a plus bi. So an example could be something like 3 plus 5i. 3 is our real part, and 5i is the imaginary part. Other examples might include negative 4 plus 3i. That's also a complex number. Or, what if the real part were 0? That would be 0 plus 6i, which is just 6i. This is an imaginary number, 6i. Complex number is a combination of both a real and an imaginary part. 6i is complex because the real part is 0, but it also has complex components. Similarly, we could say something like negative 3/2 plus 0i, which is just negative 3/2. That's a real number, as we discussed earlier, but it's complex because the imaginary part has a coefficient of 0. Therefore, all real numbers are in fact complex numbers, and all imaginary numbers are complex numbers. What happens if we multiply 4 times 3i? Well, 4 times 3i is 12i. What about if we multiplied 4i times 3i? What do we get? Well, 4 times 3 is 12, and I times I is I squared. But what's I squared? Recall that I is equal to the square root of negative 1. If we square both sides, on the left side we get I squared. On the right side, the square of a square root is just the number that's inside of it. In this case, it's negative 1. So in fact, I squared is always going to be equal to negative 1. So back to our problem, 4i multiplied by 3i is equal to 4 times 3 is 12, I times I is I squared. But I squared, we said, from this right here, is equal to negative 1. So this is 12 times negative 1, or negative 12. Let's do another example, and I'll keep that right there so we can see. 13i times negative 2i. What does that equal? First we'll multiply 13 by negative 2, and then we'll multiply our i's. I times I. 13 times negative 2 is negative 26, and I times I is I squared. But remember, I squared, that's equal to negative 1. So what we get is we get negative 26 times negative 1, which gives us a negative times a negative equals a positive, and we get positive 26. If we were to multiply two complex numbers, say 2 plus 3i multiplied by 1 plus 4i, we multiply the similar way that we would multiply two real numbers when we would FOIL. Okay? So 2 times 1 become 2 times 1 plus 2 times 4i plus 3i times 1 plus our last terms 3i times 4i. Simplifying that, we get 2 plus 8i plus 3i, and our last term, 3i times 4i, become 12i squared. And I squared, recall, is negative 1. So 12i squared is negative 12. So we can rewrite this as 2, 8i plus 3i is 11i. So 2 plus 11i minus 12. 2 minus 12 is negative 10 plus 11i. Let's do another example. 4 minus 2i times 3 plus I. Multiplying out our first term, 4 times 3. So we have 4 times 3. Plus, our next term is going to be 4 times I. Those are our outer terms. So we have 4 times I. And then we do our inner terms. Negative 2i times 3. So plus negative 2i times 3. And finally we do our outer terms. Plus negative 2i times I. Well, does this simplify? 4 times 3 is 12. Plus we have 4i. Negative 2i times 3 is negative 6i. And then last we get minus 2i squared. But remember, I squared is negative 1. So this is minus 2 times negative 1, which is really equal to positive 2. So what we get is 12. 4i minus 6i is negative 2i plus 2, or 10 minus 2i. What about if we multiply 2 plus 3i times 2 minus 3i? What does that equal? Our first terms will be 2 times 2, plus our outer terms will be 2 times negative 3i. Our inner terms will be plus 3i times 2. And finally, our last terms will be plus 3i times negative 3i. Simplifying, we get 2 times 2 is 4. 2 times negative 3i is minus 6i. 3i times 2 is positive 6i. And lastly, we get 3i times negative 3i is negative 9 times I squared. And recall, I squared is equal to negative 1. So negative 9 times negative 1 is positive 9. So we get 4 minus 6i plus 6i plus 9, where the plus 9 comes from negative times negative. So we can look here, our negative 6i and positive 6i cancel, and this is just 4 plus 9, which is 13. But there's something interesting about this 4 and this 9. If you notice, 4 could be 2 squared, and 9 could be 3 squared. So if we have something of the form 2 plus 3i and 2 minus 3i, where the only difference between the two is the coefficient in front of the I changes from positive to negative, your answer could be written as 2 squared plus 3 squared. In the more general term, if we had something of the form a plus bi multiplied by a minus bi, that is simply a squared plus b squared. In our previous example, we had 2 plus 3i times 2 minus 3i, and that was 2 squared plus 3 squared. This is something that we call the conjugate. Going from a plus bi to a minus bi, this is called the complex conjugate. In section 3.4, we're going to look at properties of real functions. The first thing we'll do is find the domain of a function. Recall that a domain is basically all the possible x values that a function can have. So for example, if we had a function h of x is equal to 5x divided by x minus 3, the domain of that function, d, is equal to all real numbers except when it's not possible. When is it not possible? Well, since we have a denominator, the denominator cannot be 0. We cannot divide by 0. So d, our domain, is all real numbers except x equals 3. Another way of writing this is the set of x such that x does not equal 3. So we can do another example where our function g of x is equal to the fraction 7 times x divided by the quantity x minus 2 times x plus 3. Looking at this function, we look at when is this not possible. And when it's not possible, two things we look for. Either having a negative under a square root or having a dividing by 0. In this case, we have two terms on our denominator, x minus 2 and x plus 3. We don't want to divide by 0. When would this first term be 0? When x minus 2 is equal to 0, or when the second term is 0, x plus 3 equals 0. We don't want to divide by 0, so that's why we get this. Therefore, we end up with x equaling 2 or negative 3. Now that's not our domain. Our domain is all values but that. When x is 2 or negative 3, we're dividing by 0. So our answer, the domain, is the set of x such that x does not equal to 2 or negative 3. Sometimes we might have a function f of x equals x plus 9 divided by the quantity x squared plus 2x minus 15. What is the domain for this? Well, in this case, we actually have to factor out the denominator. What does the denominator look like when it's factored? Well, we get x plus 9 on the top, and on the denominator, what we get is we'll start filling out x and x. And now, what factors make 15? What makes 15 is 15 and 1 and 5 and 3. Well, 5 and 3 will give us that 2x, or 2x. So, we'll put in 5 and 3. And filling in, we get positive 5 and negative 3. So therefore, our domain is the set where x cannot equal negative 5 and positive 3. Notice negative 5 and 3. These are actually really important values. So what do they play besides not being in the domain? If we look at the graph of this function, this is the graph of the function. And look at what happens when x is negative 5. It doesn't cross that line, and when x is positive 3, it doesn't cross 3. So when we have these lines that it doesn't cross, these are what we call vertical asymptotes. And our vertical asymptotes are the values that x cannot equal. So our vertical asymptotes is actually x equals negative 5 and x equals 3. How about now we look at an example, f of x equals x plus 3 divided by x squared minus 49. This could be simplified as x plus 3 divided by x minus 7 times x plus 7. The domain we look at and we see we cannot divide by 0. So we're going to have this first term and this second term play effect. So the domain is the set of all x such that x is not equal to 7 or negative 7. Because of this, our vertical asymptotes are equal to x equals 7 and x equals negative 7. These x equals 7, x equals negative 7, they're not points, they're actually lines. They're vertical lines. Now let's take a look at the graph. The graph we see at x equals negative 7, it doesn't cross, and when x is positive 7, it doesn't cross, but the graph is true for all values except for 7 and negative 7, and so that's why our domain is all x except x is 7 and negative 7. Now this vertical asymptote right here at negative 7 and positive 7. Vertical asymptotes have a definition. We're going to say vertical asymptotes are vertical lines where the function gets close to but does not touch that line. And so if we notice with these this function, negative 7 and positive 7, these two vertical asymptotes, these lines that I just drew right here, our function will get close. It keeps coming and coming and coming. It gets closer on both ends, very, very close, but in fact it doesn't actually touch it. It doesn't touch it and it doesn't cross. And that's why these are called vertical asymptotes. Now let's look at this function. If g of x equals negative 3x squared divided by x squared plus 9x minus 22. We can factor out the denominator, and negative 3x squared divided by the quantity, so we're going to have x and x, and factors of 22, well, the only factors of 22 are 1 and 22 and 2 and 11. Well, 2 and 11 will give us 9, so 2 and 11. And since it's positive 9, we're going to put a plus by the 11 and a minus by the 2. So therefore, our domain, D, is the set of x such that x is not equal to 2 or x is not equal to negative 11. The vertical asymptotes are going to be x equals 2 and the other vertical line x equals negative 11. And now let's take a look at the graph. So we notice at 2 we have a vertical asymptote going straight up. It approaches, but it's not actually equal. But we can't really see at negative 11. So let's take a look. Let's zoom out at negative 11. As we zoom out further and further, we see that there is sort of this line that's beginning to form. It's going vertically all the way up, and that's at the point negative 11. We also see this one over here at 2. Well, that's it for vertical asymptotes. What do you think the next topic might be? If we covered vertical, then we'll cover horizontal asymptotes. Consider if we have a function f of x is some sort of fraction. P of x divided by q of x, where p and q are polynomials. They could be a polynomial like x to the 4th plus 5x squared, or any sort of polynomial. Our first rule says that if the highest power on the numerator is less than the highest power on the denominator, then our horizontal asymptote is the line y equals 0. So let's take a look at some examples. If we have y is equal to 1 over x, what is the highest power on the numerator? Well, we can think of 1 as really being 1 times x to the 0. The highest power on the numerator is 0. The highest power on the denominator is 1, is x to the power of 1. Since 0 is less than 1, we have a horizontal asymptote of y equals 0. Because our numerator has a highest power of 0 and our denominator has a highest power of 1. So our horizontal asymptote is y equals 0. Let's take another example. If we have g of x is equal to negative 5x to the 6 minus 37x squared plus 5 divided by 12x to the 8 minus 100. The degree on the numerator right here is 6. So the numerator has a degree of 6. The denominator right here has a degree of 8. The denominator has a degree of 8. Since 6 is less than 8, since the numerator's highest power is less than the highest power of the denominator, it has a horizontal asymptote at y equals 0. What about if we had a function h of x is equal to x cubed plus 5x squared minus 4 divided by x squared plus 2 times x squared minus 2. The highest power on the numerator is equal to 3, is x cubed. So the highest power on the numerator is 3. But what about the denominator? Well, each of these terms, the highest power is x squared, but remember, we're actually multiplying these two terms together. So x squared times x squared is x to the 4. So we have the highest power in the denominator is x to the 4. And that would happen if we were to expand and multiply this out. Since the numerator is less than the denominator in terms of the highest power, the horizontal asymptote, which I'm just going to abbreviate with HA, is given by the equation y equals 0. So this should be the easiest one. When the numerator has a highest power less than the denominator's highest power, our horizontal asymptote is simply y equals 0. Next, we looked at if the highest power of the numerator is equal to the highest power of the denominator. So if we have, for example, function f of x is equal to 12x cubed plus 25x minus 4 divided by negative 4x cubed minus 3x squared. The highest power for each of these is our x cubed on the numerator, and on the denominator it's also an x cubed. Since they're both equal, the highest power is 3. Our horizontal asymptote HA is given by the line y is equal to, we take the coefficients 12 and negative 4. So y is equal to 12 divided by negative 4. In this case, 12 over negative 4 simplifies to negative 3. So our horizontal asymptote is y equals negative 3. So taking a look at the graph, the graph approaches negative 3. So let's take a look at one more example. If we have a function g of x equals 3x squared divided by 2x squared plus 12. The highest power on the numerator is x squared, and the highest power in the denominator is also x squared. So therefore, our horizontal asymptote is really just the ratio of the coefficients. It's y is equal to, our coefficient on the numerator is 3, and our coefficient on the denominator is 2. So taking a look at the graph, we see that the graph goes up to 3/2 or 1.5. It approaches on both sides. It approaches 1.5, and that's our horizontal asymptote. if the highest power on the numerator is one value greater than the highest power in the denominator, then this is what we call an oblique asymptote. And to find that, we use long division. An oblique asymptote, instead of being a horizontal line or a vertical line, is a line that's diagonal. So let's take a look at an example. F of x is equal to x squared plus 9x minus 5 divided by the quantity x minus 3. Now we notice that the highest power in the numerator is 2, the highest power in the denominator is 1. So we have the numerator is 1 power greater than the denominator. So that implies that we have an oblique asymptote. And I'm going to abbreviate that with OA. To find our oblique asymptote, we use long division. We can use synthetic division in this case because our denominator that we're dividing by only has a power of 1. But if it's anything greater than that, we have to use long division. And we'll do an example of that later. But so here's long division. We're going to divide. So we write x minus 3. And then we have x squared plus 9x minus 5. So how many times does x minus 3 go into x squared? Well, it goes in x many times. So we multiply x minus 3 times x and we get x squared minus 3x. And now we subtract. X squared minus x squared is 0. 9x minus a negative 3x gives us, so minus a negative is like adding, so 9x plus 3x is 12x, and we bring down our minus 5. Next we look at how many times can x minus 3 go into 12x minus 5. Well, x goes into 12x 12 times, positive 12 times, and we multiply 12 by x minus 3. So 12 times x is 12x, and then 12 times negative 3 is negative 36. So let's go and move this a little bit more. And so what are we left with? When we subtract, 12x minus 12x is 0. Negative 5 minus negative 36 is positive 31. However, what we're really interested in is this number that we had up here, x plus 12. That, in fact, is our oblique asymptote. Our oblique asymptote is y equals 12 plus, x plus 12. So let's take a look at the graph. We said that our oblique asymptote is the line y equals x plus 12. And so this graph has, you can see this line right here, it can continue, and so therefore that's actually what our oblique asymptote is. And let me pull out a little bit further from this so we can see it a little bit better. So we can see it actually continues on both sides, but we see that there's this asymptote. An asymptote is a line that it approaches but never actually quite passes. So that is our line, and that's the line. Notice that this also has a vertical asymptote right here. What is the vertical asymptote? Well, recall that the vertical asymptote is when we divide by 0. When we look at what is the domain? Well, we have x minus 3. So in fact, it should be the line y equals 3. And if we zoom in to where this point is, we can see it should be about 3. Goes up and down. In the previous example, we could have also used synthetic division. That was because we were dividing by a power of 1. If we were to look at another example, for instance, f of x equals 2x cubed plus 11x squared plus 5x minus 1, all divided by x squared plus 6x plus 5, we're no longer dividing by just x plus something or x minus something. First, look at our highest power in the numerator is x cubed, and our highest power in the denominator is x squared. So the numerator is 1 greater than the denominator in terms of its power. So we know we'll have an oblique asymptote. So to find this, we divide. So we're going to use long division, and we'll write x squared plus 6x plus 5 divided by 2x cubed plus 11x squared plus 5x minus 1. First, look at how many times does x squared go into 2x cubed. Well, x squared goes into 2x cubed 2x times. And we'll multiply 2x by our original x squared plus 6x. So we get 2x times x squared is 2x cubed plus 2x times 6x, we get 12x squared. And then 2x times 5 is 10x. So we'll subtract. I'm going to move this up a little bit. And we're left with 2x cubed minus 2x cubed is 0. 11x squared minus 12x squared is negative x squared. 5x minus 10x is negative 5x, and we'll bring down the negative 1. So now, how many times does x squared plus 6x minus plus 5 go into this new expression? Negative x squared minus 5x minus 1. Well, x squared goes into negative x squared negative 1 times. We multiply negative 1 by that, and we get negative x squared minus 6x minus 5. Okay. And subtracting, we get negative x squared minus negative x squared is 0. Negative 5x minus negative 6x. So a minus a negative, we end up with a positive x. And a negative 1 minus a negative 5, we get positive 4. However, this number is the one that we're looking for, 2x minus 1. So our oblique asymptote is y equals 2x minus 1. So let's take a look at the graph. There is an asymptote right here. In fact, you can see the line of this asymptote is the line y equals 2x minus 1, just like what we found. Do you also notice vertical asymptotes? An asymptote right here and an asymptote right there. Do you know what they are? Well, if we take a look at our denominator, x squared plus 6x plus 5, if we factored that, that's x plus 5, x plus 1. So our vertical asymptotes are x equals negative 1 and x equals negative 5, which is what we found. Negative 1 and negative 5. Finally, we look at what happens if the highest power on the numerator is 2 or more greater than the denominator. In that case, there is no horizontal or oblique asymptotes, and you're done. For example, if we have f of x is equal to 5x cubed minus 3x squared plus 2 divided by 17x minus 5. The highest power on the numerator is 3. The highest power in the denominator is 1. Since the numerator is 2 greater than the denominator in terms of power, there is no oblique asymptotes and no horizontal asymptotes. And this applies to any function. If we have a function g of x is 17x to the 6 divided by 2x squared, notice that the numerator has a power of 6 and the denominator has a power of 2. 6 is greater than 2 and it's greater than 2 by a lot, so there is no horizontal or oblique asymptotes. If we had another function, h of x is 3x to the 100, and our denominator was 5x to the 98 plus 22. Since the power in the numerator is 100, and the highest power in the denominator is 98, that's 2, and that's what we need. Or if we have 2 or more, then there is no horizontal or vertical asymptote. So finally, let me put everything together in one slide. Recall vertical asymptotes, we look at when we're dividing by 0. For horizontal and oblique asymptotes, we look at the highest power of the numerator and the highest power of the denominator. So for this first point, if the highest power of the numerator is less than the highest power in the denominator, our vertical asymptote, or excuse me, our horizontal asymptote is y equals 0. If the highest power in the numerator equals the denominator, then it's the horizontal asymptote we get when we divide just the coefficients. Oblique asymptotes are a little bit harder. If the highest power in the numerator is 1 greater than the denominator, then an oblique asymptote, to find that we use long division. Finally, if the highest power of the numerator is 2 or more greater than the denominator, there is no horizontal or oblique asymptotes. When dealing with vertical asymptotes, our graph cannot cross the vertical asymptote because it's when we divide by 0. It's not in the domain. But horizontal asymptotes and oblique asymptotes, the graph can cross. In section 3.5, we're going to combine everything we've learned about rational functions and examine their graphs. First, I'll begin with a few steps. The first step is factor the numerator and denominator of a rational function and find that domain. Next, we'll write the function in its lowest terms. Then we can locate and plot the intercepts of the function, and using the multiplicity of the zeros, we can determine the behavior at each x-intercept. Then we can locate and plot the vertical asymptotes. After the vertical asymptotes, we'll locate and plot the horizontal and oblique asymptotes. And then we can use the zeros of the numerator and the denominator to divide the axis into intervals. And then we can plot. We'll go over an example, but take a moment to write down each of these steps. Let's begin with an example. Say we have a function f of x is equal to 3x divided by x squared plus x minus 12. We're asked to analyze and graph this function. Step 1 says we need to factor and find the domain. So if we factor the numerator is already in simplest form, but we can factor the denominator. Factoring, we get 3x divided by x squared plus x minus 12 can be simplified. 12 we can get by multiplying 1 and 12. We can get by multiplying 2 and 6, or 3 and 4. If we multiply 3 and 4, the difference of 3 and 4 would give us a positive 1. So we're going to use 3 and 4. X minus 3 and x plus 4. That factors out into x squared plus x minus 12. What is the domain of this function? Recall the domain are all the possible x values. Since we're dividing, we don't want to divide by 0. We'd be dividing by 0 if this first term, x minus 3, were 0, or the second term, x plus 4, is 0. So we cannot have x equaling to 3 from here, or x equaling negative 4 from here. So our domain is the set of x such that x is not equal to 3 or negative 4. Step 2 says write the function in lowest terms. So we actually can't simplify this. If we had a common factor where we could cancel out, let's do that. But in this case, we actually don't have anything. So step 2 is already done. We'll look at step 3. Step 3 says locate the intercepts of the graph. So intercepts. How do we determine what the intercepts are? To find the x-intercept, the y value is 0. That's when it crosses the x-axis. So we're going to set our function for our x-intercept to be 0. 0 is equal to 3x divided by x minus 3 times x plus 4. For this function to equal 0, we need our numerator to be 0, because 0 divided by anything is still 0. So we want 3x to equal 0. That implies that x equals 0. So our x-intercept is at x equals 0. Now we look for our y-intercept. The y-intercept is slightly easier than the x-intercept. The y-intercept is when it crosses the y-axis. That means the x value is 0. So we plug in 0 into our function. F of 0 is equal to 3 times 0 divided by 0 minus 3 times 0 plus 4. But 3 times 0 is 0, so that's actually equal to 0. So our y-intercept is also y equals 0. So both x and y-intercepts are the same thing, mainly it's at the origin. When solving for our x-intercept, which was x equals 0, we found that there's only 1. It has a multiplicity of 1, because this was just x, if it wasn't x squared. And if you recall, from section 3.1, we discussed what happens with multiplicity of a 0. If the multiplicity is an odd number, then it crosses the axis. If the multiplicity is even, then it touches the axis. So the x-intercept at x equals 0, since it's an odd multiplicity, mainly 1, it crosses the x-axis. Step 4, we look at the vertical asymptotes. If you recall, vertical asymptotes can be found by looking at the domain. And since we determined from step 1 that the domain was x cannot be equal to 3 or x cannot be equal to -4, those in fact are our asymptotes. The vertical asymptotes are x equals 3 and x equals -4. The next step, step 5, we look at the horizontal and oblique asymptotes. Recall our function was f of x was equal to 3x divided by x squared plus x minus 12. To determine if we have a horizontal or oblique asymptote, we look at the highest power in the numerator and the highest power in the denominator. The highest power in the numerator is 1 from our 3x, and the highest power in the denominator is 2 from our x squared. Therefore, looking at this, we see that since the highest power in the denominator is greater than that of the numerator, we have a horizontal asymptote. So since we have the highest power in, and let me move this, in the denominator is greater than the highest power in the numerator, we have a horizontal asymptote, and that horizontal asymptote is equal to y equals 0 for our horizontal asymptote. So now let's take a look at everything that we have so far and start graphing. From step 4, our vertical asymptote was x equals 3, so we'll draw a dashed line at x equals 3, and x equals -4. We'll draw another dashed line at x equals -4. From step 5, we have that a horizontal asymptote is at y equals 0. So we draw that. From step 3, we know it intersects the x-axis at the point x equals 0, and it intercepts the y-axis at the point y equals 0, which those are both actually the same point right here at the origin. Step 6 says, use the zeros from the numerator and denominator and create intervals. Our 0 on the numerator was 0 from 3x. So we have 0. Our zeros on our denominator were -4 and 3. So we have, let's move this up first. So we actually can break this off into sections. One section less than -4, one section between 0 and -4, one section between 0 and 3, and then one section that's greater than 3. So let's move this up a little bit first. And now we'll make a table. So first let's pick a point in this first region, less than -4. So let's pick a number, I'd say maybe -5. Then we look at this next region between -4 and 0. I'll pick that number as -1. You could pick anything, but -1 is a nice number to work with. Now we look at our third region between 0 and 3. and we'll call that 1. And finally, we'll look at our fourth region greater than 3. Well, how about 4? Next, we look at what is that function f of x at that value. So what is f of negative 5, f of negative 1, f of 1, and f of 4? Through some calculations, we can find f of negative 5. We plug in negative 5 into 3x divided by x squared plus x minus 12, and we end up with this equaling negative 15 over 8. Solving for f of negative 1, plugging in negative 1, you can see if you use it on your calculator or by hand, this is 1/4. F of positive 1 ends up equaling negative 3 over 10, and f of 4 is 3/2. So this actually gives us 3 points. We have the point when x is negative 5, y is negative 15 over 8. We have the point negative 1 and 1/4. We have the point 1 and 3/10. And last we have 4 3/2. These points are helpful because within each interval, in the interval less than negative 4, all values will all be either all positive or all negative. Since we determined from here that it's negative, all the values will be negative. Similarly, in this second interval between negative 4 and 0, all the values will either all be positive or all negative because it doesn't cross the axis. If it did, we would have found that there was another 0. So they're all going to be the same sign. By plugging in that value negative 1, we found out that it's positive 1/4. So in that interval, it'll all be positive. In this third interval, we found that it's negative. So all the values are negative. And, excuse me, I didn't write negative down there. So 1 comma negative 3/10. And lastly, we look at the interval when x is greater than 4, and we found that that's going to be a positive. So we can go back to our graph and list those points. At negative 5, we're at negative 15/8. That's just under negative 2. So we're about right here. At the point negative 1, our y value is 1/4. So we're positive just up here. At the point positive 1, we're at negative 3/10. So we're going to be down here. And at the point 4, we're at positive 3/2, or 1.5. So we have 5 points filled out so far of our graph. How do we fill in the rest? Let's start with the vertical asymptotes. The vertical asymptote over here at negative 4, we see that our points 1, 2, and 3, they're approaching this line, but the vertical asymptote means it cannot cross. So as it approaches the vertical asymptote, it begins to follow and go straight up that way. So if we connected these lines, we might have something look like that. Similarly, we look at the vertical asymptote over here when x is positive 3. Our line might approach the vertical asymptote, but it cannot cross. So it would look maybe something like that. And we look at our other asymptotes. So now let's look at the point out here at negative 5, comma, negative 15 over 8. Remember, we have two asymptotes. We have a horizontal asymptote right here and a vertical asymptote right here. We also know from the work that we just did that everything in this section will be negative. It will not be positive. And since there's a horizontal asymptote right there, this line would approach the asymptote but not cross. And going down to this vertical asymptote, it would also approach but not cross. Similarly, with our last point out here, we have a horizontal asymptote as well as the vertical asymptote. Since the values will not cross the vertical asymptote, and we also determined it will not be negative from down here, then our graph would look something like this. And that's how you graph this function. F of x equals 3 divided by x squared plus x minus 12. In the first part of this section, we covered how to do each step. Now we'll look at another example. So let's say we want to plot the function f of x is equal to x plus 4 over x. First, let's simplify this. Let's write this as one fraction. So this can be written as something with a common denominator. Our common denominator is x. So our first term of x can be written as x squared over x plus 4 over x, which simplifies to x squared plus 4 over x. Step 1 says to factor and find the domain. Well, this can't be factored any further, but we can find the domain. The domain of this, the domain is all possible values of x. Since we have an x in the denominator, we don't want to divide by 0. That means that x cannot be equal to 0, so our domain is a set of x such that x is not equal to 0. Step 2 says write our function in lowest terms. It's already in lowest terms. Step 3, we want to locate the intercepts of the graph. So we'll look at first of all the x-intercept. So the x-intercept is when y is equal to 0. So we set our function 0 equals x squared plus 4 divided by x. Well, when is x squared plus 4 equal to x? When is 0 equal to x squared plus 4? Well, if we subtract 4 from both sides, we get negative 4 is equal to x squared. X squared can never be negative in dealing with real numbers. So in fact, there is no x-intercept. Next, let's look at our y-intercepts. So for our y-intercept, we're going to set x to be 0. So we're going to put f of 0, which is 0 squared plus 4 divided by 0. Well, what's here in the denominator? We're dividing by 0. We cannot divide by 0, so this is undefined. So in this function, we actually have no x-intercept and no y-intercept. The next step says, let's look at the vertical asymptote. The vertical asymptote is the same as our domain. So the vertical asymptote is x equals 0. Vertical asymptote. Next, we'll look to see if we have a horizontal asymptote or an oblique asymptote. Remember, our function was f of x is equal to x squared plus 4 divided by x. To look at this, we need to examine the highest power in the numerator and the highest power in the denominator. The highest power in the numerator is 2, and the highest power in the denominator is 1. Since the highest power in the numerator is 1 more than the highest power in the denominator, we have an oblique asymptote. How do we find the oblique asymptote? We divide. Well, we could long divide or use synthetic division, but remember, this function was originally in the form x plus 4 over x, where 4 over x was our remainder. So, when we divide, x was the answer we're looking for, and so our oblique asymptote was y equals x. Now let's go and start graphing. So we have a vertical asymptote at 0, which we found. And that's also where our domain is undefined. It's defined everywhere else. We have an oblique asymptote at y equals x. So we have our asymptote line like that. And we also have no intercept, no x-intercept or no y-intercept. So right now we actually have 4 distinct regions. Because we have asymptotes right here, and right here we have a region, one region up here, another region out here, another region down here, and the last region is over here. Those are all distinct regions, but we might not have a point in every region. Step 6 says to look at the zeros of the numerator and zeros of the denominator and break it up into sections. Well, there is no zero in the numerator, and the only zero in the denominator is x equals 0. So we only have 2 regions from 0, and we have the region to the left of it, and we have the region to the right of it. And let me bring this up just a little bit. Okay. Well, let's pick a point to the left. Let's not make it too complicated. Let's just pick the point -1. And the point to the right, I'm going to choose 1. Now let's figure out what is f at -1 and what's f at +1. Plugging that value into this equation, x squared plus 4 divided by 4, so we will plug in -1. -1 squared plus 4 divided by -1, so -1 squared is 1, 1 plus 4 is 5, 5 divided by -1 is -5. And f of +1, we'll plug in +1 into our equation for f of x. That's 1 squared plus 4 is 5. 5 divided by 1 is 5. So we're given the 2 points, -1, -5, and +1, +5. So back to our graph, we have the point -1 and -5. That would be down here. And we have +1 and +5. That would be up here. So we know that we're only going to be in this section and this section, since it's a line. Since we have oblique asymptotes, we're going to at some point follow the asymptote and follow the asymptote up here. Since we have a vertical asymptote over here at 0, our line will also end up following the 0. So if I were to zoom out a little bit, the graph would look something more like that. You gotta get closer to the axis. So I guess I didn't draw it too clearly the first time, but that's an idea of what our graph would look like. We'll do one more example. Say we have a function f of x is equal to the quantity x plus 3 times x minus 5, all divided by x plus 3 quantity squared. So step 1, this is already factored, but we can find the domain. The domain is the possible x values. Since we're dividing, we don't want to divide by 0. This denominator is only 0 when x is 3, so our domain, when x is negative 3. So our domain is the set of x such that x does not equal negative 3. The second part is write the function in simplest terms. Notice that the numerator has x plus 3 and the denominator also has x plus 3. So we can simplify. We can cross out our x plus 3's. So f of x can be written as x minus 5 divided by x plus 3. And that we got by canceling out x plus 3 on the top and one of the x plus 3 on the bottom, since it was squared. Step 3 says, locate the intercepts. To find the x-intercept, we want y to equal 0. When y is 0, it crosses the x-axis. So we set our function equal to 0. We'll use the simplified function right here. So we're going to set 0 equals x minus 5 divided by x plus 3. Since we want this fraction to equal 0, all we need is the numerator. All we need is x minus 5 to be 0. So that implies we want 0 to equal x minus 5. Therefore, our x-intercept is going to be x equals 5. So our x-intercept is at the point where x is 5 and y is 0. And intercept is spelled with an I, so there's an intercept. Okay. Now we'll look at the y-intercept. So the y-intercept. To solve for the y-intercept, we want x to equal 0. When x is 0, that's when it crosses the y-axis. So we just plug in 0 into our function. That means f of 0 is equal to 0 minus 5 divided by 0 plus 3, which is negative 5/3. So our y-intercept is at the point when x is 0 and y is negative 5/3. That's our y-intercept. Step 4 says to determine the vertical asymptotes. Our vertical asymptotes were the values that the domain does not exist. So the vertical asymptote we found, since the domain is not equal to negative 3, our vertical asymptote is x equals negative 3. Step 5, we look at horizontal and oblique asymptotes. Since our equation looks of the form f of x is equal to x minus 5 divided by x plus 3, we look at the highest power in the numerator and the highest power in the denominator. In this case, the highest power is 1, or x to the 1, and the denominator is also x to the 1, which means that they are equal. When the highest powers of the numerator and denominator are equal, we have a horizontal asymptote, and the equation for the horizontal asymptote is just the ratio of the coefficients for the highest power of x and the highest power of y. In this case, it's actually just going to be 1 over 1, or y equals 1. So that's our horizontal asymptote. Let's go ahead and start graphing. So we have a vertical asymptote when x is negative 3. We have a horizontal asymptote where y is 1. Our x-intercept is at the point 5, 0, so I'm going to need to zoom out just a little bit more. So 1, 2, 3, 4, 5. So we have we have an intersection right there at the intercept, and 0, negative 5/3. Negative 5/3 is between negative 1 and negative 2. So we have right there. Looking at step 6, we're going to look at the zeros of the numerator and zeros of the denominator. The zeros of the numerator would be 5, and the zero of the denominator is negative 3. Since our equation is f of x is x minus 5 and x plus 3, so we get 5 and negative 3. So drawing that out, negative 3 and 5. And let me move this down just a little bit. So we pick points. We'll pick one point in the region to the left of negative 3, pick a point in between negative 3 and 5, and a point that's greater than 5. So the first point, I'll pick negative 4. A point between negative 3 and 5, well, 0 seems like an easy number to work with, and then greater than 5, I'll pick 6. So what is f of negative 4? We're plugging in negative 4 into our function, so we get negative 4 minus 5 divided by negative 4 plus 3. And we end up with 9. Next, we plug in 0 into our function for f of x. So 0 minus 5 divided by 0 plus 3, f of 0, we end up as negative 5/3. And finally, we plug in 6 for x, and we end up for that 1/9. So we get 3 more points that we can plot. The point negative 4, 9, the point 0, negative 5/3, and 6, 1/9. So let's go ahead and plot that. And let me move this over just a little bit more. So let me extend this axis, and we had the point negative 4, 9. So that would be a point somewhere up here. We have the point 0, negative 5/3, which we actually already plotted when we found our intercept. Then we'll have a point 6, 1/9. So 6, 1/9 would be something maybe just above here. But keep in mind, we have our asymptotes up here, and then our horizontal asymptotes out there. So these asymptotes mean that we cannot cross it. This horizontal asymptote right here means that our 3 points, 1, 2, and 3, tell us that we're approaching that asymptote. So if we were to fill in the lines, it would look something to that effect. But we also have the vertical asymptote right here. So as it approaches the the vertical asymptote, our curve goes down. And finally, this last point up here, since it's near this vertical asymptote, we can assume that if I zoom out a little bit, it will move up towards that asymptote, and eventually when it moves down, it'll go to this horizontal asymptote. So it will go down like that. In section 4.1, we're going to talk about composite functions. Well, what is a composite function? Say we have a ship that's leaking oil, and as it leaks oil, the oil starts leaking around the ship, and it gets greater, and it keeps increasing, and as more time goes on, we have a greater range of how far the oil spread, and it gets larger and larger. If we wanted to contain the oil, we would need to figure out how far it's going. If we try to stop it going around this way, by the time we end up at the top, the oil might have already expanded. So what we want to do is we want to be able to figure out how far the oil will be at a certain time, so we can maybe set our expansion greater than that, so it'll be just perfect. So what do we need? Well, what if we know that the radius of increase, so the rate that the oil is going outwards, is a rate of the radius as a function of time is equal to 3t. Well, if the radius is 3t, can we figure out the area? Do we know the area given a radius? Well, the area of a circle given a radius is pi times r squared. So say when time is 20 minutes, so when t is 20, what's our radius? Our radius at time 20 is equal to 3 times 20, which is 60. What's the area at time 20? Well, the area is really our radius at time 20, so our area is going to be our area at 60, which is pi times 60 squared, or 3600 pi. So let's move this up a little bit. So where did we get that 60? Where did we get 60 when our area we used, our input was 60? 60 was from our radius. Our radius at time 20. So in fact, instead of writing 60, we could write our area as radius of 20. So this is pi times our radius at 20 squared. So what we have written right here, area as a function of radius of time, that's what we call the composition of functions. Because we have one function, our area, and its input is a second function. So our area is our first function, and the input of the area is another function on itself, r. We write composition of functions as the following. If we have a function f and g, the composition is going to be written as f circle g of x. And that's equivalent to writing as f of the input is g of x. So to solve this, we first figure out what g of x is and plug that into the input for f. So just like with the oil example, we found out what our input was. Our input was our radius. We found the radius and plugged that into the area. But there are many examples we can do, including things such as converting currency and links. So let's rewrite that. F of g of x is equal to f of g of x. Let's do an example. If f of x is equal to 2x plus 6 and g of x is equal to 4x squared plus 3, what is f of g of 4? Well, f of g of 4 is going to be f of g of 4. What is g of 4? Well, let's look at that. G of 4 is equal to, since we know what our function g of x is from right here, g of 4 is 4 times 4 squared plus 3. And so if you calculate that, 4 times 4 squared plus 3, you'll end up with 67. So f of g, or g of 4, excuse me, is 64. So this is f of 64. Well, what is f of 64? Our function for f is defined right here, so that's really 2 times 64 plus 6. 2 times 64 is 128 plus 6, or 134. We can find other compositions of functions, such as we can find f of x. So this is f of the function f of x. Let's figure out what is f of 2. I just moved it up, but what is our function f of x, if you recall? F of x was 2x plus 6. So I'm going to write that over here. Our f of x is 2x plus 6. So f of 2 is, well, we first need to figure out what is f of 2. F of 2 is 2 times 2 plus 6, or 4 plus 6, so that's 10. So we know that f of 2 is 10, so f of 2 is f of 10. And f of 10, well, we'll do the same way. Since f of x is 2x plus 6, we'll find out what f of 10 is. F of 10 is 2 times 10 plus 6, which is 26. So f of 10 is 26. But we can actually find all sorts of combinations. We found f of g of x, but we can also do, I'm going to move this up a little bit, we can find g of f of x, we can find f of x, g of x, and we can even keep going. We can look at f of x, and so forth. Really just any combinations. We can also look at something in a slightly different format. So if we had x and f of x, and we looked at this at a table, so for x is 1, f of x is negative 2, 7, 8, 8, 3, 12, and 13. And then we looked at another table for x and g of x, and we had negative 5, 1, negative 2, negative 8, 1 and 7, and last 3 and 8. If we were to find something such as maybe f of g of 3, how do we find that? Well, first of all, we're going to look at g of 3. What is our g value when x is 3? So this second table is for our g's. So when the x, or the input of g is 3, g of 3 is 8. Okay, so this is, well, f of g of 3, but we know that g of 3 is 8. So this is f of 8. What is the value of f when our input is 8? If our input is 8, the value for f is 3. So this is just 3. And let me just move this a little bit more. But we could find, for example, maybe f of g of negative 5. So that's f of g of negative 5. What's g of negative 5? G of negative 5. When x is negative 5, g is 1. Okay, so that's f of 1. If x is 1, our f is negative 2. And we could do another one. We'll do one more. F of g of 1. So that's f of g of 1. What happens when g is 1? When g is 1, or excuse me, when x is 1, g is 7. So this is f of 7. And what happens when x is 7? F of x is 8. Let's do another example. If f of x is 5x squared plus 1, and g of x is 1 over x, what is f of g of x? So now we're dealing with functions. We're not dealing with just numbers. So f of g of x can be written as f of the quantity g of x. What is g of x? G of x is 1 over x. So this is f of 1 over x. Our input here is 1 over x. Our input for f is 1 over x. So we're going to plug that in to our function. What does the function f do? The function f takes an input and multiplies 5 times the input squared plus 1. So we'll do that. We'll do 5 times our input, which is 1 over x, quantity squared, plus 1. So simplifying this, we end up with 5 over x squared plus 1. And that is our composition. What about g of f of x? So this is g of the function f of x. G of f, our function, f of x, is 5x squared plus 1. So this is g of 5x squared plus 1. But what does our function g do? Our function g takes the input and we write it as 1 over the input. So here, if our input is 5x squared plus 1, g of that function is 1 over 5x squared plus 1. And so notice that f of g of x and g of f of x are two different values. Now, we have that two composition functions are equal if f of g of x is equal to g of f of x. An example of this is if we were to let f of x equal the square root of x and g of x is x squared. What is f of g of x? So that's f of the function g of x. This is f of our function g of x is x squared. So this is f of x squared. Well, if x squared is our input for our function f, we'll plug that right into the square root of x. Okay, so this is going to equal the square root of x squared. The square root of x squared is just x. Now we'll look at g of f of x. So the function g of f of x is equal to g of, what is f of x? F of x is the square root of x. So this is g of the square root of x. Our function g takes our input and squares it. So this will be the square root of x, quantity squared, which equals x. Since our f of g of x is x, and our g of f of x is x, then we know that those two compositions are equal. F of g of x, in fact, equals g of f of x. This is not the case all the time. In fact, this is not the case most of the time. Only sometimes will we actually have this. Say we have another function, f of x is equal to 9 divided by x plus 7, and a function g of x is equal to x plus 2. What is the composition of this function? F of g of x is f of g of x. So g of x, we said, is x plus 2. So this is going to be f of x plus 2. F of x plus 2, looking over here, f takes our input, and we say 9 divided by the input plus 7. So we get 9 divided by our input, which is x plus 2 plus 7. So this is 9 divided by x plus 9. This is our composition of our function. Now let's look at the domain. What's the domain of f of x? The domain of f of x, well, we cannot have a 0 in our denominator. So for the domain for f of x is the set of x such that x is not equal to negative 7, because we cannot divide by 0. What about the domain for g of x? Well, g of x can be possible for all x values. So the domain for g of x is the set of x, all values. Okay. But what about our composition? Our composition, f of g of x, is this. So the domain of our composition, f of g of x, is, well, what? We don't want to divide by 0, so our domain is the set of x such that x is not equal to negative 9. So up until now we've covered functions f of g of x when we're given f and g and we're asked to compute what's the composition. But what if we're given the other way around? So what if we're given some function, let's call this capital H of x, that's really a composition of two functions. Let's say f of g of x. What if this composition, say, were equal to 1 over x squared minus 80? So what we want is we want to find two functions, function f of x and a function g of x. So what do? Well, we look at what's happening. We have two things that are happening. The first thing is a fraction. It's 1 over the denominator. We have another thing that's going on in our denominator. Our denominator is we're taking an x and we're squaring it and subtracting by 8. So if we first look at what's happening with the x, we're taking the x and we're squaring it and we're subtracting 80. Well, we could let g be that. We could let g be x squared subtracted by 80. And now that we have that, if we're trying to find our f would be our other thing that's happening, which was dividing. So f could be 1 over x. So solving for functions f and g given a composition, basically what you do is examine what's happening. We have at one point maybe we're dividing, and we're adding, and we have a square inside. So we can break this into two things, and that's how we can find our f and our g functions. In section 4.2, we're going to cover one-to-one functions and inverse functions. If you recall, a function is a line that passes the vertical line test. So if we're to look at the curve, it passes any vertical line test. If we look vertically, it doesn't have more than one value over any vertical line. Another way of saying that is that for every input, we have exactly one output. So if we were to look at something like this and we had, say, points A, B, and C, and D, E, and F, point A we know goes to just one value. If point A goes to two numbers, that's not a function. But if we had A, B, C, D, E, F, so if A just went to one value, B went to another value, and maybe C went to the same value, that is a function. So that's what a function is. But what is a one-to-one function? A one-to-one function is a function where if you have any two inputs, they have two different outputs. So if we look again at maybe points A and B and C and D, if point A goes to C and point B goes to D, this is a one-to-one function because we have two inputs that go to two different outputs. If instead we had A and B and C and D, and A went to C and B went to C, this is a function, but it's not one-to-one because we have two different inputs giving us the same output, C. What about if we had A and B, C and D? If A went to C and A went to D, and maybe B goes to C. What is this? Well, our function, or our value A, has two different outputs. Therefore, it's not a function. So in words, what a one-to-one function is that any two inputs have different outputs. And so if we're to look at the graph of a function, graph like this is, say, the graph y equals x squared. If we looked at the input, maybe input where x is equal to -2, our value for our f of x equals x squared, f of -2 is -2 squared, which is 4. But what about when x is +2? F of +2 is 2 squared, which is also 4. So what we have here is we put two inputs, -2 and 2, and we came with the same outputs. Now this is a function, but this is not one-to-one. We put values, and they ended up having the same output, the same y value at 4. Okay? So we can tell by looking at the graph of a function if it's one-to-one by looking at a horizontal line. So this is what's called the horizontal line test. The horizontal line test says, just like the vertical test, we write a horizontal line going across, and if the curve crosses the horizontal line more than once, then it doesn't pass. Just like the vertical line test, we move through and see, does it pass the vertical line more than once. If it does, it's not a function. Horizontal line, if it doesn't pass, then it's not one-to-one. Next we look at the inverse function. So a normal function, what it does is it takes an x value and it gives us our y value, or our f of x. What the inverse function does is it starts with our y value, or our f of x, and it goes and it gives us our x. So it goes backwards. It's doing the inverse. We write our inverse function f raised to the -1. It's not actually a power. It's not f to the -1 power. It's just written to look like that. And we call this f inverse of x. Now the domain of a function, so if we have the domain of some function f of x, the domain of that function, if we notice, the domain, this value, x, is really the range of the inverse. So the domain is what goes in, the range is what goes out. So the domain of f of x is equal to the range of f inverse of x. And similarly, we have that the range of f of x is equal to the domain of our inverse. So our range of f of x is this, that's what it goes out to, but that's really the input for our inverse. So that's the domain of the inverse. Let's take a look at the following set of ordered pairs. So if we have a set of ordered pairs, say 4, -9, 2, -8, 0, -7, and how about -2, -6. So if we have this set of ordered pairs, what would the inverse of this be? So the inverse switches our x with our y, our domain and our range switch. So the inverse is going to be the set of, instead of 4 going to -9, it'll be negative 9, 4. Instead of 2 and then negative 8, our x value would be negative 8, and our y value would be 2. Instead of 0 and negative 7, it's negative 7, 0, and then instead of negative 2, negative 6, it is negative 6, negative 2. What's the domain of our original function, or our original set? Well, the domain is just all the x values. So that was 4, 2, 0, negative 2. What about the range? Well, the range were the y values. So we have negative 9, negative 8, negative 7, negative 6. What's the domain for the inverse? The domain is the x value. So negative 9, negative 8, negative 7, and negative 6. And what is our range? Our range is going to be 4, 2, 0, and negative 2. What do we notice? Well, the domain for our original function, 4, 2, 0, negative 2, is the range for the inverse, 4, 2, 0, negative 2. And the range of our original function is the domain of the inverse. So if we have an input x, and we apply our function f of x, we end up x going to f of x. But if we apply our inverse function is supposed to take us going that direction. So if we applied, so this is where we applied f. If we apply our inverse function, what we get is f inverse of f of x. So the inverse of f of x just leads us back to where we started, at x. Okay, so let me write that. F inverse of f of x is just x. That's what an inverse is. And f of f inverse of x is also equal to x. So now let's take a look at two functions. If f of x is equal to 2x plus 4, and g of x is equal to 1/2 x minus 2, are these functions inverses? Remember, two functions are an inverse if f of f inverse of x equals x. So if we take the composition of two functions, and if the composition is equal to x, then they are inverses. So our two functions will be inverses if f of g of x equals x. So if f of g of x equals x, then we have that f and g are inverses. So let's verify. What is f of g of x? G of x is 1/2 x minus 2, so this is f of 1/2 x minus 2. But what does f do? F takes our input and multiplies it by 2, and then we add 4. So this is going to be 2 times our input, which is 1/2 x minus 2 plus 4. Multiplying the 2 out, 2 times 1/2 x, we're left with x. 2 times negative 2 is negative 4, and then we have plus 4. So we're left with just x. So in fact, f of g of x is equal to x. So we have that f of g of x is x. But remember, it's not always the case that f of g of x equals g of f of x. Let me put that in writing. So it is not always the case that f of g of x is equal to g of f of x. So we checked this first one, now we need to check g of f of x. So what is g of f of x? F of x was 2x plus 4. So g of f of x becomes g of 2x plus 4. Our function g is 1/2 x minus 2. So our function g takes a half of the input and subtracts 2. So this is going to be 1/2 of our input, 2x plus 4, and then we're going to subtract 2 from there. Simplifying this, 1/2 times 2x is just x. 1/2 times 4 is 2. So this simplifies, and our 2's cancel, and we're left with x. So g of x does equal f of x. So yes, our original function, or our two functions, f of x equaling 2x plus 4, and g of x is 1/2 x minus 2, they are in fact inverses. So because from these two things we get that f and g are in fact inverses. So every time we want to check the inverse, we need to check both f of g of x and g of f of x. Let's do another example. Verify that the following two functions are inverses. F of x is equal to 7x minus 5, and g of x is equal to x plus 7 divided by 5. To find if they're inverses, we're first going to look at f of g of x. Then that is f of, our function g is x plus 7 divided by 5. What does our function f of x do? Our function f of x multiplies our input by 7 and then subtracts 5. So this is going to be 7 times our input, which is x plus 7 divided by 5. And then we subtract 5. So what do we have? Well, multiplying 7 out, we get 7 over 5 times x plus 49 over 5 minus 5. Right here we see this is not equal to x. So this is not an inverse. F of g, or excuse me, f and g are not inverses. Since f of g of x does not equal to x, then f and g are not inverses. The last thing we're going to cover is how to look for the inverse of a function given its graph. Well, if we're given a graph of a function, say something like this, to plot the inverse, all we have to do is look at the line y equals x and mirror the function off of that. So this is our function f of x. Its inverse is a mirror. Okay, so what would go up here, we're going to reflect it off of this line. So if we have something up there, it goes like that. So we're going to come out and over and out, something like that. It's not the best drawing, but it gives you an idea. Let's look at something a little bit more simple. Say we have a line that might look like that. That's our function f of x. And we'll extend this down some more. We look at the line y equals x, and we reflect. So down this region we're below, so we should be above over here. Since we're above the y equals x, we're going to be below. So the reflection looks something like that. This is our inverse, f inverse of x. I'll do one last example. Say we had a function, maybe it looks something like that. That's our function f of x. And that's our line y equals x. So what does the reflection of this look like? If we're over here, reflected off of this would be over here. So we're going to start over here and draw a line that looks like that. That's our inverse, f inverse of x. And that's it. That's how we draw the inverse of a function. Now we'll take a look at the steps for finding the inverse of a function. So let's take a look at an example. If we have the function f of x is equal to 5x plus 3. The first thing we'll do is we'll write it as y. So step 1 is write it. So write f of x as y. So this will be y equals 5x plus 3. Now the second step is to interchange or we switch our x and our y values. So interchange x and y. So therefore we, instead of writing y, we write x. And instead of x, we write y. And then the third step is to solve for y. So we solve for y. So to do that, we'll subtract 3 from both sides. And so we get 5y is equal to x minus 3. Dividing by 5, we get, and I'm just going to pull this up a little bit. Dividing by 5, we get that y is equal to x minus 3 divided by 5. This here is equal to our inverse function. So our f inverse of x is equal to x minus 3 divided by 5. Now, to double check if it is in fact the inverse, so to check if f of x and f inverse of x are inverses, what we need is we need f of f inverse of x to equal x, so the composition of f inverse, as well as the other way around, f inverse of f of x should also equal x. So let's check that. So remember, f of x is 5x plus 3, and f inverse of x we claim is, or we said is, x minus 3 over 5. So let's find the composition. What is f of f inverse of x? Well, that is f of f inverse of x, and f inverse of x, which we found right here, f inverse of x is x minus 3 over 5. So this is equal to f of x minus 3 over 5. And what does our function f do? Our function f takes the input and multiplies it by 5 times the input plus 3. Since our input is x minus 3 over 5, this is 5 times x minus 3 over 5 plus 3. So what do we have here? We have 5 and we're dividing by 5, so they cancel. And we're left with x minus 3 plus 3, which equals x. So yes, we're good for this first one. So that's a check mark. There we go. Now, we need to also check if f inverse composed of f of x. So that's f inverse of the function f of x. And what is our function f of x? Function f of x is 5x plus 3. And I'm just going to draw a line to separate these two lines. So what does f inverse do? F inverse takes the input x, subtracts it by 3, and then divides by 5. So we take our input, which is 5x plus 3, and then what do? We subtract 3 from there. So subtract 3, and then divide it by 5. So what do we have now? So the 3 minus 3, they cancel, and so we're left with 5x divided by 5. And our 5's cancel, and so we're just left with x. And yes, so we're good. Since f inverse of f equals x, and f of f inverse also equals x, then that means that they are inverses. So let's do another example. What if we had a function g of x is equal to the fraction 4x minus 3 divided by negative 2x plus 5. What is the inverse? So we're going to write this as y equals 4x minus 3 divided by negative 2x plus 5. And now we interchange our x and y's, so x is 4y minus 3 divided by negative 2y plus 5. Now, from here, what we do is we'll multiply by the denominator both sides. So we have x times negative 2y plus 5 is equal to 4y minus 3 divided by negative 2y plus 5 times negative 2y plus 5. Since we multiply both sides by negative 2y plus 5. On the right side, we can cancel out. Now on the left side, let's expand that. So what do we have left? We have negative 2xy plus 5x is equal to 4y minus 3. Now I want all the y's on one side of the equation, so I'm going to add 2xy to both sides. And so we have 5x is equal to 4y plus 2xy minus 3. And if I add 3 to both sides, we get 5x plus 3 is equal to, and on the right side, what we have, both of these have y, and we're trying to solve for y, so we're going to factor y out, and we get 4 plus 2x. 4 plus 2x. So if we're trying to solve for y, what we can do is divide both sides by 4 plus 2x. And so, on the right side, 4 plus 2x cancels, and we're left with y is equal to 5x plus 3 divided by 4 plus 2x. This is our inverse of g. And so we can verify this, and I'll leave this as an exercise for you to verify that this in fact is the inverse. And how would you verify that a function is the inverse? Well, we check that g of g inverse of x is just x, and g inverse of g of x is equal to x. As an introduction to section 4.3, I thought I'd begin with an example. Say we have a species, let's say rabbits. Okay, so we have rabbits. And at each time step, rabbits will have a birth rate. And we'll call this birth rate B, and the birth rate is 0.1 or 10%. So at each time step, 10% of rabbits will give birth. But also at each time step, rabbits will die. So there'll be a death rate. We'll call that D, and the death rate for rabbits, let's say, is 0.03, or 3% of rabbits. So if our birth rate is 0.1, or 10%, and our death rate is 3%, then that's 10% of all the rabbits will give birth. So if we have 100 rabbits, 10% of 100 rabbits would be 10 rabbits. And if we have 3% of 100 rabbits die, then that would be 3 rabbits die. So how do we get that? We multiplied the rate times 100, or the rate times the number of individuals. So now, if we looked at our change in population, so we're going to call that delta P, where P stands for population. The change in population is going to be the birth minus the death rate multiplied by the number of rabbits. Because remember, the birth rate times the population gives us the number being born, and the death rate times the population gives us the number dying. So in our case, say if we had maybe 500 rabbits to begin with, then our change in population would be 0.1 minus 0.03 times 500. And what is that? 0.1 minus 0.03 times 500, well, that's going to be 35. So the change in population for rabbits after one time step will be an increase of 35 rabbits. So our new population, is equal to our old population, which was 500, plus our increase, so plus 35. So we have 535 rabbits. Another way of writing this is saying our new population, let's call that P at our time plus 1, is equal to 500 was our population, so it's equal to P at T, plus 35, and 35 was our delta P, okay? But what was delta P? Remember from earlier we said that delta P is really equal to our birth minus our death rates times P. So we can actually write this as our population at T plus 1 is our population at T plus the quantity B minus D times P. And this P is actually our previous population time. Now, can we factor this? Well, notice on the right side, we both have P sub T. So let's factor out P sub T, and what do we get? We get 1 plus B minus D times P sub T. If we group this all together, 1 plus b minus d, and let's call it just something, say lambda, then we can actually write an equation for our population at time plus 1 is equal to lambda times p sub t. And with the example that we did, when we said, if you recall, our birth rate was 0.1 or 10% and our death rate was 0.03 or 3%, then lambda is equal to, well, remember, lambda is this equation right here, 1 plus b minus d. So lambda is equal to 1 plus 0.1 minus 0.03. And so we get for lambda that is 1.07. So I'm going to write over here our equation. Our equation was our population at t plus 1 is equal to lambda, which was 1.07 times p sub t. So our population is 1.07 times our previous population. If we start off at time equals 0, so if we have our time, and then we have a column for our population at that time. So if we start off at time is 0, p sub 0, if we assume that to be 500, so we're starting off with 500 rabbits. This is what we call an initial value. It's the initial value. So we're starting off with 500 rabbits. Now, when time is 1, what is our population? When time is 1 is going to be p sub t, or p sub 1 is, looking at our equation here on the right, is going to be 1.07 times p sub 0 times the time before, which is 1.07. P sub 0 we had right here is 500. So this is 1.07 times 500. And that is equal to 535 rabbits. So at one time step, we went from 500 to 535 rabbits. When time is 2, so our p sub 2, that is going to be 1.07 times our previous time step, p sub 1. We found p sub 1 to be 535. So this is 1.07 times 535. But what is 535? We found 535 up here by multiplying 1.07 times 500. So we can actually write this as 1.07 times 535 is 1.07 times 500. Okay, so we got this 1.07 times 500 from this line up here. But we have 1.07 times 1.07, so we can simplify. 1.07 times 1.07 is 1.07 squared. So 1.07 squared times 500, which, if we simplify, is 572.45. So what we found is when time is 2, p sub 2 is 1.07 raised to the power 2 times 500, which is 572.45. So now we'll look at when time is 3. P sub 3 is going to be 1.07 times the previous time step, or excuse me, the previous population. That population we just calculated, which was 572.45. So, what is 572.45? So, 1.07 times 572.45 we found right here. That is 1.07 squared times 500. And we can simplify this yet again. So 1.07 times 1.07 squared gives us 1.07 cubed times 500. And that is approximately 612.52. So when t is 3, we have p sub 3 is 1.07 raised to the 3 times 500, or approximately 612.52. We'll do another one. When time is 4, we have p sub 4 is equal to 1.07 times our previous time, our previous population, which is 612.52. But 612.52 we found right here is, so we have 1.07 times, instead of 612.52, we'll write it as 1.07 cubed times 500. And 1.07 times 1.07 cubed gives us 1.07 to the fourth. So 1.07 to the 4 times 500. And this is approximately equal to 655.40. Alright, so at time is 4, we found p sub 4 is 1.07 to the 4 times 500, which is approximately 655.40. Do we notice a pattern? Time is 1, 1.07 to the 1 times 500. Time is 2, 1.072, or raised to the 2 times 500. Time is 3, 1.07 to the third. P is 4, 1.07 to the 4. So, can you figure out what the general equation is, so at p at any time? So at some time t, what would that be? So that would be 1.07 raised to that value t, whatever our time is, times 500. This is our equation for our population at any time. So if we wanted to find the population at time is 100, instead of having to solve 100 equations to get there, if we came up with this formula, we just have to plug in 100 for t. So what does this graph look like? So this is what the equation looks like as we graph it over time. We start off with 500 individuals, 500 rabbits, and one step it becomes 535, and then it increases to 572, and then 612, and then 655, and it increases, and it's starting to increase quickly and more rapidly. This kind of graph is a graph that we call an exponential graph, because this equation is called an exponential function, because there's a variable as an exponent, in this case t, where 500 was our initial condition, and 1.07 is what we call a growth factor. So 500 is our initial condition, or our initial value, and 1.07 is what's called the growth factor. Because at each time, the population grows by a factor of 1.07. So this is what we'll be learning in 4.3. In section 4.3, we're talking about exponential functions. So let's take a look at some of the laws of exponents. So if we're going to say that S, T, A, and B are real numbers, And we're going to assume that A is greater than 0, and so is B, that they're both greater than 0. Laws of exponents say first of all, that if we have some value A raised to the power S multiplied by another value A raised, that is equal to A to the S plus T. So if we multiply two values, A to the S times A to the T, we're actually adding the exponents. So let's take a look at an example. So say we wanted to multiply 2 to the power 3 multiplied by 2 to the power 4. And this looks like the same form as on the left, because they both have 2 on the bottom, but they're both being raised to some power. Now, 2 to the power 3, that's actually equal to 8. 2 to the power 4 is 16. So 8 times 16 is equal to 128. But this law of exponents says that this should be equal to 2 to the 3 plus 4, which is 2 to the 7. And if you calculate that, 2 to the 7 is equal to 128. So we end up with the same values. But that's what we expected, since this is part of the laws of exponents. The next law says that if we have A to the power S, that quantity raised to the T, that is equal to A to the S times T. So if we have A to a power, the whole quantity raised to a power, then we multiply the powers. In the previous one, if we're multiplying two values, we add the powers. Here we multiply the powers. So let's take a look at another example. Let's take a look at the quantity 2 cubed squared. Well, 2 cubed is equal to 8. 8 squared is 64. But according to the law, 2 to the 3 quantity squared should be the same as if we were to multiply our exponents. This should be 2 raised to the power 3 times 2, or 2 to the 6. Well, what is 2 to the 6? That, in fact, is also equal to 64. So 64 equals 64. And we're good. The next law of exponents says that if we have the quantity A times B, that quantity raised to the S, that is equal to A to the S times B to the S. So taking a look at another example, we're going to say, what is the quantity 3 times 2, the quantity squared? Well, 3 times 2 is 6. 6 squared is 36. Or, according to this law of exponents, this should be equal to 3 squared times 2 squared. 3 squared is 9, and 2 squared is 4, and 9 times 4 is 36. So yes, this does verify the third law. The next law says 1 to the S is equal to 1. And hopefully by now you know that 1 raised to any power is going to be 1. The next law says that A raised to a negative power S is equal to 1 divided by A to the positive S. So if we're being raised to a negative power, it's the same as 1 divided by that. Or we could also write this as 1 over A raised to the S. and I'm running out of room, but I have one more law to cover. And the final law is a to the 0 is equal to what? Any number raised to the 0 power will always equal 1. Okay, so these are our 1, 2, 3, 4, 5, and 6 laws of exponents. If you recall from the part 1 video, or a function f of x equals c times a to the x is what we call an exponential function. Now, what would f of x plus 1 be? Remember, a function, f of x, is in this case where we take c and we multiply a to whatever our input is, and our input in this case is x. So what would f of x plus 1 be? And that's a plus. So that would be c times a raised to our input. Our input in this case is x plus 1. So that's what f of x plus 1 is. What if we divided these two functions? If we divided f of x plus 1 divided by f of x, what do we get? Well, let's write this out. C times a to the x plus 1 divided by c times a to the x. Our c's cancel out, and we're left with x to the a to the x plus 1 over a to the x, which we could rewrite this as a to the x plus 1 times 1 over a to the x. 1 over a to the x, if we looked at our laws of exponents, our fifth law, we get 1 over a to the x is the same as saying 1 over a to the x is going to be a to the negative x. So what we have now is we are multiplying a to the x plus 1 times a to the minus x. Since they both have a on the bottom, when we multiply, we actually add the exponent. So this is a to the x plus 1 minus x, or just a to the 1, or a. In other words, our function, if we have an exponential function, and this in fact is a theorem. So if we have an exponential function, f of x is equal to c times a to the x, and we're going to assume that a is greater than 0, and also that a does not equal to 1. If that's the case, then what we have is the division f of x plus 1 divided by f of x is just equal to a. Or, if you prefer, if we multiply both sides by x, what we get is f of the quantity x plus 1 is equal to a times f of x. This value a is really the ratio of consecutive outputs, f of x plus 1 over f of x. So if we're given a table of values for a function, so x and f of x, we're given the values for x and f of x are negative 1, 2, 0, 5, 1, 8, 2, 11, and 3 and 14. Can you tell if this function is linear, exponential, or neither? If it's linear, then the change in rate will be constant. You have a constant slope. That's what a straight line does. If it's exponential, from the theorem that we just did, an exponential function says that the ratio of consecutive outputs are equal. And if it's neither linear nor exponential, then it's none. So let's take a look. So let's take a look at the slope between -1 and 0. Our change in y over our change in x. Our change in y is going to be 3 and our change in x is 1. So that's 3. What about the slope between 0 and 1? The change in y over the change in x, which is, again, 3 over 1, or 3. And if we continue the next two, we find that the change in y over the change in x is 3, and again, 3. So since they have the same slope, this function, the same slope of all three, this function is linear. Now let's look at another example. So we have x, and then we have, let's say, g of x this time. And our values for x will be -1, g of x will be 1/4, 0, 1, 1, 4, 2, and 16, and then 3 and 64. So let's calculate the slope. Delta y over delta x. In this case, that is equal to 3/4. Now let's take a look at the slope between 0 and 1. That slope is 3. So right here we know that this is not linear because 3/4 and 3. So it's not linear, but is it exponential? Remember, if it's exponential, that means that we can be dividing consecutive outputs. So what is the consecutive outputs between x's -1 and 0? What are the ratio of that? So let's divide 1. So again, we're going to do between these two. We're going to divide 1 divided by 1/4. 1 over a fourth is the same as saying 1 times 4 over 1. Since we're dividing by a fraction, 1/4, it's the same as multiplying by that fraction flipped. So 1 times 4 over 1 is 4. Now let's look at the ratio of the consecutive outputs between 0 and 1. So in this case, we're going to divide 4 over 1, which is 4. All right, this is a good sign because we already had 4 for the last one. Now let's look again at the consecutive outputs between 1 and 2. What is the ratio? Well, at 2 it's 16, at 1 it's 4. 16 over 4 is 4. All right, this is a really good sign. And let's finally look at the outputs, the ratio of the outputs between 2 and 3. So that'll be 64 divided by 16. And as you guessed, that's 4. So we had 4, 4, 4, and 4. And according to that theorem we just did 2 slides ago, this is an exponential function. The last example we're going to do is we have x and h of x. Our values for x are going to be -1, and for h it'll be 3, 0, 6, 1, 12, 2 and 18, and then 3 and 30. So let's look at first the slope, delta y over delta x. So this will be the rise over the run, which in this case is 3. So the change in y between 3 and 6 is 3, and the change in x is 1. What is the slope in this? Well, the change in y is 6, the change in x is 1, so our slope is 6. Since 3 does not equal 6, it's not linear. Okay, so we move on and check to see if it's exponential. So in this case, we're going to divide our two consecutive values, 6 divided by 3. And we get 2. Alright, and the next, we're going to divide 12 divided by 6. We get 2. Alright, good so far. For the next one, we're going to divide 18 divided by 12. So 18 over 12, that's not equal to 2. That's equal to 1.5, or 3 halves. So because these two aren't equal, it has to be equal for all the time. Once we find one case where it's not equal, then we know that it's not exponential. Just like over here, when we found two slopes that were different, we knew right away that it's not linear. Recall from the first section, when we plotted an exponential function, the graph of the exponential function looks something like this. And this is if we have a function y is equal to a raised to the x. And we're going to assume that our value for a is greater than 1. What's the domain of this function? What is d? Well, the domain of this function, as we go on, it actually keeps going forever in the positive x direction. And as we go to the left, it also goes forever. So our domain is all real numbers, or negative infinity to positive infinity. But what about our range? Well, we look, our y value keeps going up all the way to infinity, but our x value goes down and approaches the x-axis, but doesn't really cross it, continues to it like it's an asymptote. So our range is 0 to infinity. When does it cross the y-axis? Well, the y-intercept is going to be at the point 0, 1. And the x-intercept, when does it cross the x-axis? Well, it doesn't. So there is none. There is none, but the x-axis is a horizontal asymptote. Some things to notice about this function is that our function f of x equals a to the x is increasing. It's always going up, and it's a one-to-one function. Points that are on this graph include the point 0, 1, 1 comma a, and negative 1 comma 1 over a. But this is all done with the assumption that a is greater than 1. So what happens when a is less than 1 but greater than 0? In that case, the line for y equals a to the x, where a is between 0 and 1, that graph looks like this. And so the domain for this function is all real values, or negative infinity, positive infinity. The range, similarly, is also 0 to infinity. And it also includes the point 0, comma 1. That is our x-intercept. The x-axis, or the line y equals 0, is a horizontal asymptote. But notice this graph is actually a flipped image of the last graph. That's because a is between 0 and 1. And if you think about it, maybe just pick a point over here. Maybe if a is 1/2. If we have 1/2 and we raise it to a higher power, a positive power, maybe 2. 1/2 squared is 1/4. 1/4 is a small value. And we raise it higher and higher, and it goes all the way down this way. And so this graph for f of x equals a to the x is decreasing. But it's also a one-to-one function. And this graph contains the points 0, 1, and now -1, 1 over a, and 1, a. These are the same 3 points that we had on the last graph. But the difference is, if a is a fraction between 0 and 1, 1, a is going to be a small number between 0 and 1, and that's why it goes down. If a were a larger number, say 5, then it would be 1, 5, which would be up here, and that's why we have the other function went up, like this motion. Now there's a special function that mathematicians look at. And if our function f of x is equal to 1 plus 1 over x raised to the x, what happens as x gets larger? In fact, what mathematicians define this as is we call this the number e. So e is equal to the limit when x goes to infinity of 1 plus 1 over x raised to the x. Now there's a value for e, and that value for e is approximately equal to 2.71828, and it actually goes on forever. Just like pi was a number, pi is the number 3.1415 and so forth. E is a number, and you'll see that a lot. In fact, you see it so often that you can find it on your calculator. So you'll see on your calculator e. But we use e with exponents so much that there's even a special function on your calculator for calculating the exponents. And that is the sign on your calculator that says exp with a parentheses around the x. What that means is this key is actually e to some value of x. So if you're trying to calculate e squared, on your calculator you would push this button, exp parentheses x, and so you should get, it come out to exp with a parenthesis, and the squared, this value is your exponent, and you would close the parenthesis, and you would hit enter, and you can calculate your value from there. This value is approximately 7.39. So you can double check your work. The graph of y equals e to the x looks like this, very similar to the graph of y equals a to the x. In fact, since a is greater than 1, that's exactly what it is. The graph of y equals negative e to the x is flipped. And that's, look at, we multiplied our y value by -1. So everything that was once positive, if you multiply it by negative, it goes down. So all the same rules of graphing apply. So if we were to have graphed something like y equals e to the x minus 3, it would have just been the same graph up here shifted over by 3. Or if we had a graph y equals negative e to the x plus 2, what we would have would be this graph y equals negative x just shifted up 2. So in our final section of 4.3, let's take a recap at the laws of exponents. So if we had a to the power s times a to the power t, that's equal to a to the, we are adding this time, s plus t. What if it were the quantity a to the s all raised to the power t? In this case, we multiply. This is a to the s times t. And if we had the quantity ab raised to the power s, this is a to the s times b to the s. And 1 raised to any power s is still 1. A to the minus s is 1 over a to the positive s, which is really just 1 over a all raised to the s. And last, a to the 0 is equal to 1. Now, we also have this property. If a to the u equals a to the v, then u equals v. So using this, let's try and solve some equations. If 7 to the x is equal to 7 cubed, what is x? Well, remember, if they both have the same base, 7, then their powers are equal. So that implies that x equals 3. How about this one? What about 2 raised to the negative x equals 16? What is that? So this doesn't look quite like our previous one. This previous one, they both were written with the same base. The base on the left side of this is 2. The right side of this doesn't even have a base. But wait, can we write 16 as 2 raised to some power? Well, 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. So in fact, we can write 16 as 2 to the power 4. And now we look at our exponents. They have the same base, 2, so the exponents, negative x, should equal 4. So that implies that negative x equals 4, or that x equals negative 4. So let's try another one. 1/4 raised to the x is equal to 1 over 64. So how do we solve a problem like this? Well, what is the left side of the equation? 1 over 4 raised to the x. Well, this is the same as 1 over 4 to the x. And we have, on the right side, we have 1 over 64. Same rules apply. This is essentially the same problem as solving 4 to the power x equals 64. Can we write 64 as 4 raised to something? Yeah, in fact, we can write 64 as 4 cubed. And so therefore, we see, since our exponents need to match if they have the same base, then we can get that x equals 3. How about, let's look at this example. If we're solving for x, we have that 9 raised to the negative x plus 15 is equal to 27 raised to the x. Now, this is different because we can't write 27 as 9 raised to any power. But what do you notice about 9 and 27? Well, 9 can be written as 3 squared. So I'm just going to do a little note on the side. 9 is 3 squared. And 27 is 3 cubed. So we can write our left side of the equation, instead of writing 9, we'll write 3 squared, all raised to the negative x plus 15. And on the right side, instead of 27, we'll write 3 cubed raised to the x. Now what happens when we have a power raised to another power? Do you remember what the law said? We multiply. So the left side of the equation is 3 raised to the 2 multiplied by negative x plus 15. And on the right side of this equation, since we have a power raised to another power, this is 3 raised to the 3x. So, since we have an equation where they both have a base 3, then we conclude that the exponents must be equal. So that implies that 2 times negative x plus 15 equals 3x. And now this is just a simple algebra equation, so let's solve. The left side will multiply by 2. So we get negative 2x plus 30 equals 3x. If I add 2x to both sides, we get 30 equals 5x. Pull this out just a little bit. If we divide both sides by 5, we get x is equal to 6. So what we did in this problem is we noticed that 9 and 27 could be written in this form. Can be written as something that have a common base. We'll do one example that deals with e. Solve for x. If we have e to the 3x equals e to the 2 minus x. Well, they have the same base e, so that means that 3x equals 2 minus x. If I add x to both sides, we have 4x equals 2. I divide by 4. And so x equals 1/2. So let's do another example. Solve for x if we have e to the 4 all raised to the x multiplied by e to the x squared equals e to the 12. Okay, this is combining everything. So what do we do? Well, e to the 4 raised to the x, what is that? We have a power raised to another power. So by the laws, we multiply. So this is going to be e to the 4 times x times e to the x squared equals e to the 12. And now what happens on the left? We have e to a power multiplied by e to another power. What can we do? If we're multiplying, we add the exponents. So this is e to the 4x plus x squared equals e to the 12. So now, since we have an equation that on both sides is e, our powers are equal. So we have that 4x plus x squared equals 12. Do we know how to solve this? Yeah, we do. This is just a polynomial. I'm going to subtract 12 on both sides. And instead of writing 4x before x squared, I'm going to write x squared plus 4x minus 12. I just reordered it and move 12 on the other side. Can we solve this? Well, let's try factoring. Factors of 12 is 1 and 2, or excuse me, 1 and 12, but that doesn't make 4. 2 and 6, yeah, 2 and 6, so let's try that. X plus 6, x minus 2 equals 0. And does that check? Yes. So we get that x is equal to 2 or negative 6. So as you notice, these problems get progressively harder. But as long as you keep in mind all the different laws of exponents, you can break them down into easy steps or simpler steps. In this case, we first looked and combined a power raised to a power. So we got 4x, and then the next thing is we looked at what happens when we multiply, when we add our powers. And then we ended up with a quadratic. In the previous section, we talked about exponential functions, such as something like y equals 3 to the x. The graph of that looks something like this. Now this graph is 1 to 1, and because it's 1 to 1, we know that it has an inverse. This is from section 4.2. So what exactly is that inverse? That inverse is what we call logarithmic functions. A logarithmic function is if we're given a value a, and we're going to assume that a is greater than 0, and also that a is not equal to 1, then the logarithmic function is given by the following equation. Y is equal to log base a of x. Another way of writing this is x is equal to a to the power of y. This equation on the right looks like our standard exponential function that we just saw in the previous section, except our x and y's are switched. It just has an equation, x equals some base a raised to the power of y. This equation on the left, this says that y is really what? Looking at on the right side, y is our power. So we're going to call this the power is equal to something that we call a log or a logarithmic function with a base of a. So a is what we call the base. And x, well, I like to think of x as our answer. So x is really the answer. So if we look at it, we have x, our answer, is equal to our base a raised to the power y. Okay, so this equation on the left is what you'll need to know for logs. And one last thing. Since we're dealing with an exponential function right here, because this can be written as an exponential function, so what is the domain of this logarithmic function? The domain is x values. What are the possible x values? If we looked at this same function written as an exponential, what are the possible values of x? In this case, this equation on the right, our x values are really sort of like what would be our y values, or the range. So if we look at this graph up here, what is the range? The range is all positive values. It just can't be 0 or negative. So our possible x values, or our domain, is that x has to be greater than 0 for any logarithmic function. The value inside the log, or what I call the answer, has to be greater than 0. So let's take a look at an example. Let's say x is equal to log base 2 of 6. Can you write this as an exponential function? So the logs were written as, what was this answer or what is this on the front? This first one is, if you remember, that's the power. Okay. And then this value dropped down a little bit below the g, that's the base. And finally, this last value, our 6, that's sort of what we called the answer. So our answer, 6, is equal to our base, which is 2 raised to our power, x. So when we looked at the logarithmic function, we look at the base raised to the power, and that's equal to our answer. So these two equations, one is the logarithmic function and one is the exponential function. And these two are inverses. The corresponding exponential function for every logarithmic function are going to be inverses. So let's do another example. Log base 12 of 3 equals x. Can we write this as an exponent? Well, our answer, which value was our answer? That was 3. So our answer, 3, so this implies that 3 is equal to our base. Our base is the bottom just below the log. So it's going to be 12 raised to the exponent. And the exponent, or the power, is that. So that. We could have another function. Say we have a function log base e. Log base e of 7 equals x. Okay, how do we write this as a function dealing with exponents? So again, which one is our answer? Our answer is this value right here. So 7 equals, our base in this case is e. So e raised to our power. So we were able to go from logs to exponents. Can we go the other way? Say we have an exponential function that looks like 16 is equal to 4 squared. Can we write that as a log? Well, how are logs written again? Logs are written as log of, what is our base? Our base is 4, so log base 4, and what comes after that? The answer. And this is our answer, 16. So log base 4 of 16 is equal to the power. What's our power? Our power is squared. So our power is 2. And that's it. So we went from writing an exponent to writing it as a logarithm. How about another example? 3 to the x is equal to 7. Can you write that as a logarithm? Well, we begin with log, and then we look at our base. What's the base? The base is 3. So this will be log base 3 of the answer, 7. So log base 3 of 7 is equal to our power, and our power in this case is x. So there you have it. Now we can look at a function, say something like log base 3 of 27. What is that? Well, we can simplify this. So we can begin by saying, well, what does this equal? And we'll use a variable. We'll say this equals x. We'll rewrite this first as an exponential function. This is going to be 3, that's our base, raised to x. X was our power. Remember, this is log of a base. The next this is our answer, and over here is our power. So this is 3 to the x is equal to 27. 3 to what power equals 27? Well, 3 cubed is 27, so 3 cubed is equal to 27. So therefore, we know that x must equal 3. So we can rewrite our log base 3 of 27 as just equaling 3. We can use other values. Say log base 5 of 25. What does this simplify to? So we can say this is some variable x. Rewriting this as an exponent, this is 5 to the power x equals 25, and 25 is the same as 5 squared, which implies that x must equal 2. So our answer for this log base 5 equals 25 is simply just 2. What about if we had another example? Log base 3 of 1 over 9. How do we write that? So again, we'll start again by writing this as equaling x. If we wrote this as an exponent, this is 3 to the x is equal to 1/9. Well, what is 1/9? 1/9 is equal to 1 over 3 squared, since 9 is 3 squared, but since this is a fraction, we can actually write 3 squared, 1 over 3 squared, as 3 to the negative 2. And now we can see 3 to the x equals 3 to the negative 2, which implies x is negative 2. So log base 3 of 1/9 is equal to negative 2. So we already know that logarithmic functions and exponential functions are inverses. So let's take a look at the two. So if we have a logarithmic an exponential function, y is equal to some value a raised to the x, versus a logarithmic function, this y is equal to log base a of some value x. And just a note here that this x, this is not an exponent. It's not a raised to the x. It's a log with a base a, where a is a little bit lower than the log, and x, which should actually be on the same line as the log. Now, what do the graphs of these two look like? Well, the graph of the exponential function, as we had discussed in the previous section, looks something like this, where it crosses at the point 1. If you recall, to graph a inverse of a function, we would look at graphing it, finding the reflection over the diagonal line y equals x. So that reflection actually would look something like this. So that's the graph of the logarithmic function, and it crosses the x-axis at the point 1. The exponential function crossed the y-axis at 1. The logarithmic crosses the x-axis at 1. But what are the domains of these functions? Well, the domain for the exponential function is all real numbers. So the domain, the x values, go from negative infinity to positive infinity. What is the range of this? The range, it goes just to 0 and then all the way up to infinity. but it doesn't actually quite hit 0 since the x-axis was a horizontal asymptote. So it's 0 with a parenthesis to infinity. Now let's look at the logarithmic functions. What is the domain of this function? The domain being the x values. Well, the x values, it goes all the way to just before the y-axis and then to infinity. So the domain is 0 to infinity. And the range is the possible y values, and this is negative infinity to positive infinity. So what do we notice? The domain for the exponential is actually the range of the logarithmic, and then vice versa, the range for the exponential is the domain for the logarithmic. Does that make sense? Well, yeah, it should. Because when we solve for inverses, what do? The first thing we did was we changed x with y. So when we interchanged our x and y, what was once a domain in x becomes a y, the range. And vice versa, what was once a range becomes a domain. So here we have the two domains and the two ranges for logs and exponential functions. But essentially, what we want to think about is we want this value, the x value, or the answer, so to speak. This has to be greater than 0. So let's take a look at some examples. What is the domain of the function f of x is equal to log base 2 of x minus 4? Now remember, the domain is what are the possible x values. Now we're actually looking at what is this so-called answer. When is that answer greater than 0? So what we want is we want x minus 4 to be greater than 0. And so that implies that x has to be greater than 4. That is our domain. How about another example? What is the domain of g of x equaling log base 10 of x squared? Well, the domain is when this value, our so-called answer, is greater than 0. It can't be negative. So we want x squared to be greater than 0. Is x squared greater than 0? So let's look at if x is negative 1. Well, negative 1 squared is positive 1, and yes, that is greater than 0. So this works pretty much for all x values, except one value. What is that value? When is something squared not greater than 0? Actually, if x were equal to 0, 0 is not greater than 0. So the answer for this is all real values except x equals 0. Let's do another example. Say we have f of x is equal to log base 4 of 2x plus 3. What is the domain? So we want 2x plus 3 to be greater than 0. Or 2x has to be greater than negative 3, or x is greater than negative 3/2. This is our domain. And we'll look at one final example dealing with domains. If we had the function g of x is equal to log base 10 of the fraction 1 divided by x plus 1, what is that domain? Now, we want that to be greater than 0. So we want 1 over x plus 1 to be greater than 0. So when is that greater than 0? Let me move this up first. So when is this 1 over x plus 1 greater than 0? Well, we have a division, 1 divided by something. So if we're dividing, we have either, for it to be greater than 0, we need to either have a positive divided by a positive. So a positive divided by a positive is greater than 0, or a negative divided by a negative is also greater than 0. But we cannot have a positive divided by a negative, because a positive divided by negative is negative. And the same thing, negative over a positive. A negative over a positive is also less than 0. We want one of these first two cases, since we are trying to get it greater than 0. But what is the numerator? The numerator is 1. 1 is positive, so we're just dealing with this first case. So that means that we want our denominator to also be greater than 0. So x plus 1 has to also be greater than 0, meaning x has to be greater than negative 1. So that is our domain. Let's take a look at some of the graphs of log functions. So y equals log base a of x. That graph will look something like that, where as it comes down over here, that's actually a vertical asymptote. Now, what would happen if we changed it slightly? If this was y is equal to log base a of x minus 2. So just like with every other function when we graphed, if we subtract 2 to the x, where the x is, that's a shift horizontally. We shift it 2 to the right. Since it's minus, it's the opposite when dealing with x. So that graph, oh, this is a bad line. Let me erase that. Let's see. So let's try that again. Let's say, so the graph, instead of having the vertical asymptote on the y-axis, our vertical asymptote is going to be shifted over 2. So that would be our new vertical asymptote. And so our graph now looks something like that. What about if we were to have written a function y is equal to log base a of x, but we add on to this whole thing a plus 1. Adding a plus 1, just like the other functions, shifts it up 1. So we have a vertical shift up by 1. So instead of crossing the x-axis at the point 1, it crosses now up here. So we have the line looks something like that, going down. What about if we, let's move this up so I have a little bit more space to graph. What about if we had the function y is equal to negative log base a of x? What do we do that? What do we do in that case? What does negative multiplying the function by negative do when we dealt with parabolas and exponents? Negative just flips it. So if we have our axis like that, the negative might look something like that. So that is our graph for negative. So the graphs that we had just done, those were assuming that a is greater than 1. And so when we graphed y is equal to log base a of x, those graphs look something like that. We're across that 1. But what about, just like with the exponents, what about if our a were between 0 and 1? What changes in that case? So maybe if we were to graph something like y is equal to log of base 1/3, so log base 1/3 of x, that graph would look actually something like this. So just like when we dealt with the exponential functions, and our a was between 0 and 1, it was flipped just the same way here. So instead of as x gets larger, an increasing function, it becomes a decreasing function. So it's flipped. And in fact, this function looks very similar to the function of something like y is equal to negative log base a of x. Now there are some log functions that we write so often that we write abbreviations for. And this is log base 10. So any function that's base 10, so log base 10 of x, we write it so often that we just drop the base 10 and we write it as log of x. In fact, it's so often that you see it on your calculator. So on your calculator, when you see log, it's assumed that it's log base 10. Another function that we use so often, just like with exponents, is a base of e, so a log base e of x. We write this a lot of times, and so this is going to be abbreviated with ln of x. ln stands for natural log. And so what do these two functions look like as an exponent? The first one is a base 10. So this looks like, if these were, say, y equals, so if they were y equals, these two functions would look like 10 to the y is equal to x, and e to the y is equal to x. So here we have the inverses of each function. So the inverse of the function log 10x is equal to 10 to the y. And the inverse of this function, or the inverse of natural log, is e to the exponent. So now we can solve problems. Say we have a function where we have an equation log base 5 of x equals 3. How do you find x? Well, when solving, what we do is we first convert it to an exponential function. So this is equivalent as writing 5 to the third is equal to x. Well, what's 5 to the third? 5 to the third is 5 times 5 times 5, or 125. That's our answer. What about using one of the common logs? So log, we're assuming it's a base 10, so this is just going to be a log of 100 equals x. When dealing with this, trying to solve these problems, sometimes we can write it back with this base. So this is actually log base 10, 100 equals x. Now we can write that as an exponent. So this is 10 to the x equals 100. 100 is 10 squared, and therefore we find that x is 2. So what do we do in this problem? Seeing it as it originally was, we might not have been able to have wrote it as an exponent. So we first changed just log 100 to log base 10 of 100. We'll do another similar example. Say we have a natural log. So ln of e to the x equals 5. So this e to the x is actually just one value. So if we wrote this with the base, ln, or the natural log, if you recall, is a log with a base of e. So this log base e of e to the x equals 5. Writing this as an exponent, we have e raised to the 5th power is e to the x. So we get e to the 5th is equal to e to the x, and we see from there x equals 5. So again, in this problem, we changed ln to log base e, and there we could write it as an exponent and solve. What about if we had something like log base x of 1/8 equals 3? Well, we write it as an exponent, so this is x to the 3rd equals 1/8. Now, 8 is 2 cubed. Or we can actually write this as 1/2 quantity cubed. And why did I do that? Because over here on the left, everything is being raised to the 3rd power. If I wrote it like this, our 1 is not being raised to the 3rd. So, but 1 to the 3rd is still 1. So if I wrote it like this, it matches. Therefore, we have x cubed is 1/2 to the power 3. Since our exponents are the same, then our bases are the same. So x must equal 1/2. How about this problem? Solve for x if we have the natural log of e to the negative 2x equals 8. So we write it as a log base e of e to the negative 2x equals 8. And now we write it in exponential form, so we get e to the 8 is equal to e to the negative 2x. And from here, we see that our bases are the same, so the exponent should be the same, our powers. So 8 equals negative 2x. Divide by negative 2, and we get x is equal to negative 4.